Viewers. Okay. It's a good question. Maybe. Okay, we're already online.
Wait for a few minutes.
Okay. Let's wait for a few minutes. I have these.
That's fine.
I want to go over them. So,
Hello. Is this too loud? For you. For Nika, it's okay. I think that would be better when he used it. Well, you can test it. Okay, welcome everyone. Welcome to our early Safari online workshop on memory robustness. It's a bit too early here in Zurich, 8 a.m. Very unusual time for our group because most people wake up pretty late. This is the time many people go to sleep in the group. Not everyone. Some early wakers are here. But this is our first day in a series of workshops that we will hold on some of the research going on in the group and at the cutting edge. Today is going to be focused on memory robustness. And this set of workshops came into being thanks to Giray Yağlıkçı, who is a recent Safari graduate. And he's an incoming faculty member at CISPA Helmholtz. He's going to join there soon. So he's going to be looking for good students over there soon. I'll leave it to him, but we have an exciting program for a full day. We're going to cover a lot of issues in memory robustness, safety, security, reliability, RowHammer, RowPress, real characterization of memory chips, as well as some solutions. And after that, we have another workshop coming on July 14th. That's Monday, right? Monday. And then we're going to talk about health applications, covering a lot of research on bioinformatics, genomics, and accelerating different workloads. And then we'll have another workshop workshop day on July 21st. And then we will cover data-centric and energy-efficient architectures, covering a wide variety of research on memory-centric computing, as well as making things more efficient in the design of hardware. So today is memory robustness. And if you're here, we'll have a break around 10 where people can get coffee and wake up. But hopefully Giray will wake you up before that. So Giray will start the workshop. Go ahead, Giray.
yeah, thanks, Onur. I guess I got yeah. So I just put together a bunch of slides to introduce this Safari Live workshop. In short, I call it SaLWo, and I'm going to explain why. But so before that, why do we have this workshop? Because teaching drives research and research drives teaching, and we have a lot to conduct in research. And as we conduct research, we have a lot to disseminate to the whole world. And the best way of doing that is talking with people, of course, and giving these presentations, but more importantly, have the brainstorming and discussions afterwards so that we can find out what is coming next and talk about future research and stay in the cutting edge, right? And advance the research, basically. And this is our purpose. So in the best scenario, we will have a lot of discussions, a lot of brainstorming. And we have been conducting something similar called Safari Live Seminars. This is a screenshot from YouTube playlist. So this is very similar in spirit. And now we have Safari Live Workshop, SaLWo. Obviously, it's an abbreviation of Safari Live Workshop. And it sounds like the word SaLWo, which means a simultaneous discharge of guns or bombs, but we are not discharging guns or bombs, maybe guns or bombs in the to the difficult research questions. And it means a sudden burst or spirited attack. So this is basically a burst of Safari Live seminars, but in a synergistic way that should foster more fruitful discussion and brainstorming. And we have a website now, as Onur mentioned. We have 3 days programmed today, on next Monday, and the next Monday. So you can reach to all the details in that website, and all 3 days will be live streamed over YouTube. So this is the Safari Live Workshop, and I'm gonna move to the first, or maybe I can talk about the today's program a little bit. I didn't have a slide for that. So today we have several speakers. The first one is me. And then we have Ismail, Hasan, Ataberk, and Nisa in order. And they will talk about, all of us will talk about several cutting-edge research from like past few years. And they're all about memory robustness today. And we will have a break at 9:45 or 10-ish because we started a little bit late. And then we have another break after RowPress talk around like 11. And then we will have a lunch break. Maybe we can keep it a bit short as well. So, and we aim to finish by around like 5 p.m. after Nisa's talk. And we have another coffee break in the afternoon as well. Okay. Oh, okay. So I'm sharing slides. Yes. Okay. So I was sharing, okay, I meant to share this program on the website, but okay, here you don't see anything. Maybe I can just move with the first talk. And I guess I'm not sharing it yet. Share. Okay. Okay, I think it will come soon. Good. So the first talk is about enabling secure and scalable system scaling. So secure and sustainable system scaling. I have a typo there. Okay. So this is me, Abdullah Giray, Yağlıkçı, and I'm currently a postdoc and a lecturer in ETH Zurich as part of software research group. I finished my PhD last year, and this fall semester I'm going to start as a faculty at CISPA in Helmholtz as part of Helmholtz Institute. And I've been conducting research for quite some time. I joined Safari in 2016, so it has been almost 9 years because it was in August. And earlier than that, I finished my bachelor's in Turkey, in Tob University, and then did a master's in University of Notre Dame. And my research interests are computer architecture, memory subsystem, hardware security, dependability, and sustainability, hardware-software cooperation, testing and verification, but the list goes on, so I didn't put everything there. Okay. So today, I'd like to talk about system scaling in 2 aspects. The first one is scaling down manufacturing technology node size. So this allows us to build our chips denser, and it gives us higher performance. It reduces our energy consumption, so everything goes well and better for better. But it comes up with the circuit level failure mechanisms, and to mitigate such failure mechanisms, we had to incur higher hardware complexity into our chips. They consume extra energy and they reduce the chip's availability. So there are also these cons. So this is one aspect of scaling. The other aspect of scaling is scaling out systems in a distributed manner so that we can lower the cost of ownership and we can enable dynamic scaling on demand. So these are really beneficial things, but at the same time, it comes with the concerns of security and privacy, preventing to achieve their full potential. So in an ideal world, systems should scale robustly and sustainably as chips get denser, and many users share those systems. So this is my journey towards robust and sustainable scaling. So I started doing research on energy efficiency, in particular understanding the memory access latency and memory energy consumption of real chips. And later on, I focused on this phenomenon called disturbance that I will introduce in a short while. And then we put more emphasis on research on availability of data and resources. and I'll talk about some future research at the end as well. So I'll directly jump into my PhD research and give a summary of that now. So the main concept that we need to focus on is memory isolation. So imagine that this is your memory and you perform an access to a memory location and you observe a bit flip, data being changed in a different location that you didn't access. You do not want this to happen because it can lead to data loss or corruption. It can compromise your application's correctness, or it can be used against you to leak your private information or even to take over your computer. So when such thing happens, data integrity and confidentiality issues may emerge. And as a rule of thumb, an access to one memory location should not incur unintended side effects on other places. And unfortunately, memory isolation is difficult in modern memory chips today. And here's why. So today we use DRAM, dynamic random access memory, as a prevalent memory technology. And it stores data in the form of charge on a capacitor. And by nature, it's a leaky circuit, and it needs to be periodically refreshed. And there is this phenomenon called DRAM read disturbance. When you access a DRAM cell, it disturbs other physically nearby cells, and it exacerbates their charge leakage. So as a result, you lose your data sooner than you should. Okay, so internally inside DRAM chip, we organize DRAM cells in two-dimensional arrays, and internally we access them in a DRAM row granularity. So to access data in row 2, we need to first open it, and then once we are done and we want to access another piece of data in another row, we need to close this row 2. When we do this operation many times, we observe bit flips in nearby regions, and this can be used to break memory isolation, and it can cause to all those problems that I listed before. So this is a phenomenon that is discovered to be a widespread issue in 2014 in this Philippine Bits paper. And then just a year later than that, Google Project Zero exploited it in system level to take over some computers. And when we do fast forward to 2024, we see a paper from like last year's DRAM Sec basically, showing that Google did another attack to the state-of-the-art mitigation mechanism that Samsung implemented in their chips and was successful at the end. So I just wanted to put this to emphasize that from 2015 to 2024, a lot of research is done, and still we have this issue in 2024. So you can use RowHammer in many different ways. There are a lot of works in the literature that I will highlight some of them that that allows you to conduct RowHammer attacks using JavaScript code on mobile devices. You can use GPUs to accelerate your RowHammer attacks. You can use network packets to hammer rows. You can use RowHammer to leak out some information in a very reliable way. You can attack to some weights in your neural nets so that their accuracy can go from around 90% to 10%. And the research so far shows that error correcting codes, or ECC in short, are not really effective against RowHammer. You can bypass them. And there's a number here, for example, from this paper. You can induce up to 7 RowHammer bit flips in a data work that requires a really strong ECC that is quite expensive today. Another recent paper already showed that RowHammer is an issue in DDR5 devices as well. So with all that, it's also quite simple to mitigate RowHammer. So what you need to do is, if you identify that your row 2 is being hammered, in other words, it's aggressive row, then you just perform an operation called refresh in the physically nearby rows, and it fixes the problem. So the problem, so the challenge here is when to do this refresh, how to do this refresh, where to do this refresh, and there's a lot of work done on that as well. And when we look at RowHammer over years, we observe that with technology not scaling, chips get denser, DRAM cells get smaller, and they get closer to each other. And as a result, you need much fewer activations to perform, to induce a bit flip. And DRAM cells become increasingly more vulnerable due to this scaling. So basically, disturbance or RowHammer are major limitations of technology not scaling in DRAM technology. And existing solutions become prohibitively expensive or ineffective going forward. And we need more efficient and scalable and comprehensive solutions to DRAM read disturbance. So in my thesis, our major contributions are, so our goal is to effectively and scalably mitigate DRAM read disturbance. And to achieve this, we build a detailed understanding of DRAM read disturbance. We looked at its sensitivities to temperature, memory access patterns, victim cells' physical location, and voltage. And also we devised novel solutions leveraging insights into DRAM chips, internals, and memory controllers. So for that, we did leverage heterogeneity across DRAM rows in a DRAM chip to reduce the overheads of mitigations. We parallelized the preventive actions. So these are all hardware level mechanisms that we can implement today at low cost to reduce the performance overhead of and energy overhead of the read disturbance mitigations. And lastly, we have a mechanism that selectively throttles unsafe accesses so that we do not have bit flips in real chips. So I'm not going to cover all of these because of time limitations, but I'll try to do as much as I can. So, okay, let's start with temperature. So for that, we use a infrastructure. This is an FPGA-based infrastructure called DRAM Bander. Basically, we have an FPGA board here that is programmed with our own design called DRAM Bander, and it's open source today, available on GitHub, and it supports several boards. And Ataberk will talk about it, I think. And so we plug in a DRAM module, and we clamp this DRAM module with heater pads from both sides, and we control them by using a commercial controller, and we have a power supply to play with the voltage on certain power rails on the FPGA. So this infrastructure gives us fine-grained control over DRAM commands, timing parameters, temperature, and voltage. And DRAM Bander is available in for different standards for different FPGA boards today. Okay, so we conducted tests on 272 DRAM chips from 4 major manufacturers that implement different densities, die regions, and chip organizations for this study. And we did our best in our testing methodology to run the chips in the worst case conditions. We basically prevent the source of interference during the test by disabling refresh, disabling calibration events, disabling RowHammer mitigation mechanisms, and we finish everything in less than a refresh window so that we don't have retention errors. And we perform the worst case neon access sequence to that day. And we look at the effect of temperature. So in this study, we sweep temperature from 50 degrees Celsius to 90 degrees Celsius. And what we observe is a lower bound and an upper bound of a temperature range. In between, we observe bit flips in a DRAM cell. But outside of this temperature range, if you go colder or warmer, you do not observe bit flips. And we call this temperature range vulnerable temperature range. And when we look at different, basically all the vulnerable DRAM cells to RowHammer, we observe that the vast majority of them exhibit a continuous vulnerable temperature range. And this is quite curious observation, actually. So here's a little bit more detailed data. So in this test, we perform RowHammer by activating rows for 150,000 times to get the bit flips. and we sweep temperature, as I said earlier. So this is a population density plot of DRAM cells. And on the x-axis, we have the lower bound of this vulnerable temperature range. On the y-axis, we have the upper bound of this vulnerable temperature range. And the numbers in each cell shows the fraction of vulnerable DRAM cells. So if you look at this particular point, it tells us that 4.3% of the vulnerable cells are vulnerable to RowHammer, only between 50 degrees Celsius and 60 degrees Celsius. If you warm them up to 70 degrees Celsius, they don't observe bit flips. And we also observe that different DRAM cells are vulnerable to RowHammer in different temperature ranges. So as a result, if you want to buy a DRAM chip, put it in your server, and you need to understand if it's vulnerable to RowHammer at certain condition, you basically need to test it at every possible operating temperature to make sure. And when you look at the data in a more coarse grain, in a DRAM raw granularity, so we look at the temperature on the x-axis here from 50 degrees to 90 degrees Celsius, and on the y-axis we have the fraction of bit flips or bit error rate in a DRAM raw. And we observe that overall, when you warm up the chip, the dominant trend is that it makes the chip more vulnerable to RowHammer because you have more DRAM cells experiencing bit flip. And this is an observation that is applicable for 3 of the 4 manufacturers that we tried. And one of them is showing the opposite trend. And this one is Samsung in the study. But it's not important which one is that, because the more important message here is that based on your DRAM chip design, DRAM manufacturing technology, the relation with the temperature is quite complex, and you really need to pay attention to that in your tests, especially. So what we observe is empirical observations, and this is very similar to a model that is called trap-assisted charge leakage. So this is, excuse me, this is a plot from this particular paper that studies read disturbance or RowHammer in a TCAT simulation model, and they have different charge trap models here. And on the y-axis, we have the RowHammer threshold. So we observe that for different trap models, the RowHammer threshold goes down and up for different ranges, basically. And this is why it happens, as explained in that paper. Increasing temperature helps electron move easier. So it goes to higher leakage and smaller RowHammer threshold. But at the same time, it makes traps lose charge as well, so that the trap-assisted leakage gets weaker. So which one of these like leakage paths will be dominant? It's not for certain, or it's not really like generalizable, because it highly depends on device characteristics, and it varies across cells, chips, and manufacturers quite significantly. Okay, so this temperature study's impact on literature. Sure.
So there's no way you can determine a vulnerable temperature for a cell by some sort of modeling. You have to test every single cell, because very much dependent on cell characteristics. Correct? Or some other easier way to determine temperature.
Okay, so the question is there an easier way to determine which temperature range the cells are vulnerable? To the best of what we know is that you really need to test every cell at every temperature. So we didn't observe any like generalizable trends. As I said, like for 3 of the 4 manufacturers we tested, we observed that the bit error rate increases as temperature increases, but one of the manufacturers observed the opposite pattern. So, and when you look at like different parameters as well, it's hard to find a generalizable trend. So, as far as I know, to this day, there's no like simple analytical model that shows the relation between RowHammer and temperature.
What is the maximum variation?
In terms of AC first, I don't have it here. So yeah, I need to check that actually.
Do you remember what the range is? 5x?
No, actually, okay. So we can say, okay, so we observe bit Phillips at activation. So for these chips, especially, we observe bit Phillips at activation counts at the order of like 10,000, 15,000 activations or hammers. And so these cells observe bit Phillip around this range, right? So this hammer count. And then when you go to a different temperature, even with 150,000 activations, you end up not seeing in a bit Phillip. So it's like an order of magnitude, I would say. Yeah, yeah. Correct, yes. It is, yes. More research is needed, more testing is needed to find such models. Yeah. Other questions? Okay. Can someone monitor the YouTube chat as well? Thanks. Okay, so a follow-up paper from Luis, who was a postdoc in our group earlier. Now he is in Galicia Supercomputing Center. He found a way of finding some canary cells that tells you which temperature the DRAM chip is at. And based on these canary cells, RowHammer vulnerability, it can identify like the temperature of the chip. And based on that, it can monitor remote machine's temperature. So this is an attack that basically spies on a remote machine's temperature by using RowHammer. And it can be used, for example, imagine a cloud environment, and there are some busy hours, and there's a lot of load in the system, and you identify like when it happens, and then you want to start your denial of service attack at that time, for example. So this is that kind of attack that's already a follow-up work of this study. Okay, so I'll move to another aspect of this study. So we tried different memory access patterns, and in particular, so this is the memory access pattern that is known before the study as the worst-case access pattern. So you open and close DRAM rows as frequently as possible so that you can maximize the activation count at a given time. And instead of doing that, we say that let's activate the row and then wait for some time when the row is active. And the idea behind that is that when you activate a row, you basically put some high voltage on some metal layer over there. And that creates some electrical field because of the voltage difference. And we wanted to exacerbate that and see if it has any effect. So we tried this access pattern. And we observed that we can significantly reduce the hammer count needed to induce the first bit flip. And this has an immediate implication on the existing mitigation mechanisms, because if your mitigation mechanism doesn't account for that, then you can easily bypass it. And more importantly, this study it was a preliminary study of these access patterns, and later on, Ha-Sung from our group studied this in a more detailed way, more rigorous way, and then it led to the discovery of RowPress by him. And this is what RowPress does. So I guess I can just say that, you know, as you increase aggressive row on time on the x-axis, as you go extreme, On the y-axis, we have the RowHammer vulnerability, and it goes down significantly. And it goes down by like 1 or 2 orders of magnitude. It's huge difference. And in extreme cases, at like, if you wait for 30 milliseconds, for example, then you only need like 1 activation to induce bit flips. And it's a trend that exists in DRAM chips from 3 major manufacturers. And when we look at later on, Ataberk will talk about this as well, actually. When we look at HBM chips that are quite popular today for the new workloads, like large language models, for example, they're also vulnerable to RowHammer. They're also vulnerable to RowPress, and we can achieve bit flips at only like 335 activations. This takes not really long time, actually. It's a really small number. And more importantly, when we look at the behavior of the benign applications today, even the spec workloads that we keep using for evaluating our architecture studies, they reach to this activation count. So the benign workloads become attacker, and then you need to perform mitigations more rigorously, more aggressively, and the overheads increase, of course. So it's another major limitation against DRAM scaling, right? Okay, so maybe I can just skip this and say that this RowPress is demonstrated to be something that you can do on a real system as well by running some code. And I guess Hasan will talk about all these details anyway, so I'm going to skip this for now to avoid the redundancy. But I want to emphasize that after after we publish RowPress, there are some news articles saying that Samsung and probably some other manufacturers are also concerned about this phenomenon, and they're implementing countermeasures against those. And we will see if they implemented some strong countermeasures. The last piece of characterization study that I want to talk about is RowHammer's sensitivity to voltage. So as I said earlier, when you perform RowHammer, you put some high voltage on some line called, some wire called word line, and then it creates some electrical field around it. And then you do this again many times, and then you observe bit flips. So repeated toggle in the voltage on the word line is causing the RowHammer bit flips. And what we were curious and we show in the study is that if we reduce the magnitude of voltage on the word line, then we can reduce RowHammer vulnerability at the cost of having the DRAM cells at a weaker state. Because when you reduce voltage, then you have smaller charge in the capacitors, and the channel formed in your transistors are weaker. So you need to access them in a slower way, but you can reduce disturbance. And we observe that the reduction is not very great, but also not negligible. Okay, so okay, I have yet another one for the characterization study. So imagine that this gray rectangle represents all DRAM rows in your DRAM bank. And when we look at the 10% of the weakest rows, just identify and cluster them together and say that they need N hammers to experience a bit flip. The remaining 90% of the rows require more than this 2N hammer count. So you need to double the hammer count for the remaining 90%. This shows us that RowHammer vulnerability significantly varies across DRAM rows. And if you configure your solution, your mechanism for the worst case in this study, we show that you're basically overprotecting many rows and make your RowHammer defense mechanism more expensive. And there is a follow-up work that actually exploits this or leverages this observation to make the mechanisms much more efficient. So the key insight is that we have significant variation in RowHammer vulnerability across DRAM rows. And our key idea is to dynamically tune the aggressiveness of these RowHammer defenses to the victim row's disturbance vulnerability level so that we can perform fewer preventive actions if not more than that is needed for stronger rows. And this is a tandem mechanism that works with existing RowHammer solutions. And here is an existing RowHammer solution, Para, proves row activation. So here's how Para works. So when a row activation happens and then you close the row, Para generates a random number. And then compares this random number against the threshold value. And if random number passes the threshold, then Para preventively refreshes the victim rows. So we basically get this victim rows information, feed it into our mechanism called SWERT, and then SWERT dynamically changes the threshold. And as a result of that, if we have less vulnerable victim cells, we have a higher threshold, and as a result, we perform fewer refresh operations, and vice versa. And so SWERT works with many existing RowHammer defenses, as long as they rely on some sort of threshold value, and pretty much all of them require that. And we show how it works with 5 different RowHammer solutions like Para, Aqua, BlockHammer, Hydra, and RRS. And we evaluate the performance impact of this mechanism and show that SWERT reduces the performance overhead of existing solutions and significantly improves the system throughput by doing so. And it can be implemented at low hardware complexity, either inside the DRAM chip or inside the processor. So if your mitigation mechanism is in the memory controller or inside the DRAM chip, it can support any of them. Okay, so improves the systems availability at low cost without compromising data integrity. Is there a question? No, okay. Sure. Maybe I can give you a microphone.
Okay. How about now? Better?
I believe they can
Okay.
hear.
This should be hopefully hearable. So in this, I think this is a very interesting analysis of spatial variation. How easy is it to exploit this? Because you need certainly per row information. And that per row information needs to be determined through profiling, some sort of testing.
Yes, that's true.
Do you already need to determine this information to figure out the lowest HC first in the system for a given chip?
So yes and no. If you want to identify the lowest HC first or the RowHammer threshold in a given chip, you can do the test in a simpler way, actually. Let's say you want to test for 1,000 activation count. You can just hammer every single row for 1,000 activation count and see if there's a bit flip. If there's not, you can try 2,000. If there's not, you can try 4,000, for example. You can go like that. And during your sweep, the first time you observe a bit flip, that determines your worst case RowHammer threshold. In contrast, in this, to leverage this variation, you need to basically find that value for every single DRAM row. Or what we did in the study is a little bit coarser grained than that. Basically, we tried different RowHammer thresholds, like 1,000, 2,000, 4,000, 8,000, like we sweep like that. And we cluster the DRAM rows into each activation counts group based on if they observe a bit flip or not. So we didn't go really like fine grain in finding the exact HC first of every single DRAM row, but we cluster them in like buckets in a sense. So it makes the testing a bit more complex and more time consuming, but not really like to the extreme as well.
Mm-hmm.
And you can choose the granularity of the testing as you want.
Yeah. I mean, I think that makes testing easier, of course. You're not trying to identify the lowest possible. You're trying to bin the rows into different categories based on HC first.
Exactly.
And in terms of implementation, you need to store those bins associated with each row, right?
That's true, yes.
So I don't see that you have evaluated PRAC here, which is the favorite RowHammer solution of everyone these days.
Yes. So
because this was published a few years before PRAC.
True.
So if you have PRAC, not probabilistic, per row actuation counters, does that make the implementation of spatial variation awareness easier?
I believe so. So basically so this is some sort of metadata that we need to store to identify each row's bin in terms of RowHammer vulnerability. And it depends on how many bins you have, of course. Like, let's say you have like only 8 or 16 bins. Now you need to have like 3-4 extra bits for each DRAM row. And this per row activation counting PRAC mechanism already envisions storing around like 10, 11 bits per DRAM row, let's say, inside the DRAM chip. And the premise is that the DRAM technology is dense enough so that it's not too big of a concern, in a sense, I think. So I'm just like assuming this, of course, because I don't know what they think. So the PRAC mechanism assumes that you store like a few bits for the RowHammer threshold, row activation count for each DRAM row. So we can add another like 3-4 bits to each row as well to store it. And since per row activation counting is a DRAM in DRAM mechanism, and it already knows like what is the activation count of a row and when it should perform the mitigation operation. So it can basically like read the bin information at the same time as the activation count and compare it, and then perform the mitigative operation, which is refresh, very easily. And I think it doesn't introduce additional like significant complexity to that. And when you have this, when you exploit this heterogeneity, basically you don't need to block. Okay, yeah, I need to talk about that as well. So per row activation counting needs time to perform refresh operations. So it sends a alert signal, backoff signal back to the memory controller to stop the memory accesses. So it hurts performance and energy consumption, of course. And if you perform these refresh operations less frequently for some rows, of course, it will send fewer backoff signals back to memory controller to stop the whole system. So I guess it will be beneficial in performance and energy-wise as well.
Yeah. No, I think in general, it's a good idea to exploit this sort of variation. That way you can reduce the overhead of all of these mechanisms as you've shown and improve performance and efficiency. Mm-hmm. So another question is, how does this interact with temperature? So you'll need to test both spatially and at different temperature bins.
That's true. So in the study, we couldn't do that because temperature is really complex and it significantly increases the number of tests we need to conduct. So we did it for a constant temperature. Mm-hmm. And we tried in different temperatures as well, showed some similar variations. So it's not like when you change temperature, you have a homogeneous system. But yeah, so to fully leverage this, you need to also test for temperature and spatial variation together. We didn't conduct that in a rigorous way, though.
Mm-hmm. Okay, maybe that's an idea for a future study.
Maybe.
Anybody else?
Another microphone.
Okay.
So you're saying that for SWART, you have bins and you assign the rows in those bins, right?
Yep.
Because of the testing. So what if the HC first changes over time and then you need to reassign it? How would you do that?
That's a really important problem. And I agree that SWART is like, it's one of the weaknesses in SWART because it requires that that information basically to be up to date, right? For security safety. It's a problem dependent from SWART as well, because if you don't leverage this, your worst case hammer count threshold can still change over time if that's a concern, right? So I think it's a separate problem, and to address that, we need to invest more on and conduct more research on online profiling methodologies so that we can keep our information up to date. Does it answer your question?
Yes, I thought that because here you need to consider all rows, right?
Yes.
You need to make sure that all rows they're in their bins. But I'm not sure if it's the case, but once you figure out the weakest cells that you show in deeper look, right? Like 10% of them are actually the weakest. So for them, maybe it's easier to characterize. But in SWART's case, you need to actually monitor all of them, like whole 100%, right?
That's true, yes.
So maybe that could be a difference. And also like aging.
But there's also not a guarantee that, you know, maybe in future, like a row from that 90% chunk will be the worst row.
That's also true, yes.
So you need to test all the rows. So SWART's added complexity is that you need to test all the rows for several different hammer counts instead of just like one or two. So it linearly increases the testing time or testing complexity, but other than that, like the remaining problem is there without SWART as well.
Yeah, regardless, to understand which one is the lowest, like weakest, you need to test all. Yeah, that's true. Yes. Thanks.
Thanks. Other questions? Okay. Can I get the microphone? Yeah, so I'm not sure if it was audible, so I'm going to repeat the question. So the question is if we found any correlation between the variation in RowHammer vulnerability and variation in other problems of DRAM like retention time or other things. So I spent quite some time. So it's not in this paper because we couldn't find any strong correlation. I spent quite some time and I didn't observe anything. It doesn't mean that there's no correlation. It's still like an open research question, and I think more rigorous studies need to be conducted on that. Does that answer your question? Okay, thanks. Any other? No. Okay. Let's look at from a different look at RowHammer issues from a different angle. This is about compatibility, so I'm gonna move back to very high level. So in the application level, how we access memory is that we deal with virtual memory addresses, right? And then when you go to the system level, you translate these virtual memory addresses to physical memory addresses. And then in the memory controller, you get this physical memory addresses and then parse it into the logical addresses of DRAM bus, basically which channel of DRAM, which rank, which bank you need to go, etc. And all these translations are visible within the processor. And when you send these logical addresses to DRAM chip, internally inside the DRAM chip, some of these processor visible addresses, such as row addresses, for example, are translated again to physical row addresses. And this is something done for making optimizations in the DRAM circuitry and also repairs after the manufacturing. So it has some insights into the manufacturing quality and also the DRAM design. And that's why this information is proprietary. DRAM manufacturers do not want to disclose this information. And with this translation knowledge, when RowHammer attack hammers row A, here's what happens. So let's say you have a mechanism in your processor that identifies this row A being accessed very frequently. It performs a refresh operation targeting A+1 and A-1. And this can fall into really irrelevant locations in your physical DRAM. And your actual victim rows can still experience bit flips, and this is an issue. And many existing solutions rely on this proprietary information because of the obfuscation in this interface. So RowHammer provides, this is our mechanism, provides an alternative approach. If it identifies a row A is being hammered, what it does is that it detects this hammered row and then selectively throttles the accesses targeting this particular row. And as a result, you can avoid redisturbance bit flips in the actual victim rows. And you do not need the knowledge of this in DRAM address translation at all. So this work was done in 2021. Actually, it was submitted several times, I guess, starting from 2019. It took like 2 years to get it accepted. And then it was published. And then an update to DRAM standards introduced something called DRFM, Directed Refresh Management command. So there's no direct reference to this work, but I think this work already increased some awareness on this issue. And this directed refresh management gets this row A's information, passes it to DRAM, and then inside the DRAM, it identifies which victims to refresh and then performs refreshes on those. So this is that work, RowHammer, and we evaluated the performance impact of RowHammer. So there's something curious here as well. Not curious, it's very straightforward and intuitive actually, but it's quite important, interesting. So if there's no RowHammer attack in your system, you basically do not throttle any memory accesses because you selectively throttle when there's a RowHammer attack. So the performance and energy overheads are quite small. But when there's a RowHammer attack present in the system, by nature, the RowHammer attack wants to activate rows quite frequently for large activation counts. And RowHammer is quite good at identifying this behavior, and it throttles those accesses. So it punishes the attacker basically, and it improves the system performance and energy consumption quite significantly by throttling the attack and opening up more bandwidth for the concurrently running benign applications. Okay, so that was RowHammer, and there's a list of papers in my PhD dissertation that I didn't cover all of them, but I wanted to put a list here. But we covered all of them in earlier software live seminars, actually. There's one live seminar that's focusing purely on the characterization works that I briefly talked about today, and also about solutions as well. So I want to refer you to those talks and to talk with me for more details and more discussion. I wanted to highlight one more thing about RowHammer. Today, in 2025, after 11 years since RowHammer is shown to be a widespread issue, we have quite some interest still in the academia and in the industry to RowHammer. So not earlier this month, late last month, June 21st, there was a workshop called DRAM SEC that was conducted, that was held with, collocated with ISCA 2025. And it was pretty much mostly focused on RowHammer issue and what we should do as the system builders. And there were attendees from NVIDIA, Microsoft, Micron, and Samsung. So there's a full footage of this workshop available on YouTube. So please go and check the discussion over there. It was quite interesting. And also there was a session dedicated to RowHammer in the main conference as well. Okay, so with that,
before you go on, maybe I have some questions. First, I have a correction over here. RowHammer was shown to be a major issue earlier than 2014, but the first RowHammer paper we wrote got rejected. It could have been published in 2013 actually, but reviewers delayed progress as they normally do in this case. It's good to put it on record one more time. Second is, yes, there was a lively discussion in the DRAMsec workshop later last month, and there were actually other people present from other companies like Rambus, and I'd encourage people to look at that because everything's online. It gives you a sense of the state-of-the-art discussions on RowHammer. I think one of the issues is people are too focused on this industry standardized protection methods like PRAC, per row activation counters, but we need probably more creative ways of thinking about solutions. And I like BlockHammer. I'm going to get back to BlockHammer because it's a different way of thinking about a solution, right? A lot of the solutions proposed to RowHammer are proactive refresh or some sort of basically preventive refresh, let's say. But BlockHammer does throttling. So how do you see these two things to be combined? Is there a way to combine them so that you can actually scale the solution to a much lower threshold?
I will talk about it actually.
Okay, you'll talk
Yes.
about it. Okay, you'll get to it. That's good.
Yeah,
okay, maybe I'll ask the next question when you talk about that, because it's going to build on that probably.
Okay.
Okay.
Yeah, thanks for the correction as well. I'll fix the slides later on. Okay, so that was done in my PhD, and then in the last year, we also focused more on the availability of data and resources in existence of disturbance issues and the overheads of the mitigations. I'll try to quickly cover them, so I'm running out of time actually. Sorry, Ismail, you're the next. Okay, so meanwhile in industry,
we can have a longer day.
Of course, yes. In industry also reacted to this RowHammer research, and JEDEC, the body that defines the DRAM standards, formed the RowHammer task force, and the manufacturer's attitude changed over time from denial to solution. In the early days, they were just denying that there's RowHammer vulnerability in DRAM cells, and the words from our group, from Kave's group, from other groups, repeatedly show that even from the system level, you can exploit RowHammer vulnerability and mount effective system level attacks. So they changed their attitude from denial to solution in a way that one, for example, manufacturer, relatively smaller manufacturer, released a patent on RowHammer solutions. And we looked at the security analysis of that solution as well. It's a paper on arXiv. And then we also observed other papers coming up from Microsoft, from SK Hynix, Samsung, NVIDIA, and another paper that I mentioned earlier, Google, hacked the Samsung solution from 2023, for example. So industry is also working on that, and there is an increased awareness on this RowHammer. So JEDEC released 2 documents that are not very helpful to provide some information to system builders and DRAM manufacturers to talk about ways of RowHammer mitigation. But then later on last year, they released the update to DDR5 SDRAM standard with the first promising update after a decade of RowHammer research. And it's called PRAC, per row activation counting in DRAM. And that's the mechanism that we were just talking about with Onur just a minute ago. So we went ahead and investigated this RowHammer solution that Jadek introduced, and it was presented in last year's DRAM SAC workshop. And we show that it is secure against RowHammer, yes. And it comes at the cost of like storing activation count values for every single DRAM row in the DRAM chip. And it increases the latency of closing the DRAM row quite significantly. And it causes around 10% performance degradation for benign workloads. And it can be exploited by memory performance attacks and can be, you can perform a denial of memory service attack, basically, by reducing DRAM's availability by 94% in extreme cases. This is how PRAC works. So it's called per row activation counting. The tracking of the row activations and the access patterns all done inside the DRAM chip. So you maintain an activation counter for each DRAM row and update the counter when a row is closed, basically. And to mitigate RowHammer, basically, you need to internally perform preventive refreshes, and you need time to borrow from the memory controller to perform these refresh operations. And to enable that, they allow the DRAM chip to send a signal back to the memory controller called backoff signal, alert backoff in full name. And it tells the memory controller to stop accessing that particular bank or rank. And as a result, memory controller provides DRAM chip with some time to perform the preventive refresh operations, and it performs the preventive refresh operations, and no bit flips survive. Okay, so far, like the mechanism makes sense, right? But the devil is in detail. So our analysis show that, in particular, this detail, updating the counter of a row while the row is closed is an issue. Because it incurs around 10% slowdown in the common case for benign workloads. And the reason is that when you close the row, you want to close it as soon as possible so that you activate another row, serve another memory request, right? But now you need to update your counter. To do that, you need to perform a read operation and then increment the counter value and then write it back and then close row. So it takes quite some time, and it increases the latency of closing the DRAM row by 140%. It's quite significant increase. And as a result, it translates to like 10% system scale slowdown. And so to address this issue, we came up with another idea called Cronus. Cronus makes this industry's best solution much better than what it is today. So it basically updates the row activation counters in parallel to column accesses of DRAM rows. And how we do that is we leverage subarray level parallelism. And when we do this, Cronus significantly reduces PRAC's performance overheads from around 10% to 0.04%. So it basically mitigates pretty much all the performance issues of that. So here is how it works. So in a DRAM bank, this is a cartoonish picture of DRAM bank. You have multiple smaller arrays of DRAM cells, those two-dimensional arrays. And these subarrays pretty much work independently most of the time, but they share some common I/O. So they already exist, like many of these subarrays exist in a DRAM bank, and we append a even smaller one on the top. Of course, it's on the top on this cartoonish picture. It can be anywhere. And we have a row buffer for this. We have a row decoder, and we have an increment logic here. We did all design in the paper. You can find details. So basically, we store the counter values of these rows, not inside the rows, but inside the rows in this additional counter subarray here, so that once we access a row, perform a regular access to these regular subarrays, at the same time, we can also activate a row here, get the counter value, increment it, and write it back. And we can overlap these latencies. They can completely be in parallel. And by using the subarray level parallelism, we can reduce the overheads. So this work is published in HPCA earlier this year in March. And all the implementation is open source on GitHub, so you can try it yourself as well. Another work I wanted to mention.
There's a question by Ismail over there.
Ah, sorry. Yeah, I can repeat.
And go back one slide here. So here you store counters in a DRAM subarray, right?
Yes.
And if I just have access to each row in the one subarray, I'll need to activate, for example, the first row of the counter subarray repeatedly. Basically, I can hammer the counters rows in the counter subarrays. So
yes.
That could introduce some RowHammer bit flips in other counters.
Yeah.
How would Kronos solve that issue?
Yeah, it's okay. It's in high level. It's the issue that's like really common in many works, I guess. Like, okay, you protect some data, and to protect data, you also store some metadata. So how do you protect the metadata? And here we need to protect the bits inside the counter subarray. So and you can quite significantly hammer those if you craft an access pattern really carefully. Yes, that's true. And to do that, we discussed several different solutions. Basically, we can do the same refresh operations here as well. Basically, keep the count of these rows as well, and then refresh them. Another way that we discuss in the paper is to implement the mechanism called rega. Basically, whenever a row is activated in that counter subarray, we have, so it's a bit abstracted out here, but in this row buffer, you have an array of sense amplifiers and then an array of latches over there. And whenever you activate one of the counter rows, you latch the information. And then meanwhile, you refresh other rows in the counter subarray. So by doing that, you keep all the rows quite refreshed all the time. And it can reduce the chance of RowHammer. Well, it can prevent RowHammer bit flips. And I think that the performance overhead of that is also taken into account in the evaluation.
Yeah, also like the counter subarray is pretty small, right? You can have like similar to ZRAM, like where you add some dummy rows between each counter rows.
Yes. Yeah, we also discussed ZRAM.
Oh, okay.
Yeah, I remember that. I guess you wrote it. Okay. Yeah, yeah, you can put some isolation because while in regular subarray you have like around 1,000 rows, in the counter subarray you have, I don't know, 60 rows, 100 rows, something like that. Okay, any other questions?
So this counter subarray is actually a specialized subarray.
True.
Its goal is to store, update counters and enable mitigating actions.
That's correct, yeah.
So that complicates the design.
That complicates the design, yes. And we need an incremental logic very close to that counter subarray.
Yeah.
Yes, it complicates the design.
So how many counter subarrays do you have per bank?
It's just like one counter subarray for bank.
Okay.
And in a bank, you have like hundreds of regular subarrays.
Okay.
So I think it's still relatively a smaller overhead. Like without this counter subarray, you still need to store all those counter values.
Mm-hmm.
So you need to make the DRAM bank like larger in horizontal way, but now you made it like larger in vertical way, and you can add some extra logic because it's at the edge of the DRAM bank. I mean, it can be anywhere in reality, but yeah, you can manufacture it at the edge of the DRAM bank, and you can put some specialized circuitry there.
Mm-hmm. Okay, It just makes the now you design two different kind of subarrays, right?
That's true. Yes.
With PRAC, you have only one kind of subarray.
That's correct. Yeah.
Yeah.
But you have also quite significant performance degradation just to mitigate RowHammer bit flips.
Yeah, I agree. Yeah. I think it could be a good trade-off, and we should be changing the DRAM architecture as opposed to trying to keep everything the same, which will not lead to any advance if you try to keep everything the same.
Yes.
That's by definition, I guess.
Yeah.
But people don't seem to realize this very well in research as well as industry. If you don't change anything, you don't advance.
Sure.
The other question over here is, how does this affect TFAW?
Okay. So TFAW is a constraint for activation window, and it's related to power limitations of the chip. So now you need to activate two rows, one in the regular subarrays, one in the counter subarray, and it potentially increases your power consumption. And yes, it can like change the requirement from your power delivery circuitry, and with the current circuitry, it might cause some issues with TFAW, but I think it's also subject to change when we do this kind of specialized subarray. And the subarray, as I said earlier, while answering Ismail's question, that the counter subarray is quite smaller than the regular subarray, so you don't really drive huge bit lines inside it, and the additional power consumption shouldn't be as large as regular subarrays anyway. So that's one thing. Another thing is TFAW is, so when you look at the refresh operation, it already violates all the restrictions that TFAW introduces, and that's because TFAW takes into account the power consumption of the I/O circuitry as well, not only the row activation. Like the name says for activation window, but it actually assumes that when you activate a row, you need to read some data or write some data, and it accounts for the power consumption of those as well. So the limitation is put based on that assumption. But if you actually activate like multiple rows, and the additional rows do not perform, do not use the like global I/O, then the power consumption is smaller. So so we do not know the details because the DRAM circuitry models are not really informative about those. But my gut feeling is that it's not really a major issue. It's not a major limitation. And we actually did some tests. Maybe Ismail will talk about it later. For processing using DRAM operations, when you activate multiple rows, how the power consumption changes. And we do not observe a quite significant change, actually. After activating one row, you already consume a lot of power, and then the increase on additional rows is quite marginal. I think, yeah, that's my answer to that question. A lot of speculation, but I think it's an educated guess.
No, I mean, it makes sense. I think people have shown that there's a lot of slack in TFAW for the reasons you suggest. I'm not sure if TFAW specification is that clear in terms of what it includes. Is it?
It's not clear, but when you do the simple math, it's quite clear that the regular refresh operation greatly violates TFAW.
Yeah. Okay.
Okay. Any other questions? Okay. So this was Kronos, and then I'll get back. Now it's time for your previous question about using refresh-based mechanisms and throttling together. So here in this work, we focus on DRAM chips availability in existence of really high RowHammer vulnerabilities. So this is a mechanism called RowHammer that throttles suspect threads in hardware. So RowHammer names comes from the analogy with the breakwater. So in ocean fronts, for example, you have this structure called breakwater that breaks the waves to reach to the marine, so that in the marine, you don't have like the water really wavy, and it doesn't hurt the infrastructure over there. And you need a lightweight maintenance inside the marine when you have breakwater. I'm talking about the civil engineering concepts here, right? And it's analogous to RowHammer. Basically, we break the RowHammer so that when it reaches to memory controller and RowHammer detection or mitigation mechanisms, it requires a relatively lightweight maintenance and mitigation. So that's the key idea. So we detect and slow down the memory accesses of the threads that trigger many RowHammer preventive actions. So here we assume that there's a RowHammer preventive action is performed by the memory controller or inside the DRAM chip, and there's a RowHammer defense mechanism already exists there, probably a refresh-based mechanism, because many of those mechanisms are refresh-based. And we observe these RowHammer preventive actions from this memory channel, and we trace back which thread triggered them. And then we identify a suspect thread based on that as the attacker. And then we slow down the memory accesses of this attacker so that it doesn't consume much memory bandwidth. It doesn't access DRAM quite significantly. And then it reduces the number of hammers that it performs. So when we evaluated the performance overhead of this, of course, and under attack, it significantly improves system performance and reduces the energy consumption quite significantly. And when there's no RowHammer attack, it doesn't affect the system. It just keeps observing the memory access patterns and doesn't take a lot of actions. And this was also published in Micro 2024 last year in fall. And the implementation is also on GitHub, and you can easily use it on RAM later. Okay, so this was the thing that I was referring to answer your question. So maybe I can get to your other questions as well.
Okay, so you went through it relatively fast, but this works well with PRAC as well?
Yes. So to make it compatible with PRAC, what we do is that in PRAC, everything is inside the DRAM chip. So we cannot observe many of the events inside the DRAM chip because this is a mechanism that is in the processor, in the memory controller, in caches, and etc. What we can observe is that the back-off signals coming from the DRAM chip to the memory controller, and we identify like which thread it's sort of a prediction of like which thread is causing many of these back-off signals, and based on that we throttle that.
Mm-hmm.
So it can work with PRAC.
Mm-hmm. And if it's implemented with PRAC, the performance impact is still low?
Well, yes. The under attack impact is also quite low actually, because PRAC's major performance overhead comes from the increased latency that I talked about in the previous work. But the refreshes do not actually hurt performance quite significantly until you go to like really low RowHammer thresholds. Mm-hmm. And yeah, so the headroom for improvement is not really large over there as well, unless you go to really low thresholds. So in both under attack and no attack, for like current systems, it doesn't have major performance impact.
Mm-hmm. Okay. Any other questions?
Okay. So, okay. I'll just quickly talk about very high level about my future research, what I want to do, and I'll conclude my talk. So the one front that I want to push research is hardware software co-design for sustainable robustness. I guess I don't need to motivate hardware software co-design to this audience anyway. It basically in software you have like a lot of insights into software semantics, and hardware your your measurements are much more accurate and your responses are much more prompt. Everything is much faster and much lower cost. And when you do this co-design, you get great benefits, and it has been leveraged by a lot of works for performance, energy, and other concerns. And I believe that there is more to do for security as well. So this co-design can make security lower cost. And here's an example. So hardware level sensors and counters can quickly and accurately collect a lot of data on application behavior and react to those. So there are some examples in the literature. And when we look at software level malware detection mechanisms, they have a better big picture. So they know like which programs spawn those malicious threads, which users are using them, and they can have more constructive reactions. They can flag some functions, or they can inform programmers, and they can do a higher level countermeasure as well. So our key insight here is that system level attacks often try to attack many times, and the idea is to provide software level malware detection with lots of statistics and information from hardware level mechanisms so that they can make more educated information. So this is a very high level research direction that I want to define. Another one is data-centric robustness. So data-centric computation, we will have a huge workshop on that as well. I don't need to motivate it as well, but it's just like, it's known. I'm just iterating that the memory accesses, off-chip data movement are major consumers of the energy in our systems, and they are used for better performance per joule per area, and processing memory and processing storage are two promising computation paradigms, but the security aspects of those and how they can be leveraged to provide better security are not really well studied yet. When we look at the best practices of security, they're designed in a processor-centric mindset. But when we look at what operations they do, those operations can be done in memory, in storage as well. And in the academia, there are like a few papers popping up recently on that direction as well. So I still think that processing, memory, and storage have a lot to offer. So I'd like to look into that as well. And
I have a question.
Yes.
So what does being data-centric provide here in terms of security? Is there a benefit you get?
So, for example, if you take like Intel SGX and the encryption and the isolation that it provides, so you need to move data to encrypt to the processor. You need to run your encryption algorithm and then put the data back. So you already suffer from data movement without this, and it exacerbates it. And if you move this operation to storage or memory, and I'm not talking about cutting edge even at this moment, because it's like there are already works that exploit it. You can reduce these overheads and you can improve the energy efficiency of your system. So I'm talking about.
I buy that. So you basically improve energy efficiency and performance. But what about security? Is there any benefit you would get by keeping the data in memory?
I guess to begin with, you also like security is about like how many components in your system you can put trust on, right? Mm-hmm. So if you want to be like super secure and you want to minimize the amount of components that you want to trust, you can get rid of the off-chip data link, for example, mm-hmm. by doing that.
Yeah, you don't need to trust it basically anymore.
Yes.
Yeah. Yeah, I agree. In general, it's best to not move data.
Yeah.
Because moving data exposes it to potential other observers, right?
That's true, yes. Okay. So these are just like some recent works and cipher matches. I guess people are familiar with that here. So we had a Sapphire Live seminar on that as well. Okay, so there are a lot of works showing up, but it's basically a growing field of research, and I think there are more things to do here. And there's also the other aspect, security of data-centric computation. So basically, time-inside and covered channel attacks are easier when you're near or in memory. You have less noise in your system. You have no cache or simpler caches, and you have finer-grained control on everything. And you can have larger channel bandwidth with your side and covered channel attacks. And Nisa will talk about a recent paper that was published last month in DSN that is talking about this. So I think like these are really promising frontiers of this field of research, and there are more things to do here. So I'm not going to cover this slide. I'm just going to skip it. And this is the other research field that I want to do more research on. So better understand of failure mechanisms. So a generic question is, what is the worst case for a given system? And our failure mechanisms depend on many conditions and can be observed somewhat probabilistically. As I talked about the RowHammer characterization before, the temperature sensitivity was quite complex, for example. And post-manufacturing testing cannot practically cover all these conditions because it's expensive, it takes time, and we need better methodologies and infrastructures for having systems more secure, reliable, and safe. And testing is costly because the chip cannot be used while it's in testing, and you need to buy chips to test them. So unless you're the manufacturer, you need to invest a lot on buying a lot of chips. So this is sort of a long-term goal that I have. I think we need to revolutionize the testing and data collection with providing online testing methodologies that include some reverse engineering tools, some testing routines and stuff like that. And some attestation needs to be here as well, so that we can crowdsource the data collection and we can scale up our sample sets. Instead of testing like hundreds of chips, we can test millions of chips if we can collect a lot of data from a lot of people and a lot of servers. But for that, there are really like huge challenges of implementing these testing methodologies and reverse engineering tools. And there are some good examples for offline testing tools in the field. And we need more plug and play online runtime testing tools to achieve that. So with that, I want to conclude with my first claim, the goal: systems should scale robustly and sustainably as chips get denser and many users share systems. And to do that, we need more research, of course, in the fields that I just talked about. And that's the end of my talk. Thank you very much. I can get more questions.
Okay, thanks for the nice talk, Giray. I have a question on testing. Sure. You mentioned that test a chip in runtime when it's idle. Why doesn't the chip itself do it? So I'm assuming you're talking about a DRAM chip, but it could be any chip. Sure, but let's talk about DRAM. If the chip has mechanisms to automatically test itself and find things, would this problem be solved? Like, is there such capability?
For DRAM chips, I guess, yes. It can be mostly solved. So we still need to collect this information. And I mean, in practice, it's also quite hard to convince manufacturers to implement this runtime testing methodology inside their DRAM chip and also expose that data outside so that they can be used for research. So for that reason, I'm not seeing it very promising, but yes, like in hypothetical scenario where they're okay with that, I think it's better to perform inside the chip so that we can do it more efficiently. We can leverage parallelism inside the chip. We can hide all the latencies, and we can reduce the energy consumption of testing even. So yes. Does it answer your question?
Well, somewhat. I mean, there's work to be done in this area, so it's a more of a research direction.
Yes.
But who does the testing becomes important, right? I think if the DRAM chip is more self-managing, let's say, which someone here may be talking about later, maybe you can do the testing better.
Yeah. Yeah, that's for sure, yes. I agree that if you can do that inside the chip, if the chip tests itself, yes, it's more efficient. It's a better solution for sure.
Yeah.
But we need to get that testing data out to use in research and do like more statistical analysis on that, draw some conclusions.
I guess, yeah, depends on the type of conclusions that you want to draw, right? Like internally, you can do a lot also if you can keep the data inside the chip. But then if you don't share it, then you cannot do the crowdsourcing, maybe.
Yes. Also, so here still the high-level goal is to advance the science, right? So we want to publish this. And in a production environment, yes, maybe it's much more efficient to do the tests inside the DRAM chip, fix errors, and move on with the life. But yeah, it doesn't really advance the open literature.
Well, that's a different question, though, right?
Yeah.
Whether that data is available and how that data is used. So if you want to improve the efficiency or robustness internally, you don't need to publish that data necessarily outside, right?
Yes.
You can build mechanisms inside the chip. Like, for example, change the refresh rates of different rows.
Like Creeper does, yes.
Yeah.
But okay, so it's to me it seems similar to the kind of study that some cloud manufacturers are publishing nowadays. Like they collect a lot of logs over some extended amount of time, and they analyze like, okay, what is the reliability of DDR5 DRAM chips versus DDR4 DRAM chips, and then they draw some conclusions based on that. But when you actually want to understand why those bit flips are happening, you don't really have like much details, because so that data is collected inside the server, and they did some countermeasures to keep their servers alive, yes, but it's I guess it just like works for that company or that provider, but it doesn't really help us, the like whole community, to understand why those bit flips are happening and how can we solve them.
Yeah, I mean, I think we're talking about different things. I'm talking about mechanisms. You're talking about the data, availability, and understanding. I think both needs to happen for sure. But how do we enable this online testing efficiently is a good question.
I agree, yes.
No.
Yeah, I don't deny it.
Okay. Oh, you have a question?
So you're talking about online testing methodologies, right? And I suppose this testing is to make the system more robust or even more performant throughout the runtime, right? Okay. So previously you said that you need to test a big amount of cells in a DRAM chip in order to understand what is going on, to see the characteristics of the entire DRAM chip. But this...
I couldn't hear that part.
You need to test all cells in order to have an idea of how the DRAM chip behaves, right? But this would play a role when it comes to the aging of the chip, if this happens online. So if we don't have a separate chip in order to test, could there be a way to limit the number of testing that is needed? Because online, in order to enable this online testing, we need to test less cells.
So the testing itself also causes aging in chips.
Yes,
And
exactly.
That's a problem,
and
yes.
Yes, is there a way to limit the testing in order to reduce this sort of aging and the time needed as well, and the energy spent on the testing side rather than actually using the DRAM chip?
Yeah, I think that's a good research question as well. It's basically a knob, like how frequently you will repeat the test, and you can play with that and see like, yeah, what is the sweet spot. But I guess I have no idea at the moment about that. It's something to discover. Okay, any other questions? I'm sorry this took much longer than what it's supposed to. So I guess it's already time for coffee break, right? And then we can have your talk after the coffee break. Yes. Yeah. Okay. Then yeah, see you in like. Oh, sorry. There's a what?
This is again on online testing. Thanks for the great talk. Is it really necessary for this online testing to be necessarily only inside the DRAM chip? Because you may want to issue demand requests from the memory controller to certain areas of the DRAM that need to be sent. Maybe there's also a need for the memory controller to signal parts of the DRAM that, okay, you could go into, let's say, profiling yourself right now, updating your internal counters. We can use later. Is there a case to be made for that? Maybe not specifically for robustness, but for maybe other problems, not necessarily relevant to robustness. What are your thoughts on this?
I think that's a good point, and I think we should discuss it with SMD, right? Self-managing DRAM, no? Okay, so there's going to be another talk more focused on that, I guess. Yeah. Maybe we can, you can reiterate.
Sure.
The time. Yeah.
Thanks.
Okay, then let's go to coffee break and come back by like 10 a.m. 7 minutes, no? Too early? 10:05? 10:15? Okay. Okay. So we will have 22 minutes of break.
Something there.
So I already downloaded your thing.
I already opened it. I'll need to do. Should I share the screen?
Yes. Is this fine? No, this is mine.
Is this the correct way?
Maybe.
My head is too big. Ah. Oh.
I think it's okay.
Okay. Hello. Hello. It's fine.
Can you guys hear from back? Well, actually, you have the indicators over there. Can you try?
Hello. Yes.
Okay. I think everything works well. So welcome everyone. So we carried some of the water and orange juice over there. So if you need some, please help yourselves. So we'll continue with second talk from Ismail. Ismail Emir Yüksel is a second-year PhD student in Safari Research Group at ETH Zurich. And he works with Professor Onur Mutlu, obviously. And his current broader research interests are in computer architecture, processing in memory, hardware security, and focus on understanding, enhancing, and exploiting fundamental computational capabilities of modern DRAM architectures. And it's impressive that he has at least one paper in each of these already in the second year of PhD. So, yeah, today he will talk about PodHammer, experimental analysis of read disturbance effects of processing using DRAM in real DRAM chips. Go ahead.
Thanks a lot for the great introduction, Giray. Hello, everyone. I'm Ismail. Today, I'll be covering our recent work published in ISCA 2025 called PodHammer, experimental analysis of read disturbance effects of processing using DRAM in real DRAM chips. Let's start with an executive summary. Processing using DRAM is a promising paradigm to elevate data movement bottlenecks between main memory and processing units. Prior work showed that DRAM can perform many processing using DRAM operations by activating multiple DRAM rows in quick succession or simultaneously, as broadly referred as multiple row activation. Unfortunately, modern DRAM is subject to read disturbance, and prominent example for this is RowHammer, as Giray talked before. And repeatedly activating even a single DRAM row induces bit flips in other unaccessed rows. And the problem is no prior work studied the read disturbance effect of activating multiple rows at once, multiple row activation. And our goal is to understand and analyze how this multiple row activation has an effect on read disturbance vulnerability in the real DRAM chips. To this end, we conduct an experimental study on 316 off-the-shelf DDR4 chips from 4 major manufacturers to study this effect of multiple row activation, which we call PodHammer. We observed that PodHammer significantly exacerbates DRAM read disturbance, causing up to almost 160 times reduction in minimum hammer count to induce first bit flip. And we observed that PodHammer bypasses in DRAM RowHammer mitigation employed in DDR4 and induces more than 10,000 times more bit flips than RowHammer. And we adapt the industry's latest solution to RowHammer per row activation counting to account for PodHammer. And we observed that the adapted solution incurs an average system performance overhead of almost 50%. So here's the outline of my talk, and I'll start with a brief background. DRAM is used main memory as DRAM is used as the main memory in many computing systems, and inside the DRAM module we have several DRAM chips. Within a DRAM chip we have many DRAM banks, and inside the DRAM banks we have many subarrays.
Within each subarray, we have two-dimensional array of DRAM cells and a row of DRAM cells called DRAM row, and they are connected through word line. And the column of DRAM cells are connected to sense amplifiers via bit lines. And there are three major DRAM operations to access data from DRAM. First is activate, which fetches the row's content into sense amplifiers, and then memory controller can issue column accesses such as read from the row or write to row. And then in order to access another data in another row in the same bank, memory controller needs to issue a precharge command to which prepare the bank for a new activate. As we see until now, DRAM is just used to store data. This is because today's computing systems are processor-centric. All data is processed in processor at a great system cost. In order to perform a computation, we need to move the data between main memory and computing units. And prior work showed that more than 60% of the total energy is spent on data movement. And processing using DRAM is a promising paradigm to elevate such data movement bottlenecks. It uses analog operational principles of DRAM cells to perform computation. And multiple row activation is a key technique to realize many-pod operations, such as AND and OR. And we categorize different types of multiple row activation into two. First, consecutive multiple row activation, short for COMRA. And second, simultaneous multiple row activation, which we call SIMRA. Let's look at the consecutive multiple row activation first. The key idea, the key observation is violating the timing of precharge command greatly in off-the-shelf DRAM chips activates two rows consecutively. So here we have a DRAM subarray, which consists of many rows, including source, SRC, and destination, DSD. So if we obey the timing parameters in this command sequence, activate source, precharge, then activate destination, we will activate only a single DRAM row at a time, either source and then destination. However, we observe, and prior works also observe that if we greatly violate these timings, we can activate two rows consecutively. And we use this consecutive multiple row activation to perform a key operation in DRAM, a row copy operation, which is also called row clone. So here again, we have the same example, source and destinations rows. And as we first activate source, which will assert the source word line. And then we wait for TRAS, which is 36 nanoseconds, and it will fetch the source content into sense amplifiers, and it will restore the charge in the source row. And then we issue back-to-back by violated timings precharge and activate to destination. As a result of this, we activate destination rows. Since we violate the precharge command, we keep the bit lines at source voltage and also sense amplifier at source voltage, and also we keep the sense amplifier enabled. And if we wait again long enough by obeying the timing parameters, we observe that from sense amplifier to destination, source content is copied. And another multiple row activation technique is simultaneous multiple row activation. The key observation is activating two rows in quick succession in off-the-shelf DRAM chips simultaneously activate multiple rows in a subarray. Here we have one subarray, subarray X, which consists of many rows, including row A and row B. Here we have our usual command sequence, activate row A, precharge, and activate row B. Again, if we obey the timing parameters, we will only activate a single row at a time. However, if we greatly violate these timings, we will activate many rows in the subarray at once. And this is because back-to-back activation commands with violated timings assert many more signals in the hierarchical row decoder circuitry in the DRAM. And you can check for hypotheses and how this row decoder circuitry works from our previous work, which I will talk about in 2 weeks in the third section of our SaLWo. And one example of SIMRA is realizing in DRAM majority of 3. Here we have a DRAM subarray again, which has A, B, and B rows, 3 rows. And assume when we issue our command sequence with activate, precharge, and activate violate timings, we activate 3 rows simultaneously. When we issue this, it will assert 3 rows word lines at the same time. As a result of this, 3 rows will perturb bit lines simultaneously. And due to the charge sharing principles, sense amplifiers will sample the output of majority. In this case, is B. But unfortunately, in DRAM, we have a phenomenon called read disturbance. Even activating a single DRAM row disturbs the data integrity of other unaccessed rows. A prominent example for that is RowHammer, where we keep repeatedly accessing a same DRAM row, causes bit flips in nearby rows. We call aggressor row as the row that we hammer, and we call victim row as the rows that experience bit flips. So this phenomenon brings us to our paper's problem and goal. No prior work investigates the read disturbance effect of multiple row activation, even a single DRAM row activation causing bit flips. And our goal is to understand how this multiple row activation affect the read disturbance vulnerability in real DRAM chips. To experiment with real DRAM chips, we use a real DRAM chip testing infrastructure. It is built upon DRAM Bender, which enables us to have fine-grained control over DRAM commands, timings, temperature, and voltage. And to test a lot of DRAM and understand how memory works and understand how the other failures happens, we have a laboratory for understanding memory. And in this study, we test a total of 316 DDR4 chips from 4 major manufacturers, and we cover different die regions and chip densities. You can think of them as different DRAM architectures. And now let's move on to our first analysis, read disturbance effect of consecutive multiple row activation. Recall that COMRA, for short, activates 2 rows consecutively. So to hammer using this COMRA access pattern, we use 2 versions of hammering. First is double-sided, where we sandwich a victim row. Here, what we do is that we copy one row to another to sandwich a victim row. And the other one is single-sided, where we keep hammering one row, inducing bit flips in nearby rows. But here in this access pattern, since we use 2 rows as aggressor, what we do is that we copy from one row to another where they're very far away from each other. In a sense that we do a single-sided in both cases for source and destination. So to characterize the read disturbance effects of COMRA, we carefully sweep row addresses, source and destination, the timing parameters between precharge to activate command, and the data pattern in several different temperature levels. And to evaluate the read disturbance vulnerability of DRAM chips, we use a widely adopted metric called HC first, which is the minimum hammer count required in this first bit flip, and lower is worse. Here we have a scenario of double-sided COMRA pattern where we sandwich a victim row, and one hammer consists of one COMRA operation, basically activate source, obey the timing parameter, issue per charge, violate the timing, activate destination. And between each hammering, we obey the timing parameters to safely issue per charge command. And then after enough hammering, we record the bit flips in the victim row. So let's look at our first result where we compare against double-sided COMRA, consecutive multiple row activation, versus double-sided RowHammer. On the x-axis, we have manufacturers, 4 manufacturers that we test. And the y-axis, we have the lowest HC first observed from the manufacturer. And the hue, the colors of the bar will show the technique, either RowHammer or COMRA. And we observe that for SK Hynix, double-sided COMRA decreases the lowest HC first by almost 14 times compared to double-sided RowHammer. And this trend, this reduction trend, is consistent across all tested manufacturers. And for another analysis, we investigate each victim rows individually. Here in the y-axis, we have the HC first change. HC first change, where when we do a double-sided COMRA compared to double-sided RowHammer, and the y-axis we have the DRAM row sorted by reducing HC first changes, and each line will represent the manufacturer. To understand this plot better, let me walk through what that means, the axes. So here from P1 to P100 represents 99% of tested victim rows. Similarly, P50 to P100 represents 50% of tested victim rows. And for the y-axis, negative HC first change means COMRA reduces HC first compared to double-sided RowHammer. And for example, HC first change of -50 means, for example, for a victim row, RowHammer HC first is 100, while COMRA's HC first is 50. I hope it's clear. So we observe that more than 99% of tested victim rows experience lower HC first. We conclude that double-sided COMRA decreases HC first for a large fraction of rows compared to double-sided RowHammer. And based on these two experiments, lowest HC first and also testing each victim rows individually, we derive a key takeaway. COMRA exacerbates DRAM's vulnerability to read disturbance in all 4 major manufacturers. And that was the COMRA. Now let's move on to our second analysis, read disturbance effect of SIMRA, simultaneous multiple row activation. Recall that SIMRA activates multiple DRAM rows in a subarray simultaneously. And to characterize the read disturbance vulnerability that's caused by SIMRA, we careful sweep, again, the same things, row addresses, timing parameters, data pattern, and temperature. So let's take a look at our first result here, where we compare double-sided SIMRA versus RowHammer. And the x-axis, we have the simultaneous activated rows, and the y-axis, we have the lowest HC first. Again, minimum hammer count induced first bit flip. And we observe that from RowHammer compared to RowHammer, when we activate 4 rows to sandwich a victim row, the lowest HC first decreases by 159 times compared to double-sided RowHammer. And this trend is consistent across all tested number of simultaneously activated rows. And again, when we investigate individually each victim rows, we observe that again, more than 99% of tested victim rows experience lower HC first, and at least more than 25% of tested victim rows experience more than 99% of HC first reduction. Basically, as an example, while RowHammer induces a first bit flip by 100 hammer count, while SIMRA induces with 1. So we conclude that double-sided SIMRA significantly decreases HC first for a majority of rows compared to double-sided RowHammer. And again, based on these 2 experiments, we derive a key takeaway that SIMRA drastically exacerbates DRAM's vulnerability to read disturbance. And we also look at, yes, sorry. Yes.
So I have a question.
Yes.
It's obvious that it exacerbates read disturbance vulnerability for the vast majority. But when we look at the HC first change in the leftmost side of that plot, like the first percentile, I see values like above 0.
Yes.
And how do you explain it?
So we are checking each victim row, and the cells probably differs. This is because we believe that we hypothesize that the underlying phenomena for SIMRA is different than RowHammer. So basically, the weakest cell for RowHammer is not necessarily the weakest cell for SIMRA. So some rows, some victim rows, are not that weak against SIMRA, while weak against RowHammer. That's what we observed actually. So, but most of them are, let's say, more, let's say, vulnerable to SIMRA. But what we observe is that the cells are different actually. The HC, the first bit flip that we observe in a row.
But it seems like now you have like a similar activation. So let's say you observe a bit flip at n hammer count, like n hammer count, and when you do SIMRA, you still activate those rows for n times, but you don't observe bit flips. Isn't the case?
For the positive HC first change, you mean?
Yes.
Yes. So for positive HC first change means that RowHammer, for example, 100 means RowHammer HC first is 10, SIMRA HC first is 20. So you need to do 20 times of SIMRA for that row.
Yeah, but like in the circuit level, you still activate those assert those word lines, right?
Yes, but what I'm trying to say is that the underlying phenomena is different. So you activate them at the same time. But in RowHammer, you interleave, right? You first activate one regressor row, you precharge, you activate another regressor row. But in SiMRA, you activate both of them at the same time. You
actually simultaneously assert both word lines, and then some effects cancel each other.
Could be. And we believe that I'll show in the impact of a data pattern, there are some significant differences between RowHammer. And I believe the most important one is the bit flip direction.
Okay, thanks.
Yeah. Thanks. Harsh has a question.
So one question about the evaluation here. Does this include the rows, the cells that are successful in computing SIMRA and COMRA? Or do they include all the cells in the row that you have and you check for the first bit flip in all the cells?
So what you mean is that you test the rows, the cells that are capable of doing SiMRA? Yes.
So when
it's very similar to what we have done before in other works, that we just activate, precharge, activate, and then issue write to see whether those rows are activated or not. And then we compare against if this cell also activated to double check basically, because there could be some issues, as you said. A good question.
So if SiMRA is reducing the ACC first this much, so does this mean that if you have a random number generator that exploits multiple row activations at the same time, right? Mm-hmm. So would generating random numbers in this way exacerbates the bit flip so much that DRAM would be very much unreliable? So my question is that if this observation, does this negates the possibility of having multiple simultaneous row activation as a viable means to generate random numbers, true random numbers?
So you're saying that this effect could interfere with generating random numbers?
No. So we can still generate the random numbers by doing multiple simultaneous row activations, but this observation says that your data integrity would be very much less.
Yes.
So that means either we generate random numbers using, let's say, quack-like mechanism, mm-hmm. or we keep the data integrated in the DRAM. So both of these cannot be done at the same time.
You can have both.
Okay.
But so you need to take some countermeasures, right? So I'll discuss one of the mitigations that we adapted, but in the paper, we discuss a lot of them. So for example, you can cluster where you activate the rows, right? And you can put some isolation rows so that they won't affect other rows. Basically, you need to move. You will have a, let's say, dedicated area for this. And then this could also bring some new things. So for example, you need to copy mm-hmm. that will increase the
so basically, you're taking measurements to contain the effect rather than, but if we keep the substrate as is, then that
won't be good. But the issue is that, so we're doing it in real DRAM chips with the real DRAM chip constraints, which are not designed for this purpose, right? So actually, in order to do this, let's say, statements, we need to have a, let's say, PUD enabled chip so that we can test whether this is present or not. But we believe that the underlying phenomenon is there, the real DRAM chip is there. So this is like a more like a be careful when you're going to do that. You need to take this into account.
Okay.
But for sure, that's one of the issues. Yeah, you cannot just blindly do things. Mm-hmm. You need to take this read disturbance phenomenon into account.
Makes sense.
Yeah, it's a good question. Thanks.
I have a follow-up.
Yes.
So I know that you tried a lot of different combinations. Did you actually did you actually do something like what Rahul said, like let's say generate random numbers with using quark TRNG on commodity chips? and then see like what kind of bit flips we can observe in nearby cells. Did you look at that?
So Quark basically actually activating 4 rows at once, right? So here, for example, here is the 4 rows. So it's like what your question is, it's a bit error rate.
I guess so, yeah.
Like, yeah. For example, I want to have this much of random number generation, so I need to do this Quark operation for this many times. So the issue is we did the bit error rate with normal RowHammer, where you do like 100,000 hammer count and you check the bit error rates, right? So we did this. It's the number is a bit funny. It's like 99% of the rows that like when you sandwich it. So because as you can see here, like the lowest HC first here is 26, right? So we didn't know that when we tested. Like it was just, yeah, we have RowHammer. Let's have a like the same baseline 100,000 of activation for RowHammer, 100,000 of activation for SiMRA. We compare, but yeah, it also introduces a lot of bit flips that more than like significantly more than RowHammer in that sense as well. We will add this in the extended version of the paper.
Okay, so
with less hammer counts. Yeah.
So you showed that 26 activations can induce bit flip, right?
Yes.
So ideally, we want to keep it lower than 26 activations. And let's say we want to generate random numbers using Quark TRNG. What kind of random number throughput we would get by like 26 activations?
So the good thing about no, this 26 is the lowest that we observe. Yes, here is all victim rows and we compare against minimum. But you can see like, again, more than 99% of reduction. So the good thing is multiple row activation is that now you have your random data in your sense amplifier, which is the row granularity, 8 kilobyte of data. I mean, the entropy could change depending on the row that you use. But I don't know the number, like on top of my head, that how many, let's say, activations do you need. But even in a single activation, even in a single Quark, you can get many, not many, but it's at least 1,000 bit, something like that. But I don't recall the, let's say, the number, because we were also testing with 2, 4, 8, 16, and 32.
So would it be correct to assume that in common case, you wouldn't actually do the Quark operation many times to induce, to the extent that it will induce bit flips?
For just Quark, maybe, but maybe your random number, your application needs a lot of random number, who knows?
Sure, yes.
But so the SiMRA is not just for Quark TRNG, not just for generating random numbers. For example, SIM-DRAM, MIM-DRAM, or even other works that uses processing using DRAM to perform, let's say, arithmetic operations, right? And for example, multiplication is over there is exponential. In the paper, we say that we see that like in 8-bit of addition, as far as I remember, from SIM-DRAM paper, you need more than 600 SiMRA and COMRA operation, AP and AAP. So it's a very common case, and 26 is not that much. So if you just freely use every row, you're a bit in trouble. Then if you want to fully leverage what you have with processing using DRAM.
I guess there are more questions coming to that, but I assume that you will talk about those later on, right?
What?
The SIMD operations, no?
No. 2 weeks.
2 weeks from now, okay. Maybe we can come back to RowHammer discussion at that time.
Yeah, anytime. Yes. Any more questions? Those were good. These are purely RowHammer. I have RowPress results in the backup slides. I can show them later. But yeah, it's it's also worse than RowPress as well. Like when you not hammer with Simra but press with Simra or Comra. And also we observe that pressing is more actually more effective than hammering. Yes.
What happens if you do RowPress? So you go down to what?
2.
2 activations, basically. 2 multiple row activations. Maybe it's good to show that.
Yeah, let me find that one. It's not that much. So 9 TRFI, it's 2.
That's TRFI.
Yeah. So
9 TRFI.
9 TRFI. But even in TRFI, you can go to 2.
Okay.
Even in 4 TRAS.
That's
like
10.
10.
At least at the lower bound is 10.
Yeah.
Okay.
So I didn't go for that, like, I don't know, like 1 millisecond or something.
Mm-hmm.
But probably we will go to 1 also. If you go to 1 millisecond. So basically, for example, if you do QUAC, and then you say that, yeah, I don't need to pre-try, I'll just read the whole row.
Mm-hmm.
Basically, you will probably maybe induce bit flips.
Yeah.
Less than 26 activations.
Okay.
Yeah. Thanks. Good question. Any more questions? No? Where was I? Yeah, here. So one thing maybe I should note is that, as you can see here, it's up to 16 rows. Interestingly, I don't know why, normally we can activate up to 32 rows at once. However, I don't know why, but when we do 32 row activation, we cannot sandwich a victim row. That's another interesting point, that like it's just row decoder circuitry activates rows in a different fashion, that it won't sandwich a row. So we don't have so here, since we are working with real DRAM chips, we don't have a control over which rows are we going to open simultaneously. So it's just basically based on just the row decoder circuitry that we have. Luckily, but maybe unluckily, we found that we can sandwich up to 16 rows, but when you go to 32, you cannot do that. But it's maybe because of the rows, because of the models that we test, because row decoder circuitry changes for, like, it's different for each a different model or DRAM architecture. Yeah, it was a bit funny when we were testing it. Okay, so impact of data pattern. Here we have 2-row activation, basically 2-row activation Simra, where you just have 2 rows, a sandwich a victim. And the x-axis shows the aggressor data pattern, and victim has the negated data pattern. For example, aggressor rows if aggressor rows are initialized with all 1s, victim rows are initialized with all 0s. And the y-axis shows the HC first distribution. So here, I would like to highlight the difference between all 0s and all 1s. Basically, all 0s in aggressor data pattern means that your victim are initialized with all 1s. So initializing victim rows with all 0s increases the average HC first by 15.8x. So, and that shows that the dominant bit flip direction for Simra is 1 to 0. As you can see here is that, like, it goes more than 1 million activation if you initialize your victim rows with 0 and initialize your aggressor row with 1. On the other hand, for RowHammer, the dominant bit flip direction is 0 to 1, which prior work have shown, and also we also observe in this paper. So, and this is consistent across all tested number of activations. So this shows that Simra is significantly affected by data pattern, and directionality of Simra and RowHammer bit flips are opposite. So this suggests that, yes.
So when you talk about 1s and 0s here, are they logical 1s and 0s, or are you?
No, we reverse engineered that through an anti-cells. These
Okay.
are physical. basically, for both RowHammer and.
So from high to low, it flips.
Yes.
Okay, thanks.
Yes. So it's, I guess the dominant bit flip direction is a bit similar to RowPress, maybe, but Hasan will talk about that more. But yeah, it's even we do just hammering, not just pressing. The dominant bit flip direction is different. And we hypothesize that this is one of the reasons that we believe the underlying phenomena is different than RowHammer. Yeah, it's a bit different. The average of HC first is, yeah, around 100K. And yeah, so we saw that this COMRA and SaLWo multiple row activation has a severe effect on read in DRAM, right? So it exacerbates read disturbance vulnerability a lot. So what should we do to mitigate this effect? So we took a two-step approach. We first analyzed the effectiveness of existing in DRAM RowHammer mitigation employed in DDR4 against POTHammer. And second, we try to adapt RowHammer mitigations to account for POTHammer and see their performance overheads. So let's see the first one. So in DDR4, DRAM vendors equip their DRAM chip with a proprietary mitigation mechanism known as target row refresh, TRR. And the key idea is that TRR refreshes nearby rows upon detecting an aggressor row. Here, assume we have a memory controller and TRR-equipped DRAM chip. Assume that TRR detected row 2 as an aggressor. Upon a refresh, TRR-induced refresh, TRR will refreshes the nearby rows, basically row 1 and row 3. Prior work showed that this is not enough to mitigate RowHammer bit flips, but we would like to understand how, like compared to RowHammer, how the effect is severe, like for COMRA and SaLWo. So we test the real DRAM chips again from one module. We reverse engineer the TRR mechanism over there using prior work UTRR. And for RowHammer, here we have without TRR results. In the x-axis, you have number of aggressors. You can think of different access patterns to trick TRR mechanism. And the y-axis, we have the total bit flips. And the worst case tested access pattern induces more than 10,000 bit flips. And with TRR, it's reduced drastically. The worst case tested access pattern is different, and it induces less than 60 bit flips. For COMRA, it's very similar to RowHammer. It induces more than 10,000 bit flips without TRR, but in the presence of TRR, the bit flips are reduced greatly. It's still higher than RowHammer. It induces up to 60 bit flips, and on average, it induces 1.1 times more bit flips than RowHammer in the presence of TRR. However, for SaLWo, it's a bit different. Without TRR, you have around 240,000 bit flips. But with TRR, it's still there. We observe the worst case tested access pattern induces 180,000 bit flips. And on average, it induces more than 10,000 times more bit flips than RowHammer. And we believe that this is because, so TRR registers the activations, activation commands, and the row addresses that is sent with activation. But in SaLWo, when we issue just 2 activation, we activate more than 2 rows, right? Like 4, 8, 16, and 32. As you can see here, for example, 2 is too low compared to 4, 8, 16, and 32. So this is one thing. Basically, TRR cannot handle internally opened, activated other rows more than 2. And so we see that it's not effective. It's less effective than RowHammer to mitigate multiple activation bit flips. So we try to adapt RowHammer mitigations to account for POTHammer. And we chose the popular one, PRAC. So we took, again, 2 approaches here, a naive approach where we just reduce RowHammer threshold to SaLWo's lowest observed threshold. So that means that if your RowHammer threshold is 4,000 and SaLWo's threshold is 20, now you reduce your threshold to 20 to account for POTHammer bit flips. And the other approach is increase PRAC counters based on the vulnerability caused by the operation RowHammer, COMRA, and SaLWo. For example, upon an activation, you increase the counter by 1. However, if you issue a SIMR operation, you increase the counter by 100 or 200. So to test, to evaluate the performance overheads, we use a cycle level DRAM simulator, Remulator 2. And here's the system configuration. And we test 60 5-core multi-program workload mixes. Each mix is composed of 4 workloads from 5 major benchmark suites and 1 synthetic workload that periodically performs back-to-back processing using DRAM operations. Basically, in our system, we have 4 cores that runs benign workloads, and we have 1 more core, PIMP core, that issues just processing using DRAM operation. And here are the results. And the x-axis, we have the period of performing back-to-back SIMR and COMR operation. From left to right, you can think that the pod intensity performing this operation increases. For example, 125 means DRAM performs pod operations in every 125 nanoseconds. And the y-axis, we have normalized weighted speedup, normalized no RowHammer mitigation. And here are the results. And we observe that the weighted counting, a bit optimized version of Prague, greatly outperforms the naive version until 2 microseconds. However, Prague weighted counting incurs an average performance overhead of almost 50%. And in the case for 125 nanoseconds, it induces almost 99% of performance overhead. So we believe that we need more solutions to mitigate pod hammer bit flips. Yes.
So I'm not sure if you have this information, but let's say I'm doing some matrix multiplication using SIMDRAM. So where should be my period on the x-axis?
So don't know. So this is the issue is that here that we don't have like cores and PIM units at the same time. They're accessing the same DRAM module, right? So in SIMDRAM's case, you will just dedicate a DRAM module for just SIMDRAM for put operation. So it should be, I don't know, 50 nanoseconds, which should be like TRC, basically. But yeah.
So yeah, every 15 nanoseconds, let's say we do the SIMRA operation. But so how many times would I do that though?
So multiplication, it's too much. If you're gonna go with multiplication, and if you're, because it's bit serial, you need to do that every time. And addition, even addition takes a lot of time when you go higher bit widths. So multiplication is just exponential. It's too much. It's like ON squared compared to ON for addition, for example.
Okay, yeah. Makes sense. So it would definitely induce some bit flips then.
Yes. So you need to be careful of it. Even if you just dedicate the DRAM module for SIMR and COMR operations, you need to definitely need, let's say, intelligent mitigation mechanism.
Okay.
Harsh has a question.
So one question was, you described that with weighted counting, you would update the Prague counters based on the kind of operation that you perform.
Yes.
Let's say by 100 or 200, depending on the kind of operation.
Yes.
But how would you describe this information? Because when you do SIMRA or COMRA, you just perform act-react.
Yes.
What's the stimuli that the Prague counter should take? Do you think about this, or what do you have? What thoughts?
So for this analysis, for just mitigating it, we assume pod-enabled chip. So basically, you can issue SIMRA and COMRA operation. It's not just act. It's not like for the real DRAM chips, but just for future pod-enabled real DRAM chips, like
as commands, basically.
Yeah, basically, just you issue SIMRA with, but you give which rows you're gonna open. Basically, if you can just give similar to activation. We modify the remulator to just give this rows, and then remulator just will activate. Basically, something like that.
Okay, thanks.
Yeah. Any more questions? Yes. A PRAG without Kronos, for example. Yes. Yes.
It has already some performance impact. How does that performance impact? So what fraction of the performance impact is coming from the, let's say, poor PRAG specification in DDR5 versus the reduced HC first?
Okay. I think it's when we look at the, let's say, leftmost, where there's no intensity of put. So this is just, I think, just the PRAG's overhead. But I think here it's just almost 99%. So it's safe to say that maybe 90% of this overhead is coming from just pot operations. Maybe with Kronos we can elevate this 10%, but I'm not sure about when we have this much intensity of pot, probably we will have again more than 90%. This is my gut feeling.
Okay. And you expect other solutions, other existing solutions to have similar overheads? Existing solutions to RowHammer?
Yes, I think so. Because PRAG is supposedly in low thresholds. It works better than others. So even when you do weighted countings, assume that you do SIMRA all the time, basically your threshold is 20. So the other mitigation mechanism, I guess, suffer a lot, I believe more than PRAG in this case. Maybe not for the leftmost part, but the rightmost part again. Maybe more than PRAG.
Okay.
Yeah.
I mean, it makes sense. So in this graph or figure, how do I think about HC first?
So for PRAG naive, the HC first or HC first are different. So sorry, for PRAG naive, HC first is not different. It's just 20. But without any processing using DRAM operations or anything. For PRAG weighted counting, so your threshold is set to 4,000, but each activation increases the counter by 1, while COMRA operation increases by 10, SIMRA operations increases by 200.
Okay.
But all of them are based on the empirical results that we have from real DRAM chips.
Okay.
So you talked about how, for example, 32 row activations do not affect any sandwich row. So there is a limit to which rows are affected when you're doing this sort of simultaneous activation. So one solution would be to not use the affected rows. Would it, first of all?
So once you're saying that I'm gonna activate this rows all the time, so I'm not gonna access the other rows, basically, not use them.
Exactly, we're not going to use the affected rows. As in real DRAM chips, you couldn't even control whether or not where these rows were. So
yes,
it could be one potential solution. And the question is, would the capacity overhead be, what is the number of these sort of affected rows? And how, and could this be a potential solution of not using the rows while the operations happen?
So, for example, if you're using 16 rows, so in the paper we discussed that you can modify the DRAM chips similar to Ambit, that you will have a just complete region in a subarray. For example, over there it was just 3, but you can have here like 16, 32. And assume that the worst case 32, that you will have a great, let's say, reliable majority operations. So for each subarray, it should be at least 32, and you will need to add some isolations after that. I don't know how many rows, but when you check the JEDEC standards, it could be +1 - 1, +2 - 2, and +4 - 4. So up to 4 rows, you can think of that in the JEDEC. So basically 36 rows. You need to just make them offline or just dedicate for just compute region. So every 36 rows for a subarray, which subarrays ranges between 500 rows to 1,000 rows.
Okay, so it could be a potential solution to basically not use these rows and create a buffer, essentially.
Yes.
Okay, cool.
You can do that, but maybe you don't want to sacrifice your storage as well. Maybe you just want to do ad hoc, like directly into computations that, or you want to use multiple rows at the same time to perform operations.
Yes, makes sense.
Yeah. There's one more.
I have a follow-up to that, actually.
Yes.
So for Simra, that makes sense, but for Comra, so to perform SIMD operation, you need to copy, right?
Exactly.
So you need to do that operation with any row anyway in the subarray,
Yes.
no?
Yes.
Okay. Yeah, thanks.
Yeah. So it increases the copy operation if you're not, so if you dedicate a region. So it increases the common operation that you use. It's not severe as Simra, but still much lower than RowHammer, 10 times, more than 10 times the HC first, I guess. Yeah.
I have one more question about the access patterns that you use for the PUD operation.
Yes.
So was it arbitrary to choose back-to-back Simra and Comra? Or was there a specific reason? Could you have done just one of them?
Mm-hmm.
Or could you could you have described a pattern where you do Simra and Comra across all banks, specific to one bank? Mm-hmm. What particular pattern do you use for this particular?
So this is just an analysis of just one access pattern, right? So but the issue is that, so there is no scheduling for using at the same time pod chips, or like units that issue pod operation and units that issue normal like accessing, right? So there is no scheduling policy over there, so we don't know. So here, what we did is this, just, yeah, let's see if what you would like to do is probably you'll just copy and then you probably do some operations, right? So we just try to test it to see what happens. That's why we sweep here the intensity. That's because there is no consensus on how to schedule things, where to use them in which bank, or should we, for example, you may dedicate a bank for PUD operation while accessing other rows for just accessing them, right? For just reading and writing. So that's why we had like issues that how should we like investigate this, like analyze this, because there is no like methodology or benchmark or anything. There are some synthetic benchmarks that we actually use from DRAM's open source code, that we just took some benchmarks over there from Edition, for example. We just check, and that's why we sweep like this. It's just basically the show, the demonstration of what could happen depending on the intensity.
Yeah, I like that you use workloads from the main DRAM artifact, at least.
Yeah.
So we have some representative of what this could lie in. But I agree with you in the fact that because there isn't any existing infrastructure support for this, you can't really describe what's the correct way to do this.
Yes.
Yeah, I understand
that. Any more questions? Okay, so that was it for this one. But we have a lot of content in the paper. So a lot of characterization results. I show you like 3 figures, but in the paper, I believe we have 22, 23 figures that we analyze: temperature, spatial variation, timing parameters, access pattern, data pattern, aggressor row on time, and so on for both. And the combined access pattern of RowHammer with processing using DRAM operations. Basically, you do first Comra or Simra, and then you do RowHammer. And we compare against just purely doing RowHammer and how much HC first changes. And we observe that the combined pattern with RowHammer with PUD is more effective than RowHammer alone, and it reduces HC first by 1.6 times on average. And we have a lot more details and analysis on mitigating PUD-hammer. We discuss how modifying DRAM chips could help mitigating it. More details on track adaptation. I'll show you just 2 of them, but we discuss what is the challenge over there. So for example, you simultaneously activate multiple rows, right? So you need to update multiple counters at the same time as well. How are you going to do that? And what will be this is a bit power efficient solution. What will be the area efficient solution? So to adapt crack, which incurs higher performance overheads and a lot more. So our paper is available on arXiv. We're still and keep expanding it. You can check this link, and I think slides are also online. And let me conclude my talk for this paper. So in this study, we extensively studied the interaction between read disturbance and multiple row activation-based processing using DRAM operations. And we characterized many DRAM chips, 316 DDR4 chips from 4 major manufacturers. And we observed that PathHammer significantly exacerbates the read disturbance vulnerability. And it bypasses in DRAM RowHammer mitigation and uses much more bit flips than RowHammer. And we adapt industry's latest solution to RowHammer, per row activation counting for PathHammer. And we observe that the adapted solution incurs almost 50% of average performance overhead. And we hope that our findings guide system level and architectural solutions to enable read disturbance resilient future pod systems. That was it, and I'm happy to answer your questions more.
So should we kill SIMDRAM?
Not yet. No.
Okay.
We need to think about more when we design new chips in the future. I think if we're going to enable this pod, which has clear benefits that is shown before from a lot of works, right? So this should be taken into account, but I think this shouldn't scare people, that we should find more and more capabilities in DRAM chips so that we advance basically DRAM. And this should be also in a parallel. We should also find more and more intelligent solutions to mitigate PathHammer better than what we have done here. But what we have shown is that I think it's just again, just be careful, and it's not easy to mitigate. It's not just like, yeah, I will just adapt this. We should think about it more, and I guess, yeah, we should investigate both computational capabilities in DRAM chips and both the security of it, robustness of it. Yeah.
So the results that we see, it's coming from double-sided sandwiching, right? So is it possible to, let's say, profile this vulnerability of a given DRAM chip beforehand so that we lay out the data in such a way that when we are doing operations in runtime, we can kind of contain these effects?
So the issue is that, as I showed, like more than 25% of tested victim rows experience more than 99% of HC first reduction. So you don't have a lot of rows to, I guess, like, yeah, I'll just do this operations here. But yes, I believe we should test again beforehand, maybe online again, because this could change during time.
So I'm saying, like, the numbers that we saw, it's coming from double-sided.
Yes, these are from double-sided. Yes.
So if we ensure that we are not doing double-sided in the runtime, does this help reducing this?
It helps.
Or increasing this hammer count a bit?
So we observe that if you do it with single-sided, for example, Comra, so
because that's something that is in our hand if we change the data layout, right?
Yes.
So does that relaxes the situation, or it's still bad? I think it might be still bad.
It helps, but it's still worse than RowHammer. So basically, this is, for example, single-sided Comra versus single-sided RowHammer. As you can see, it can go like 7,000 to 4,000 or like 10,000 to 7,000. And let me check for SaMRay as well. So, for example, this is from some chips. It goes from 62,000 to 54,000. It's not that drastic as double-sided as you would expect, because it should be very similar to a RowHammer, right? So you're not sandwiching them at the same time, you're just activating, but activating multiple of them. But now, when you do this, now you have a lot of victim rows. Well, so assume that you will have 32 rows that you hammer at the same time, and each of them will have 2 victims.
2 of them.
At least, and if there's a blast radius, they will have 4 victims. Then you will need to refresh your whole subarray just for this. So it also has advantages like that, but it also has disadvantages compared to.
I think we should put that number. I mean, definitely it's getting lower than 62K for single-sided RowHammer, but we should probably put this 56K number in a like a context of, like, for example, what Giray said, like how many of these operations we need to do a matmal, right? So
yes,
that would, if this is coming on the same ballpark, then we know that how much flips we can expect.
But this is true for benign applications. What if you have an attacker on that system? It could leverage those things, right? So in most of the RowHammer papers that we investigate, we also, for example, in BrackHammer, on BlockHammer, most of the time we assume attackers over there as well. So in benign, maybe it's good, maybe it will help, but I don't know how many activations you will need. You need to do the math. But in a presence of attacker, it could exploit this operation as well, right?
Yeah, that's true.
Yeah.
So even in benign, is it actually easy to avoid that double-sided scenario? Because you perform bit serial operations and let's say you add up like 2 8-bit numbers, you go with the lowest order and then the next one and then the next one, and every addition actually sandwich some rows in between, no?
Oh, but what he's saying is that, like, assume that you have dedicated some rows that you're not sandwiching. You're just, for example, copying the data these two, like, to make it single-sided. So it's in an assumption that you're not sandwiching a row. Would that help? That was the question. So on that sense, yes, but as you said, yeah, maybe it's inevitable for that intense workloads. But yeah, we need, I think, for this study to evolve, I think we need more like scheduling, more like programming for processing using DRAM, so that we will also understand the needs for that. So those are all open-ended like questions, right? So do we need 54,000 activations? Maybe, maybe not, but unfortunately in the literature we don't have this answer yet. Any more questions? Then, yes.
When you're processing using memory operations and commodity
Yes.
DRAM chips as they are designed today, and they're not designed for doing these operations.
Yes.
Clearly. So it's good to characterize real chips and show results. I think it's really good to have more and more studies like this. But if DRAM chips are designed for doing these operations for real, going into the future, how do you expect these learnings to transfer to those chips, which will hopefully be designed in a maybe different way?
So I think the fundamental issue is there still. In order to do computation, you need to activate multiple rows at once. So if we are not careful, or the manufacturers are not careful for designing it, once you sandwich them, it's almost the same. I don't want to overclaim it, but we believe that the underlying phenomenon is coming from actually sandwiching it and activating those rows at the same time. It could depend on the access pattern as well, like, because we are violating the timings and we don't know what's going to happen. But we believe that, like, we have the timing sweep as well in the paper. But we believe that the activation of these two at the same time, these two aggressors, is the let's say, the root cause of this reduction. So right now, on top of my head, I don't know what could be the answer, but I'm not sure if we can avoid this thing. So basically, maybe the ambit way over there, when you have like separate compute region, definitely helps. Maybe we should design like that, and maybe we should be careful while implementing row clone, so that copying from storage to compute region wouldn't cause this much of an effect. Maybe we can avoid by combining what we learned from what we shown from mbit and then what we learned from this row clone, so that we combine them to design our DRAM chips to avoid such HC first reduction. Maybe that could be an answer for future.
Yeah, I like that actually. I think that's good for thinking about future work. How would you design DRAM to do computation while avoiding as much as possible these issues that get exacerbated if you do computation without changing anything in DRAM?
Yes.
Yeah. I have another question, which is maybe moot if you design DRAM carefully, but this could be a reliability issue. How would someone exploit this as a security attack? Or do you foresee this being exploited as a security attack?
Could be. I don't know. So the effect is there, and it's very easy to exploit, I would say, compared to RowHammer, where you need to do a lot of like hammering and make sure that you're sandwiching. So here, even you're not sandwiching, it's even reduced. So maybe it makes things a bit easier for attackers as well. And also, I believe, like, for example, the power side channel could be there as well, because we see that in the other paper that I'll discuss in 2 weeks, that it increases the power consumption, so that you will understand if you activate 1 row or 32 row. So I think there are some things that security people could exploit here, definitely. But yeah, in going in future, we should definitely be careful about those side effects, I believe, similar to what happened to Prague.
Okay.
So, because we're talking about processing using DRAM, would as an execution model, because there's no established execution model, could we create an execution model that is aware of this? So, could we avoid the security part of the equations? The reliability we cannot avoid, but can we avoid the security part by essentially trying not to sandwich a row of another user? Because we could have the control and we could use processing using DRAM operation in any way or form we would like, right?
Yes.
So could we create an execution model that tries to avoid this? And
yeah, that could do that. Like could like just dedicate just one compute region to someone, just one user, or just like similar to what we did, like just giving one bank to another, you only one user. Similar to that, we can do that similar things here as well, like just
with even less constraints, because we just need to constrain the sandwiching, right? So we could coexist in the same bank, but we could not allow sandwiching and selecting 2 specific rows that would potentially be harmful.
Yeah, I believe similar to RowHammer countermeasures, you can apply those things here. And for the uniqueness thing, that as I said, like maybe giving the compute region to just only one, dedicated to just one user for just in a subarray, could help as well for those kind of things.
Okay.
Yeah. Thanks. Okay. Any more questions?
Okay. Thanks, Ismail.
Yeah, thanks.
We can, thank the speaker. Okay, so now it's 11:30. The plan was to have a lunch break at 12. But I guess we can stay a bit longer and listen to Hasong's talk as well. It includes 3 papers. So it means that maybe we will go to lunch break around like 12:45 or something like that. So I'd like to take a vote on that. So should we take a break now or after Hasong's talk? Okay. Sorry? Okay, there are no hands raising. So option 1, after Hasong's talk. Okay, this is the majority already. So let's get Hasong here. Could you get rid of the, yeah. Screen sharing is paused, no. So now we have Hasong's talk. SaLWo is a PhD student in the Safari Research Group. His current broader research interests are understanding and improving the performance and reliability of DRAM-based memory systems. A huge part of it is memory robustness. And he has some other interests as well, such as accelerating BVH traversals to enable high-performance path-traced rendering algorithms and designing efficient memory architectures and systems for large language models. But today we will talk about DRAM disturbance beyond RowHammer, not about large language models, I think.
Hello? Okay. Hello? Hello, yes. Okay, I think everything is good. Yeah, so hello everyone. Welcome to the talk. I will talk about 3 papers that involves DRAM redisturbance beyond this thing? Yeah. Okay. Yeah, I will talk about DRAM redisturbance beyond RowHammer. So here's the high-level summary of my talk. I will first talk about RowPress. It is another widespread DRAM redisturbance phenomenon that is different from RowHammer. It significantly reduces the minimum number of aggressor activations needed to induce bit flips or AC-min by orders of magnitude. And then I will talk about combining RowHammer and RowPress, where we show that hammering one aggressor row and pressing the other in the double-sided access pattern achieves similar AC-min than double-sided RowPress, while significantly reducing the time to induce the first bit flip. Finally, I will talk about the inconsistencies between device-level study and real chip characterization results of DRAM redisturbance. So in this paper, we study the DRAM redisturbance bit flips characteristics. We find that these characteristics observed from real chip characterization experiments are not fully explained by existing device-level studies using TCAT simulation. So first, I will talk about RowPress. So in this paper, we demonstrate and analyze RowPress, a new redisturbance phenomenon that causes bit flips in real DRAM chips. We show that RowPress is different from the RowHammer vulnerability. We demonstrate that RowPress is using a user-level program on a real Intel system with real DRAM chips. And finally, we provide effective solutions to RowPress. First, I will talk about some necessary DRAM background. DRAM is the prevalent technology to implement main memory. A DRAM cell stores 1 bit of information in a leaky capacitor, and DRAM cells are organized into DRAM rows. Redisturbance in DRAM breaks the fundamental security property of memory isolation. A prominent example of this is RowHammer. We are repeatedly opening or activating and closing a DRAM row many times causes RowHammer bit flips in adjacent victim rows. So here we ask the question, are there other redisturbance issues in DRAM? So RowHammer, as for the time of the publication of the paper, is the only studied widespread redisturbance phenomenon in DRAM. And most mitigation works on RowHammer, they work by detecting a high row activation count. So it bears the question, what if there's another redisturbance phenomenon in DRAM that does not rely on a very high row activation count? If so, then like we can just bypass all the mitigations very easily. So now let's talk about RowPress. RowPress is a redisturbance phenomenon that if we keep a DRAM row open for a long period of time, it is enough to cause bit flips in adjacent rows. Doing so does not require many row activations as RowHammer. And in extreme cases, we find that like activating the aggressor only once is enough to induce bit flips in the victim row. And now let's see how this is different from RowHammer in more detail. So instead of using a high activation count, RowPress just increases the time that the aggressor DRAM row stays open. We observed that in extreme cases, if we let the DRAM row open for a very long time, 30 milliseconds, then like only one activation of the DRAM row causes bit flips in the victim row. So now let's talk about how we characterize RowPress in real DRAM chips. So first, the two major takeaways of RowPress characterization from our real chip studies is that first, RowPress significantly amplifies DRAM's vulnerability to redisturbance, and second, it has a different underlying mechanism compared to RowHammer. So first, I will talk about our characterization methodology. We use an FPGA-based DDR4 DRAM testing infrastructure. It's developed from SoftMC and DRAM Blender. It allows us fine-grained control over the DRAM commands, timings, and temperature. We test 164 DDR4 DRAM chips from all 3 major DRAM manufacturers. We cover a wide range of DRAM die densities and revisions. So the key metric we are looking at is the minimum number of aggressor activations to induce at least 1 bit flip in the victim row, or AC min. And here we first start with a single-sided access pattern, and which sweep the aggressor on time from the minimum value of 36 nanoseconds, or the datasheet TRS values, to 30 milliseconds. So here is a figurative illustration of the access pattern. And here we use the checkerboard data pattern. We set the DRAM temperature to 50 degrees Celsius, and we use a bisection-based algorithm to measure AC min. We have more sensitivity studies in the paper. So the key characteristics of RowPress, as we mentioned before, is that it significantly amplifies DRAM's vulnerability to redisturbance, and it has a different underlying mechanism compared to RowHammer. So let's now see how it amplifies DRAM's vulnerability to redisturbance. We find that RowPress reduces AC min by 1 to 2 orders of magnitude. In extreme cases, activating the aggressor only once is enough to induce bit flips, and it gets worse as temperature increases. It is different from RowHammer because RowPress affects a different set of cells compared to RowHammer and retention failures, and it behaves very differently as we change the X pattern and temperature compared to RowHammer. So first, let's see more detailed characterization results on how RowPress amplifies DRAM redisturbance. So here, we plot how AC min changes as we increase the aggressor on time or TIA-GAN. Here we show the a result from an exemplar DRAM. Here we plot AC min on the y-axis in log scale and aggressor on time on the x-axis. The error band around the data point show the min-max of the AC min values we measure. And when TIA-GAN is 36 nanoseconds, the axis pattern is identical to RowHammer. And as we keep increasing TIA-GAN, the attack pattern becomes RowPress. Here we highlight two aggressor on-time values on the x-axis, TREFI and 9 times of that. These are the potential activation time upper bounds as indicated by the JDAC data for standard. Here we also highlight AC min equals 1 on the y-axis. We see that like at the extreme activation time of 30 milliseconds, we can induce bit flips with only one activation. We observe that as aggressor on time increases, AC min significantly reduces. Here we show the results from 4 different DRAM die revisions and densities from manufacturer S. And here we show the more results from the other 2 manufacturers. We find that they all behave the same. So we observe that on average across all the DRAM chips from all manufacturers, AC min is reduced by 21x on average when TIA-GAN increases from 36 nanosecond to 7.8 microsecond. If TIA-GAN increases further to 70.2 microsecond, AC min can be reduced by 191x on average. So we conclude that compared to RowHammer, RowPress significantly reduces AC min as TIA-GAN increases. Now let's look at how temperature affects RowPress bit flips. So here we show the AC min of RowPress measured at 80 degrees Celsius, normalized to that at 50 degrees Celsius. So we highlight the ratio of 1 on the y-axis. So any data point below 1 means that it requires fewer aggressor activations to cause bit flips at 80 degrees Celsius compared to 50 degrees Celsius. So we observe that when aggressor on time is 7.8 microsecond, RowPress requires about 50% fewer aggressor activations to induce bit flips at 80 degrees Celsius compared to 50 degrees Celsius. So we conclude RowPress gets worse as temperature increases. Now let's take a look at how RowPress is different from RowHammer. So here we study the cells vulnerable to RowPress versus the cells vulnerable to RowHammer. We define the cells vulnerable to RowPress or RowHammer as the cells that flip with the minimum aggressor activation count. And we define the overlap between these 2 kinds of cells as the number of cells vulnerable to both RowHammer and RowPress over the number of cells only vulnerable to RowPress. So here we plot this ratio on the y-axis, and the x-axis shows the aggressor on time. We find that on average, when aggressor on time is larger than 7.8 microsecond, only 0.13% of DRAM cells vulnerable to RowPress are also vulnerable to RowHammer. So we conclude that most cells vulnerable to RowPress are not vulnerable to RowHammer. Now let's take a look at the directionality of RowPress and RowHammer bit flips. Here we plot the fraction of 1 to 0 bit flips on the y-axis over the total number of bit flips we measure. And so we find that for RowHammer, the majority of the RowHammer bit flips are 0 to 1, but the majority of the RowPress bit flips are 1 to 0. So we conclude that RowPress and RowHammer have opposite bit flip directions. Now let's take a look at the effectiveness of single-sided versus double-sided RowPress axis pattern. So here we showed the difference between the AC mean of single-sided and double-sided RowPress. We highlight the difference of 0 on the y-axis. So a data point below 0 means that it requires fewer activations to cause bit flips with single-sided RowPress compared to double-sided RowPress. We observed that as T account increases beyond a certain level, single-sided RowPress becomes more effective in inducing bit flips compared to double-sided. This is very different from RowHammer, where double-sided RowHammer pattern is strictly more effective compared to a single-sided RowHammer pattern. Yeah, we've already seen this temperature figure before. So here we also find that RowPress gets worse as temperature increases, which is very different from RowHammer. As you can see, like as T is close to 36 nanoseconds, the AC mean at 80 degrees Celsius and 50 degrees Celsius are almost the same for RowHammer. Yeah, now let's look at the real system demonstration of RowPress. Yes. You mean for RowHammer?
For RowHammer, that's what is the underlying mechanism that leads to this relationship?
I don't have a very comprehensive answer as of now. But maybe one of the reason is that let's say yeah, so I'm not sure like if I can say it because like it's like live streamed. And
yeah, that's okay. Don't say it that. Okay. So there are some hypotheses basically.
Yeah.
But okay. So there's more work to be done to explain this effect.
So
you can say it that way.
Yeah, maybe like we can see like a comprehensive answer to this kind of question is not always easy, as the third paper that highlights the inconsistencies between TCAT study and leadership characterization highlights. So yeah, there are certain more things to be studied and more works needs to be done in this.
Yeah, that's fine, I think. Basically, we don't quite understand exactly, at least in published literature, why there's such a relationship.
Yeah.
But we need to understand it more to model it better and maybe solve it in different ways.
Yes.
Okay.
Yeah. Okay. Yeah. Thanks, Onur, for the question. So now let's look at the real system demonstration of RowPress. So we use a real Intel processor and a Samsung DDR4 DRAM module that already has the industry's TR RowHammer mitigation in it. The key idea of our real system demonstration is we can keep a DRAM row open for a longer period of time by keeping on accessing different cache blocks in the same DRAM row. So here is a simplified pseudocode of our proof of concept program, where this num reads a variable just controls the number of cache lines we read from the aggressor row. And yeah, if we just read one cache line per aggressor row, then the access pattern is the same as RowHammer. So we test this on 1,500 arbitrarily chosen victim rows on that real machine. And here we show the total number of bit flips and the total number of victim rows that shows bit flips on the y-axis, and the number of and the different numbers of cache blocks accessed per DRAM row on the axis. So we find that if we increase the number of cache blocks we read per aggressor DRAM row, we both have more bit flips and more DRAM rows vulnerable to redisturbance. So we conclude that leveraging RowPress, our user-level program can induce bit flips when sometimes RowHammer cannot. Yeah, now let's talk about how to mitigate RowPress. So we propose a methodology to adapt existing RowHammer mitigations to also mitigate RowPress. So the key idea is that we will limit the maximum row open time, or TMRO, at the memory controller. And then we will just configure the RowHammer mitigation to account for the reduction in AC mean caused by RowPress. So we evaluate this methodology by first adapting to existing RowHammer mitigations, graphene, a counter-based one, and para, a probabilistic mitigation. And we call the adapted versions graphene RP and para RP. We evaluate this in a cycle-level DRAM simulator, RAMulator, and we run 58 full-core multi-program workloads from SPEC, TPCH, and YCSB. The metric we're looking at is the additional performance overhead of graphene RP and para RP over their original versions, and we measure this by weighted speedup. So our key evaluation results show that by applying this methodology, we can mitigate RowPress at a low additional performance overhead. Now, let me conclude the RowPress paper. In this paper, we demonstrate and analyze RowPress, a widespread redisturbance phenomenon that causes bit flips in real DRAM chips. We characterize RowPress on 164 DDR4 DRAM chips from all three major DRAM manufacturers, and we find that RowPress greatly amplifies DRAM redisturbance by significantly reducing the minimum activation count to induce bit flips by 1 to 2 orders of magnitude in realistic conditions. And it has a different mechanism compared to RowHammer. We demonstrate RowPress using a user-level program on real x86 machine, where it can induce bit flips where RowHammer cannot. And then we also provide effective solutions to RowPress with low additional performance overhead. We have more characterization and evaluation results in the extended version of the paper, and all the source code and data are fully open source and artifact evaluated. And yeah, here's the end of the talk for RowPress, and I'm happy to take any questions. Okay, no questions? Then I will move on to the next paper, where we try to combine RowHammer and RowPress. Yeah, okay.
Nobody ask questions, I will. Or maybe Giray is going to ask a question, but he doesn't have the microphone. So you showed a proof of concept with some Intel machine and the Samsung DIMM.
Yes.
Just to demonstrate that you can get RowPress bit flips.
Mm-hmm.
How easy is it to exploit? Well, you get bit flips in a real system in general.
Yes. You mean how easy it is to get?
Yeah, basically, there are multiple things that need to be in place, probably, right? The memory controller should keep the row open.
Yes. Yeah, so the row policy of the memory controller should, let's say, ideally be the adaptive open row policy, so that you can manipulate the row open time with the different number of cache blocks accessed and the number of prior row hits in the bank. And second, you also need to reverse engineer the DRAM address mapping at the memory controller, so you can have an accurate double-sided pattern. Mm-hmm. And the third, you also need to figure out if you have ECC and force, you need to figure out the in DRAM RowHammer mitigation techniques. So for example, here in this specific Samsung module, we know the TR implementation beforehand, mm-hmm. so we can place the dummy row activations appropriately.
Mm-hmm.
Yeah.
I see. And also you need to synchronize with the refreshes. So you need to do all of those things that
we did
you normally need to mount a RowHammer attack rate.
Yes. Yes.
Okay.
So yeah, I would say to successfully mount a real system attack, there are like these many layers from hardware to software that needs to be considered.
But people have shown that you could actually do that.
Yes, yes.
In the
yes.
later after this paper was published.
Yes.
For RowPress.
I think in the latest like MCC paper, they replicated this a result, but I don't quite remember if like they mounted an end-to-end attack. But I guess like if you can have stable,
what is the MCC paper?
It's from Kavis Group. Like they build like a cheaper version of the signal analyzer, then they can like just.
But I think Daniel Grus and Jonas, they had a paper at DIMWA where they had an end-to-end attack actually.
Yeah. That's their access pattern is slightly different, where they only have one aggressor row.
Okay, so it's a single.
Yeah, it's more likely a single-sided attack, but still they can have some increased TIAG by accessing more cache blocks. Yeah.
Okay.
Thanks.
So a quick question as well. Did you look at how the bit flips are distributed in a column or in a code word, let's say? Because you mentioned ECC. What kind of ECC is capable of like mitigating RowPress bit flips?
So we tried to use the RowPress pattern and hammer oppress as many times as possible within the refresh window. And by doing that, we see, let's say, a lot of in some cache lines, there are like many more than 2 bit flips. So completely mitigating RowPress using ECC may not be straightforward, or it requires a lot of area overhead. Yeah, but I don't quite remember the exact numbers, but I think it's like more than 7 bit flips in a cache line, so it's a lot.
Yeah, thanks.
Okay, now it works. So what I got from the talk is that if you keep the row open for a long while, it results in bit flips. But why does it result in bit flips?
So you're asking why does keeping a DRAM row open longer?
No. So this is an observation, like I kept my row open for a while and then bit flips happened. But what caused those bit flips?
I see. So we have to differentiate between the single-sided and the double-sided pattern. So maybe let's start with the single-sided pattern because it's a bit easier. So basically, if in a single-sided pattern, if you keep the DRAM row open longer, you amplify another kind of leakage that is different from RowHammer. And this, let's say, other leakage mechanism basically scales with the row open time. So the longer you leave it open, the more leakage it introduces in the victim cell. Yeah, and for the double-sided access pattern, it's a bit more complicated. So initially, as you increase TIAG on, because you have 2 aggressor rows, the increase in the TIAG on of one aggressor row is the increase in TIAG off of the other aggressor row. And then you have like kind of like 2 compound effects. So for a single aggressor row, if you start to increase TIAG off, you will reduce AC mean because you are, let's say, allowing the charge trap assisted RowHammer mechanism more time to let's say take effect, like those electrons that migrate has more time to go into the victim cells. That's one effect. And the second effect is just that, yeah, as you keep the DRAM row open, the longer time, like the mechanism that scales with row open time also plays a role. So that's why we, like these 2 different components constitute what we observe for double-sided RowPress.
And can you go back to your slide where you show in the beginning the activation count is very high and then it starts to drop? Can you go back to the slide where you're actually demonstrating it empirically? Yes, this one.
Yeah.
So in a real system, what is the average time a row is actually open when you're running a practical application? So here you actually change the row open time based on your simulation, like you decided what it should be, and then you got these results. But if you take a real system and you want to say in my application or set of applications, on average, how long I keep the row open? So where would that point be in this graph?
I see. So in the RowPress paper, we didn't measure the actual row open time in a real system. So we can kind of use like the different number of cache blocks accessed as like a proxy for that. So let's say if you access 64 cache blocks, then ideally your row open time would be 64 times TCCD-L. So maybe about, how's that? What? Yes. TCCD-L is like 6, right? So about 400, like less than 400 nanoseconds. Yeah. Also, there's like a recent paper, MCC, they replicated the RowPress code, and their measurement shows like 300 nanosecond. So maybe like the memory control row policy also plays a role here. So yeah.
But then it's more towards the left side of these graphs.
Yes.
That means in a real system, it's very unlikely that RowPress will be seen.
But there's a single-sided, and in real system, we do a double-sided. So for the double-sided results, you can refer to the full version of the paper. For simplicity, we didn't have the double-sided AC mean figure in the presentation, but the trend is the same. And yeah, I think you asked a very good question. So yeah, the only difference that the double-sided RowPress is compared to single-sided RowPress is that, yeah, so here you observe that as we initially start to increase TIAGAM, AC mean almost doesn't change. But in double-sided, it will change. So yeah. And that is actually, yeah, as I said, like it's like the TIAG off-ish thing. Yeah, we can discuss more offline if you're interested in these things.
Thanks.
Thank you for the very good question.
I think his point was about benign workloads' behavior. So could you also point out what a adversarial workload can do in terms of TIAG on here?
I think our current systems, our RowPress real system code is that adversarial.
Yeah. So what kind of TIAG do we observe there?
We didn't observe this in the RowPress paper. So if you use the number of cache blocks accessed as a proxy for that, then you can assume the row open time to be the number of cache blocks accessed times TCCD-L plus TRCD. So that's about 300 to 400 nanoseconds, I guess. Yeah.
Oh, okay.
Again,
you already answered that. Okay.
It also depends on your row policy, right? Like if you have a simple open row policy, I mean, like the naive open row policy, then you can just like keep it open.
Of course.
But if you have a closed row policy or like adaptive open policy, it will get complicated. So I don't think there's a single good answer to this. In the real system, like there's just so many things involved. Yeah.
So Ha-Sung, you said that TIAG-off has an important role at the beginning, right?
Yes.
For double side. What if I do RowHammer, but with the same TIAG-off? Basically do TRAS, and after per charge give enough time for TIAG-off. It also reduces.
Okay. So for double-sided, right? Like the increase in one aggressor row's TIAG-on is the increase in the other aggressor row's TIAG-off.
Yes.
So yes. So yeah, this effect already exists for RowHammer, but if you do RowPress, it kind of makes it like even worse because of you added the effect of like longer row open time as well. So yeah.
Okay, thanks.
Maybe one last question. You report these from DDR4 devices.
Yes.
I remember Ataberk did for HBM2 some similar study. Any luck with DDR5 so far?
We didn't have the proper infrastructure yet to characterize DDR5 chips, but based on the observation that there's no fundamental change in physical DRAM device layout architecture, I would assume the fundamental issue would still be there, and it make it worse because like they keep reducing the feature size. But if we are thinking about like real system aspects, the introduction of on the ACC may complicate the observation of the bit flips. Yeah.
Thanks.
Thank you. Thank you for the question. Okay, there are no other questions, then thank you very much for the questions. And we'll move on to the next paper. So in the next paper, we try to combine RowHammer and RowPress. So yeah, our paper and experimental characterization of combined RowHammer and RowPress redisturbance in modern DRAM chips. So yeah, I guess to save time, I will skip the background. RowHammer and RowPress, you've heard about this in the previous paper presentation. So yeah, from the previous presentation, we know that like RowHammer and RowPress have different error mechanisms. So like, what if we combine them? So let's say we have this kind of like double-sided pattern. We hammer one aggressor row and press the other aggressor row. Like what will happen? So our goal is to experimentally characterize this combined pattern. And to do so, like we characterize this pattern on 84 real DDR4 DRAM chips from all three major manufacturers. Our key results show that if we use this combined pattern, we take significantly less time to induce the first bit flip compared to the state-of-the-art double-sided RowPress pattern by up to 46.1% faster. And the initial bit flips are different across RowHammer, RowPress, and these combined patterns. So we make an hypothesis that like the redisturbance caused by RowHammer from one of the two aggressor rows in the double-sided pattern is much more significant than the other. Now let's look at, yeah, I guess I'll skip the background just to speed things up. And yeah, we will just directly go into the tested pattern. So first, let's talk about some like the baseline patterns that we compare with. The conventional single-sided and the conventional single-sided RowHammer or RowPress pattern where we just have like one single aggressor row. If we let the DRAM row, if we let the aggressor open for longer, then it's RowPress, otherwise it's RowHammer. And the second baseline conventional double-sided RowHammer and RowPress pattern where we have like two aggressor rows sandwiched in a victim row, and they are both hammered or pressed. So the thing here is like the conventional pattern has the same aggressor on time for both aggressor rows. So now the pattern that we test, the combined pattern, we hammer one aggressor row and press the other. Let's say the upper aggressor row has the TR equals TRES 36 nanosecond, and the second aggressor row has a TR larger than 36 nanoseconds. Yeah, so we test it with DRAM Bender. It gives us fine-grained control over DRAM commands and timings. And the key metrics we're looking at is first, time to first bit flip. This is just like the wall clock time to induce at least one bit flip using those different access patterns. The lower this metric is, like the worse the vulnerability is. The second is AC mean. It's like the total number of aggressor activations needed to induce at least one bit flip. The lower it is, then the worse the vulnerability. So yeah, we test many different chips from different manufacturers covering different die densities and revisions. And for each module, we test the pattern on 3K DRAM modules in a bank using checkerboard pattern, and we repeat everything 3 times. So now let's see the major characterization results. And first, let's look at the time to first bit flip. So here we show the time to first bit flip from one exemplar module from manufacturer S on the y-axis. Aggressor runtime is on the x-axis, and this blue line shows the result for the combined RowHammer and RowPress pattern that we test. The arrow bar shows the min-max value we observe. So when TIAGON is 36 nanoseconds, just like RowHammer, we highlight the 2 potential row open time upper bounds on the x-axis. Yeah, sorry, it's the standard deviation in this figure, not the min-max. And then this green line shows the time to first bit flip for this baseline 1 single-sided RowPress or RowHammer. And then this orange line shows this for double-sided RowPress and RowHammer. So we observed that the combined pattern reduces the time to first bit flip by 78.9% compared to the conventional single-sided pattern. And compared to the conventional double-sided pattern, it's still 37.6% faster. And here we show the results for all the modules we test from all 3 different manufacturers, and they behave the same. So we conclude that redisturbance bit flips can be induced in a smaller amount of time by combining RowHammer and RowPress compared to just using RowPress. Now let's look at AC min. Yes, sure.
On the previous slide, you highlighted a point on the x-axis. Can you talk a bit about the relevance of that point?
It's chosen to be like somewhere like around like a realistic row open time that you can achieve. Yeah. Okay, thank you for the question. And now let's look at AC mean. Again, we have AC mean on the y-axis. It's in log scale. And the blue, orange, and green lines just shows the AC mean for the combined pattern, the double-sided baseline, the single-sided baseline. So we find that compared to the single-sided RowPress, the combined pattern reduces AC mean by 40.5%, and the double-sided RowPress reduces AC mean by 48% compared to single-sided. And this is like this trend is the same across all the chips we test. So we conclude that as TIAGON initially starts to increase, the combined RowHammer and RowPress pattern just needs slightly more aggressor row activations to induce at least 1 bit flip compared to the conventional double-sided RowPress pattern. But it can do everything in a much smaller war clock time. Yeah, so if we put these 2 results together, that the combined pattern can induce bit flip in a smaller amount of time, and its AC mean is like roughly the same as the conventional double-sided RowPress pattern. Then we hypothesize that as TIAGON increases, the redisturbance effect caused by RowPress from one of the 2 aggressor rows in a double-sided pattern is much more significant than the other. That basically explains that like why you don't need both rows to be pressed to induce the bit flips with fewer, let's say, activation counts. Yeah. Now let's look at some further results, the bit flip direction. So we find that as TIAGON increases, the directionality of the bit flips caused by the combined RowHammer and RowPress pattern changes from 0 to 1 to 1 to 0. And we hypothesize that this is because for large TIAGON values, the redisturbance effect from RowPress becomes dominant compared to RowHammer in the combined pattern. And now we also look at the overlap between the combined between the bit flips caused by the combined pattern and conventional RowHammer and RowPress. So let's say, yeah, we have the bit flips caused by the combined pattern, some the bit flips caused by conventional patterns, and the intersection of them is the bit flips caused by both combined and conventional patterns, and we define the overlap as the number of bit flips caused by both patterns and over the number of bit flips only caused by combined patterns. So here we show this like ratio on the y-axis, and the upper row of plots show this overlap for single-sided. The lower row of plots show this for double-sided, and we observe that the combined pattern induces different bit flips compared to conventional single and double-sided axis patterns, as you can observe like the drop in the overlap for the double-sided pattern and the initially very low overlap in the single-sided pattern. Yeah. And to conclude, so in this paper, we experimentally characterize and demonstrate the combined redisturbance from both RowHammer and RowPress in real DRAM chips. We experimentally characterize 84 DDR4 DRAM chips from Austrian major manufacturers. We find that the combined pattern takes significantly less time to induce the first bit flip compared to the state-of-the-art RowPress pattern, and the initial bit flips are different. So we put forward a hypothesis that the redisturbance caused by RowPress from only one of the two aggressor rows in a double-sided pattern is dominant. Yeah. So we also hope for some future work. So we need to test more, and more importantly, examine the device-level mechanisms of RowHammer and RowPress more to verify our hypothesis and further our understanding of the landscape of DRAM redisturbance. Yeah, so here's the end of this paper presentation, and happy to take any question. Yes.
Thanks. So you combine RowHammer and RowPress in some ways here.
Yes.
Are these the like worst possible ways?
No, it's an straightforward way to combine them, and also there's some intuition behind it, because some prior device level study shows that different aggressor word line relationship with respect to the victim cell. That is to say, whether the aggressor word line is a passing word line or neighboring word line, has different underlying error mechanisms with respect to redisturbance. So by assigning different hammering or pressing patterns to the two different aggressor rows, we have a, let's say, just it's an intuition to kind of, let's say, exacerbate this difference in the device level. So if, let's say, if we interleave the hammering and pressing in a single aggressor row, so the intuition is that, like, because RowHammer and RowPress, they have like different bit flip directions, then like you're canceling out each other. I think, yeah, like we also like done some like very preliminary initial tests. They don't seem to give like any interesting results. So yeah, that's why we go for like this double-sided pattern.
I see. Okay. Yeah. But there could be basically better in the sense that it could induce more bit flips earlier.
Yes.
Better patterns.
Yes. So I believe that if we have a very comprehensive and rigorous understanding from the device level, we can just construct such pattern in a principled way. Yeah.
Yeah. But that device level understanding doesn't exist at the moment.
Yeah, it's not there yet. So yeah.
But so, that device level understanding kind of depends on the experiments done at the higher levels, right?
But So yeah, I think we will talk about exactly this in the coming paper presentation. So it turns out that like maybe the existing device level works, they are, let's say, their modeling may not be comprehensive enough to capture all the effects that happens in a real chip. So yeah, there's still more work to be done in this direction. Yeah.
Okay. Anybody else?
Just to understand what exactly the worst case patterns mean. Are you talking about what data should be written in the aggressor rows, or are you talking about there should be 2 aggressor rows where you're pressing and the 2 aggressor rows where you're hammering? What exactly do you mean by worst case scenario?
I see. That's a very, very, very good question. So I think there can be multiple aspects to, or let's say like multiple ways to define what's the worst case. Let's say if you start from an, let's say, just like a scientific understanding of the problem, then maybe you can define it as like the smallest AC min. And like if you want to think about it from like a system level or mitigation level, you may want to define it as like inducing the bit flips in the shortest amount of time. And or like if you want to, let's say, define it from like a reliability level, maybe you want some statistics that just like, yeah, across all the data patterns, all the access patterns, all the environmental parameters, what is like the highest time to first failure that, sorry, the lowest time to first failure that you can observe. So yeah, I think I don't think there's like a single definition on what is the worst case pattern. And so it's more important to, let's say, put it into context so that then you can find the most appropriate definition of the worst case. Yeah.
And the way you combine RowHammer and RowPress is that you are hammering one row and pressing the other row.
Yes.
Is there any other option?
What?
Is there any other option of combining these two?
Yeah,
any other way? Yes.
Let's say you can like just arbitrarily interleave hammering or pressing on the same aggressor row. Yeah, that's also another way to combine them. Yeah.
So does that make sense to interleave? Because from what I understand from this, based on what I understand from this presentation, for a given double-sided access pattern, one aggressor row is better to hammer and the other one is better to press.
Yes.
So does it make any sense to interleave them, like hammer and then press and then hammer the same aggressor row?
I haven't tried that. Maybe it is, but I think like one challenge is that like this, like the search space of this pattern is just like too huge to like let's say do a fuzzing essentially. So that's why let's say personally, I'm inclining more to, let's say, yeah, we start with these observations, we build a fundamental, comprehensive, rigorous device level understanding, then we can just principally construct a worst case pattern. I would think that might be more efficient, assuming we can have a comprehensive device level understanding. Then, yeah, that would be my personal, let's say, preferable way approach. Let's say towards finding a quote unquote worst case pattern. Yeah.
Okay, thanks.
Yeah, please. Yeah.
Okay, so I still need to do a little bit more reading on how this works under the hood, so my understanding is a bit cloudy. But in the last paper, you mentioned that there's still some things that we need to know about the system to be able to make this attack very effectively. So like the arrangement of the attack because of the mitigations that exist and stuff like that. So wouldn't now that we can, because we can reduce the time until the first bit flip, is it now not kind of viable to irrationally try a random access patterns like a lot of times and then just hope that we end up getting lucky? Because it's kind of a bit, you know, of a huge handicap to have to know a lot about the system before attacking it. And so what bandwidth?
That's absolutely true. So like you can do a fuzzing at the real system. So if you check the Blacksmith paper, they are kind of they're doing like a fuzzing-ish thing. It's just that like if you know more about the system, you can significantly reduce your search space. Yeah.
And can you so what's the bottleneck that doesn't allow me to just do like a lot of access? If it's CPU like computation, can't it, like do the existing extensions, for example, like M.2 or PCIe, like is there some way that these connections have enough bandwidth that I can somehow access you know, a lot more volume? Like for example, you know, these accelerators for the GPU that like can't a malicious one, for example, somehow trigger more like accesses?
I think that's a very good research topic in the security domain, like how you find the highest memory request injection rate into your memory controller. And there are many interesting works there that uses, let's say, other components in the system other than the CPU to initiate memory requests. There like, so people have done RowHammer with DMA, with NIC, with I think a more interesting one would be using the cache coherence protocol of the CPU to hammer. So all of these, like, they have, let's say, different ways of accessing DRAM. They have different, let's say, request injection rates. And there are even works that studies like which kind of instruction and like access pattern in the CPU gives you the highest, let's say, activation rate. I think like there's a work from Microsoft that they show that like in some CPUs, if you just do CL flush without accessing, you are also hammering the DRAM. It may even have higher activation rate. So it's very, there are like a lot of things in the system that you can play with to do this. Yeah.
Thank you.
Yeah. What? Okay, good. Yeah. Thanks, everyone, for the questions. So now we are at the last part of the presentation, where we talk about the inconsistencies of the DRAM redisturbance bitflip characteristics between the real chip characterization results compared to the existing device level studies using TCAD simulation. Yeah, so now I will present this paper, Revisiting DRAM Redisturbance, Identifying Inconsistencies Between Experimental Characterization and Device Level Studies. So as a summary of the paper, our goal here is to align and cross-validate the experimental characterization of DRAM redisturbance, that is RowHammer and RowPress, against the error mechanism modeled by existing device level simulation. So here we face a challenge that there's a gap between real chip characterization and device level mechanism due to low level DRAM layout that is true and enter cells. So our key methodology here is first we extract the key device level redisturbance mechanism from prior works. Then we reverse engineer the true and enter cell layout of real DRAM chips. Then we perform real chip characterization results that directly match the access and data patterns the device level works use. So we find the following key inconsistencies. First, for double-sided RowHammer, experimental characterization shows bitflips in both directions, while device level studies suggest only 1 to 0 bitflips will happen. The second, for single-sided RowPress, experimental characterization shows overwhelmingly 1-0 bit flips, while device-level mechanisms suggest that both kinds of bit flips should happen. Yeah, again, I will skip the parts that we've already seen, but I will keep the parts that we haven't seen. So as a necessary background on true and anti-DRAM cells, so the DRAM bitline sense amplifier is a differential amplifier. So it has two ends, bitline or bitline bar. A DRAM cell can represent a logical one by storing either positive or negative charge, depending on if it's connected to bitline or the complement bitline bar. Let's say if a DRAM cell represents a logical one by storing positive charge, or let's say like if the capacitor voltage equals to DRAM core voltage, we call it a true cell, and an anti-cell if it uses like VSS to represent a logical one. So yeah, and I will skip RowHammer and RowPress. And yeah, now let's take a look at the summary of existing device-level studies that studies DRAM redisturbance. So we extract the following key characteristics of device-level DRAM redisturbance mechanisms. First, double-sided RowHammer should only induce 1-0 bit flips. The second, single-sided RowPress should induce both 1-0 and 0-1 bit flips. So as a relevant background, here is like how modern 6F² DRAM is actually laid out. So on the left side, we have like the top view of the physical layout of a 6F² DRAM array. And on the right side, we have the cross-section of one active region. It's the side view that contains two DRAM cells, cell 1 and cell 2. And we mark up the relevant components in the cross-section as well as we mark it up. We mark up the same thing in the top view. So for this active region and the two cells, we have their respective word lines. For cell 1, we have word line 1, cell 2, we have word line 2. We also have two other word lines that are physically adjacent to this active region, but they don't form any connection or transistor with this active region. So we call them passing word lines. And we also have like the passing word line on cell 1 side is passing word line 1, and the passing word line on cell 2 side is passing word line 2, or PWL. Yeah, so now let's take a look at the key error mechanisms that prior works study. So the most important one is called like trap-assisted electron migration mechanism. So basically, let's say there, like due to the fabrication process, there will be charge traps near the let's say aggressor word line interface. And when the aggressor row is open, these traps are charged with electrons. When the aggressor is closed, these electrons are emitted and some of them migrate towards the victim, which constitutes off leakage. So if you keep hammering, opening, closing, then you are just like pumping electrons into the victim. Yeah. So also for double-sided RowHammer, we know that like it's much more effective than single-sided from the experimental characterization. The reason for this is that, let's say in a double-sided RowHammer, we have two aggressor rows sandwiching the victim row. So one aggressor row will be the neighboring word line, NWL here, and another aggressor row would be the passing word line, PWL here. So when we when we keep hammering them like those, when one aggressor is open, the other is closed. When the row is closed, the other is open. So let's say, yeah, when NWL is closed, as we talked about before, the electrons are emitted from the traps, then in some of them, they migrate towards the victim. But in a double-sided case, the passing word line is also open. So the electric field from the passing word line attracts more electrons towards the direction of the victim. So this causes an enhancement of the electron migration into the victim, causing more leakage. And also, as we also briefly talked about in the RowPress talk, because when the passing word line is open, the neighboring word line is closed. It's closed for a longer period of time, which allows more time for electrons to be emitted from the traps, which also causes more leakage. So these two mechanisms enhances double-sided RowHammer, and because both of them injects electrons into the victim, so it should enhance 120 bit flips. And some of the device level works even say that, the 0 to 1 bit flips are eliminated completely. So we conclude that double-sided RowHammer should induce 120 bit flips. And now let's take a quick look at the device level error mechanism of RowPress. So the prior works show that, the two different aggressor row types have different error mechanism. Let's say if the neighboring word line is the RowPress aggressor row, then when it's kept open for a long period of time, its strong electric field just like weakens the victim word line control of the channel, so you increase the leakage in the victim channel, causing 0 to 1 bit flips. And if the passing word line is the aggressor, then if it's kept open for a long period, its strong electric field just like draws electrons towards the victim from like other places in the substrate. So this causes 120 bit flips. So the key characteristics here is that like single-sided RowPress should induce both 120 and 0 to 1 bit flips, depending on like which aggressor row type your aggressor word line is relative to the victim cell. Now let's do the real chip characterization that aligns with their access and data patterns. So again, we use DRAM Bender, and we test like a wide range of DRAM cells from all three major manufacturers. And in order to fully align with the device level works, we need to reverse engineer the true and anti-cell layout. So the reason we do this is because like the internal DRAM architecture is opaque to the memory controller. So as a result, like if you're observing a bit flip from an anti-cell, then the actual bit flip direction is the opposite. So to align our real chip observations with device level studies, we have to fully understand like which types of cells we are testing. So we use a retention failure-based reverse engineering methodology. This is like because the following reasons. So prior works show that major DRAM retention leakage passes, junction, and GIDL, they leak towards the access transistor substrate, which are negatively biased. And prior works on experimental characterization of DRAM retention failures assume DRAM retention failure only contains 120 bit flips, and they leverage this to reverse engineer and true and anti-cell layout, and we take the same approach. So our reverse engineering results comes out consistent with prior works. So now let's take a look at the real chip characterization results. So first, I will just summarize like what are the inconsistencies that we find from this study. The first inconsistency is that it's about the double-sided RowHammer bit flip direction. So real chip characterization shows that we can induce both 0 to 1 and 120 bit flips, and the AC mean of 0 to 1 bit flips is like smaller than 120 bit flips. However, the device level mechanisms say that, you should only induce 120 bit flips for double-sided RowHammer. The second inconsistency is like the double-sided RowHammer bit flip count. So our real chip characterization shows that only with a sufficiently large hammer count, you will observe more 120 bit flips than 0 to 1 bit flips. But the device level mechanism again says that double-sided RowHammer enhances 120 leakage. The third inconsistency is about the bit flip direction of single-sided RowPress. So our real chip results show that we observe overwhelmingly 1-0 bit flips with RowPress, while the SaLWo mechanisms say that, yeah, both kind of bit flips should happen. So now let's take a deeper look into these results. The first, about the bit flip direction of double-sided RowHammer. We use a double-sided RowHammer pattern, and for the data pattern, we have all physical 1 or 0 in the victim rows, and the aggressor rows always have the opposite value. The key metric is HC first, the minimum aggressor row hammer count to induce at least 1 bit flip in the victim row. Here we show the HC first measurement from one example DRAM die from manufacturer M. So here we show the distribution of HC first over all the rows that we test on the y-axis, and on the x-axis it just shows that like the different bit flip direction, and we observe the same thing for all the module, all the chips from all 3 manufacturers that we test. So we find that on average, the HC first of 0 to 1 is like 24.7% lower than the HC first of 1 to 0. And even before this, like we already see that like double-sided RowHammer can induce both kind of bit flips. Yeah. So the takeaways from this study is that double-sided RowHammer involves error mechanisms for inducing both 0 to 1 and 1 to 0 bit flips. For double-sided RowHammer, the observed error mechanism for 0 to 1 bit flips is even initially stronger than that of 1 to 0 bit flips in the most vulnerable DRAM cells, and these are like essentially like the opposite of what the SaLWo mechanism shows. Yeah. Now let's look at the bit flip count of double-sided RowHammer. We use the same axis and the data pattern, and the metric here is the per row bit flip count after hammering each aggressor row for a sufficiently high amount of times, 500K for each aggressor row. So here we again show the distribution of per row bit flip count on the y-axis, and you see that if we hammer for sufficiently high amount of times, there are indeed more 1 to 0 bit flips than 0 to 1 bit flips. This seems to like align with the SaLWo mechanism, but then we look at as we increase the hammer count from the minimum to the maximum. When we start to observe more 1 to 0 bit flips compared to 0 to 1 bit flips. So here we define a metric. It's called HC. 1 to 0 exceeds 0 to 1. This is like the minimum hammer count where we start to observe more 1 to 0 bit flips than 0 to 1 bit flips. So here in this table, we compare this HC 1 to 0 exceeds 0 to 1 metric with the HC first of 0 to 1. And we find that on average, you need to hammer 4 times of HC first for you to observe more 1 to 0 bit flips than 0 to 1 bit flips. And like in extreme cases, like you need to hammer like 7.5 times more. So the takeaway from this study is that for double-sided RowHammer, the observed error mechanism to induce 1 to 0 bit flip are only stronger than that of 0 to 1 bit flips, only if you hammer for like a really, really large amount of times, like on average 4 times than your HC first. This is again also like different from the device level characteristics that like double-sided RowHammer enhances 1 to 0 bit flips. Now the last inconsistency, the bit direction of single-sided RowPress. So we use a single-sided RowPress pattern, and we do it at both the upper and the lower aggressor row. Like these are like two separate experiments. And the aggressor row is kept open for 7.8 microseconds per activation. And the data pattern is the same as, and again, we look at the per row bit flip count after activating each aggressor row for a sufficiently high amount of times. And we see that like there are no 0 to 1 bit flips even. So across all the chips we test, only in one module, it's manufacturer S 8 gigabit E die. Only in this case, we observe a single 0 to 1 bit flip. All the other modules, all the other rows, we observe 0 to 1 bit flip. So this, the takeaway is that like for single-sided RowPress, for both the neighboring word line and the passing word line, the observed error mechanism for inducing 1 to 0 bit flips is much stronger than that of 0 to 1 bit flips. So that like we can only observe 1 to 0 bit flips within the refresh window. This is also different from the Vasila works that says, yeah, the two kind of aggressor rows will induce both kind of bit flip directions. So let me summarize the inconsistencies find. So we find that both the bit flip direction and the bit flip count of double-sided RowHammer is different, and the single-sided RowPress bit flip direction also differs between real chip characterization and device-level studies. So based on these, we put forward some hypotheses. And there are two possibilities to, let's say, explain our results. First, it's possible that the retention failure-based true and anti-cell reverse engineering methodology is not always applicable in modern DRAM chips, or the current device-level explanations of DRAM redisturbance is not comprehensive enough to capture all the possible factors. So one hypothesis for like the first possibility, in modern DRAM chips, like are there like other major retention leakage passes that does not leak towards the substrate? So is like the dielectric leakage in the cell capacitor more like dominant? If so, like then that leaks towards the bit line contact, which is VDD/2. And yeah, like some prior work showed that like this is becoming more pronounced in modern DRAM because the process keeps shrinking. So this is a possibility. Or like if we think more about the device level mechanism side, maybe the existing device level works, they are making some oversimplified assumptions during their simulation. For example, prior works that study the trap-assisted electron migration error mechanism, they only focus on acceptor-like traps. Are donor-like traps not really not causing any non-trivial leakage? And maybe the device-level simulations, because they only focus on a few isolated structures and components, for example, just a single active region, 2 capacitors, 4 word lines, and a bit line, maybe by doing so, they are not modeling the redisturbance mechanism that comes from the coupling of other components in the array. Maybe those, like there are other things that becomes first order when you put everything in the context of a full DRAM array. And well, there's also like another possibility that maybe our real chip characterization results are heavily skewed because maybe the bit line sense amplifier has an asymmetrical sensing margin of reading a 1 and reading a 0. It's also possible. Yeah, or like there can just be like 2 different sets of redisturbance leakage mechanism that affects different sets of DRAM cells. Yeah, so let me conclude my talk. So in this paper, our goal is to align and cross-validate the experimental characterization of DRAM redisturbance, RowHammer and RowPress, with the error mechanisms modeled by the SaLWo simulation. And during this process, we bridge the gap between characterization and the SaLWo studies due to low-level DRAM array layout. So we find the following inconsistencies: that the bit flip direction and the bit flip count of double-sided RowHammer differs between real chip characterization and device-level simulation, and the single-sided bit flip direction also differs from real chip characterization and device-level studies. That's the end of the talk, and I welcome any question.
Any questions?
So how do you resolve these inconsistencies?
So we work with device-level groups. We align our observations and methodologies, hoping we can identify the missing parts and come up with more comprehensive and more rigorous simulation setups and methodologies.
Okay, I think that's a great approach.
Yeah.
And this can open up better collaboration across the stack, which usually doesn't happen.
Yes.
Between system level and device level people.
Yes.
So I'm curious if you have any plans, more concrete plans on investigating if this true anti-cell layout reverse engineering methodology is correct or not.
I tend to believe it is correct. We have some correspondence with some device level people we can discuss offline. Yeah, but as a side note, let's say, yeah, we assume the retention failure based reverse engineering mechanism is correct. But we still have to keep an eye on the potential other leakage mechanism that may rise up, as one of these hypotheses shows. Yeah, here. Let's say, it's ICET22 paper, they find out that because modern DRAM process feature set is so small, then the pattern alignment becomes a big issue. Let's say if your capacitor pattern sometimes it's misaligned, some conductive bridges between the capacitor and the bit line may be formed, and that's a leakage path. And this leaks towards the bit line, so it's VDD/2, not negative. So yeah, I can't guarantee, but we need to keep an eye on these things, basically. Yeah.
Okay, yeah, that makes sense. Thanks. Other questions? Okay, then let's thank the speaker.
Okay, thank you.
Now is the time for the lunch break. We don't have any lunch catered, so you will take care of it yourselves. And I think it's reasonable to come back at 1:30. Any rejection? Okay, no? Okay, let's make it 2 p.m. 1 hour. 1:45, okay. Let's start again at 1:45. We are missing one of these microphones. Have you seen them? Oh, really?
And can people hear me? Am I connected to the room audio? Okay. That's good. Testing 1, 2, 5, 4. Can I have some? Thank you. What's this? Matcha. Very good. I'll skip my self-introduction.
Okay, let's get started. Who didn't get chocolate? Okay, welcome back. Thanks for coming on time. So we have Ataberk's talk now. Ataberk Olgun is a fourth-year PhD student, and he is also a Safari member. And his broad research interests include designing secure, high-performance, and energy-efficient memory systems, especially with worsening DRAM read disturbance vulnerability. Surprise, surprise. It's increasingly difficult to design memory systems that satisfy all three characteristics. His current research focuses on deeply understanding and efficiently mitigating the RowHammer vulnerability in modern systems. His graduate work has been recognized with several honors, including induction into HPCA Hall of Fame. Congrats, Ataberk.
Thank you.
And we are curious to we are curious about what you have to say.
Thank you very much for the introduction. So this talk is titled Experimentally Understanding and Efficiently Mitigating DRAM Read Disturbance. It's a collection of 4.5 research papers, or 5 research papers. It's going to take, I don't know how long, but I have to go over around 280 slides. 1.5 hours is the time I've been given right now. So I need to go over 280 slides in 1.5 hours. Now this is me. Giray already introduced me and my research interests, so I'm going to skip this and briefly remind you about the memory isolation. We want to have this key property in our systems whereby a memory access should not have unintended side effects on data stored in other addresses. This is a fundamental property for robustness. And breaking that can cause terrible issues, as Giray described earlier today. And it's difficult to satisfy in modern memory chips. And these chips are used everywhere. And the reason why we cannot satisfy memory isolation in modern chips is because these chips are prone to disturbance errors, which we have seen examples of. And you already know about RowHammer errors appear when you repeatedly activate and pre-charge an aggressor row. These RowHammer errors appear as bit flips in neighboring rows. And we call the repeatedly activated row aggressor row and the rows that have bit flips victim rows. Now, I won't go into the details of why these errors happen, so I will be skipping a bunch of slides right now. We've already seen seminal work that showed RowHammer bit flips are widespread back in 2014 or 2013. And many researchers exploited these bit flips to break the security of our systems so far in many different ways. And you see some examples here. One thing that keeps coming up, I think, is that error correcting codes are posed as some sort of mitigation or remedy to read disturbance failures or bit flips. But many research papers have repeatedly shown that ECC cannot completely eradicate read disturbance bit flips. And we show it multiple times in our studies as well. And you'll see some example real data showing the ineffectiveness of ECC against these sort of failures in my slides. So that's a sort of like to summarize all of this very quickly. Okay, I'll be skipping some slides, as I said. Memory reliability is reducing. This is one of Onur's slides from his award talk at DSN. RowHammer bit flips are hard to defend against. The bad news is it's getting worse, and the good news is we have a lot more to do. We're architects. We can come up with solutions to this problem, or we can come up with new methodologies, new experiments to understand this problem. And my work is in the line of developing solutions and models and methodologies to understand read disturbance in DRAM chips. So I'll start with variable read disturbance. This is an experimental analysis of temporal variation in DRAM read disturbance. You see a typical DRAM-based computing system here with the CPU and a DRAM module with multiple chips. And we already know how DRAM chips are organized. You have many banks in a chip, many subarrays in a bank, and many cells in a subarray. And you have DRAM rows and DRAM columns or bit lines that are connected to a row buffer. So read disturbance, we already know you repeatedly activate and pre-charge a DRAM row and induce bit flips in neighboring rows. We already know we call the aggressor row the repeatedly activated row, and so on. And we've also seen about RowPress, where we inflict read disturbance bit flips by keeping a row open for a long time, not by repeatedly activating it necessarily. And prior works proposed many solutions, many techniques to mitigate read disturbance bit flips. And these are valuable. Each of them are valuable, I think, because they come with different reliability, performance, energy, and area trade-offs. Regardless, a common operation pattern across many different solutions that they take an action before a bit flip manifests. For example, they refresh a victim row. And to do so, they must accurately quantify the amount of disturbance a row can withstand before the row experiences a bit flip. And this is typically quantified by time-intensive testing for read disturbance bit flips. And the read disturbance threshold, or RDT for short, quantifies the amount of disturbance a row can withstand before it experiences the first read disturbance bit flip. And this is typically expressed in terms of an activation count. And you've seen this in different forms today. It was called HC first and AC min in different research papers. In this research paper, we called it the read disturbance threshold to have a more sort of general name, let's say. So now I'll try to illustrate why it's important to accurately identify this read disturbance threshold value. The x-axis here shows increasing read disturbance thresholds values in arbitrary units. And the y-axis shows performance and energy overhead from your mitigations, and again, arbitrary units. So this is a curve you would expect to see. Basically, as the read disturbance threshold becomes smaller, the solutions or mitigation induce more performance and energy overheads. And for example, one example to that is like if your read disturbance threshold shrinks, you will issue more refresh operations or issue refresh operations more frequently, and you will interfere with demand accesses more frequently. So if you have this ground truth read disturbance threshold value, that's for example 1,000, you want to configure your solution with that exact read disturbance threshold value. Why? Because if you configure it with a higher value, you cannot mitigate bit flips, and your system is no longer secure. So basically, a row has been activated 1,000 times, but your defenses were configured to mitigate bit flips at 10,000 activation count. So you couldn't mitigate the bit flip, and now you're subject to all those sorts of attacks that we've discussed earlier. Not, well, earlier today. And if you're overly conservative, if you have a very low threshold value, you incur unnecessary performance and energy overheads. So in summary, we must accurately identify the read disturbance threshold to securely prevent bit flips at low overhead. And our work tries to answer a key question about the read disturbance threshold. That is, how accurately and efficiently can we measure the read disturbance threshold of each DRAM row? And we record more than 100 million read disturbance threshold measurements across many rows in many different DRAM chips. And we find that the redisturbance threshold of a DRAM row varies significantly and unpredictably over time. The largest threshold we observe for a DRAM row can be 3.5 times the smallest we observe for the same row across many test iterations. And a row's smallest redisturbance threshold value may appear after a whopping 94,000 measurements that took us at least 2 weeks to conduct. And we call this new phenomenon variable redisturbance. It has implications for system security and robustness because the redisturbance threshold of a row cannot be quickly and accurately identified. And we evaluate guard bands, the use of guard bands for redisturbance thresholds, and error correcting codes as a solution for VRD-induced bit flips. And given our limited data set of bit flip locations, we find that relatively large guard bands in ECC could prevent VRD-induced bit flips at significant performance cost. But we think that more data and analyses are needed to make a definitive conclusion. And our results, I think, call for future work on understanding and efficiently mitigating redisturbance bit flips and VRD. This is the outline for the rest of this talk, this part of the talk. I'll continue by motivating our study even more, but you can cut me at any time to ask questions, like how we conducted this workshop so far. So redisturbance bit flips happen in more DRAM cells with fewer activations as DRAM technology scales. We see more than 10 times reduction in redisturbance threshold between chips manufactured 7 years apart. And we say, therefore, that DRAM chips become more vulnerable to redisturbance with technology scaling. This, in turn, causes existing mitigations to become more aggressive, and in turn, they induce higher overheads. Moreover, prior works assume that the ground truth redisturbance threshold can be identified, and in our work, we challenge this assumption, and we see that no prior work studies the temporal variation of DRAM redisturbance and its implications for future solutions. So our goal is twofold. First, we would like to answer 2 research questions. Does the redisturbance threshold change over time? And if so, how reliably and efficiently can we measure it? And second, we would like to analyze implications of temporal variation of redisturbance for redisturbance solutions. So to achieve our goals, we experimentally characterize DRAM chips. You've seen this many times. We use the DRAM vendor testing infrastructure to test DDR4 modules. This infrastructure provides us with fine-grained control over DRAM command, timing parameters, and temperature. And we have also another version of the same infrastructure that we use to test high bandwidth memory chips. We test many chips from 3 major manufacturers, spanning various die densities, die divisions, and chip organizations that you see here. And we carefully reuse the rigorous redisturbance characterization methodology as done by prior work, where we prevent sources of interference and use the worst case double-sided RowHammer redisturbance access patterns. And the bottom figure here depicts one hammer. So opening and closing, you see it here, yes. Opening and closing the 2 neighbors of a victim row constitutes one hammer, at least the way we define it in this work. So I'll describe the major results, starting with this key takeaway message. So we find that the redisturbance threshold of a row changes randomly and unpredictably over time, and this makes accurately identifying the redisturbance threshold very challenging. This is the most important fundamental result we have. So we plot the redisturbance threshold values observed across many redisturbance threshold measurements, or samples or observations. Basically, as measurement numbers increase, we go forward in time, per se. And this is an example point in the plot describing a measurement that yields a redisturbance threshold value of 37,000-ish hammers. This is real data, by the way. This is RDT measurements, 5 of them, across time. And this is across 1,000 measurements. We will expand the x-axis further, and we want to make sense out of this plot. So we compress those series of 1,000 measurements into this form, this box. This circle shows the average across 1,000, and the error bars show the range of values in those 1,000 measurements. Now, this is the redisturbance threshold across 100,000 measurements for one DRAM row that we tested. We tested many of them. This is just one of them. And we observe that for this series of redisturbance threshold measurements, the minimum RDT appears at around 17,000 measurements. That's like 4 or 5 days into repeatedly testing this row. So this, we believe, is a key result that demonstrates the variable redisturbance phenomenon. And we also investigate the distribution of observed redisturbance threshold values. Here we show a histogram of the RDT values where the bar's height indicates the number of measurements that yield the RDT value you see on the x-axis. And we observe that the redisturbance threshold of a row takes various different values across 100,000 measurements. And we show data for one tested row in each of 6 tested DRAM chips here, so 6 different rows here. And this observation is consistent across all tested chips. We have similar looking distributions to what I show you here, but I don't put all of those plots in the slide, so I refer you to our paper for those, but I'll be happy to take questions also. We have one question there. We have one hypothesis. I need to go to slide number 300 something. I'm going there. No. 12 p.m., 12 a.m.
And then p.m.
And then p.m. So it's a bit difficult because this has not been shown before by device level studies, like the underlying physical phenomenon. We have a hypothesis explaining that. And again, I'm not sure if I'll be able to explain this very scientifically, but these bullets summarize it. So electron migration and injection into a victim cell is one major mechanism, underlying physical mechanism. And it's assisted by charge traps in the active region. So charge traps apparently, or hypothetically, change their states. So it's the state of the charge traps, like the distribution of the states of charge traps affect, let's say, the amount of charge leaked by one hammer or one press. And those state changes happen randomly, physically randomly happen. Yeah. So that's the best hypothesis we have. If you know about variable retention time, whereby retention time of cells also vary randomly, unpredictably over time, this hypothesis is very similar to the underlying physical phenomena that explains VRT. Yes, one question.
So you showed this RDT plot for over 100K measurements for a single row, right?
Yes.
And the RDT values in the beginning were high. They followed the high pattern and then they got lowered basically.
Yeah.
And I was wondering, is it safe to assume that each one of these measurements are totally independent and nothing carries over from one measurement to another? So row refreshes actually reset everything.
Yeah, I mean, it should, as far as we know. So nothing is carried over from one iteration to the other, or nothing different is carried over, let's say.
So these two patterns don't mean much then, right? So there wouldn't be...
In what sense?
Like at large scale, over 100K measurements, we couldn't say there is some degradation, for instance, like physically happening.
Yeah, so basically the redistribution threshold could go back up again, like the mean, the reduction in mean you see here is not permanent.
Oh, okay.
I can say that there's other data that shows that.
Okay.
So there seems to be, at least from what we see in this paper, and we're still working on this, right? We're doing more experiments. But what we had with the data in that paper, there seemed to be some sort of, let's say this is broken down into two effects that we don't know. One effect causes these large swings in the mean of or the whole distribution, like this jump from here to here. And there's another thing that causes this noise. Both are seemingly unpredictable, but these big jumps, we don't have much data on these jumps because it just takes too long to get. Yeah.
So it's a large scale effect that can be observed over a lot of measurements. Basically.
Yeah.
I see.
Do you have any other questions? Yeah.
Is there any chance that this is periodic by any way?
So the smaller ones are definitely not. Well, definitely not would be an overclaim. We did try to study, like we did a a simple time series analysis for the predictability of these values. So we use the autocorrelation function, which would give you so the zero values here, see here, these would not be zero, let me put it that way, if there was some overlap between shifted series of RDT measurements. So like you take 100,000 measurements, and then you shift that measurement by 1 to the left, let's say, to see if there's an overlap, and then by 2, by 3, by 4, all the way up to 25,000. And there's no correlation as far as this says. Yeah. The bigger ones, maybe. Yeah.
You previously stated that you saw, for example, a specific threshold being reached after 47,000 accesses. 94,000 even. So this sort of periodic behavior or this time behavior may be way more, way bigger than the sort of shifting by 25,000 accesses.
Yeah, I mean, sure. Like the bigger ones, yes, I agree. I mean, this is the problem. There is, even if there's some sort of repetition, we didn't see it in the like you would be able to tell by eye. Like, okay, maybe it's an overclaim, but listen to me first. I'll explain myself. So these big shifts don't happen much. So if you plot them like this, if there's some sort of repetition, you should be able to see and figure it out.
Yeah, but I suppose even if there is a periodic behavior, it is so unpredictable in between that maybe you cannot have a very accurate estimate.
Yeah, but these shifts don't happen much. It's like this is one row. I have data for 20, I think 21 rows like this, one with 100,000 measurements. So we didn't test many rows with 100,000 measurements in this study, just 20 or so of them, one row in each chip basically. And these big shifts either don't happen too much, as in zero, such big shifts, or it happens once. And then
they may not be related to themselves, but is there another feature that sort of points to them?
Well, everything else across these iterations are the same, unless someone breaks into the lab and does something in the lab.
I think.
Yeah. We have another question there. By the way, when I'm looking at this part of the room, I don't see this part. So if you have a question, please let me know. So if it's blinking, it means it needs time to, And then like there's some sort of calibration going on. Like when you shake it too much or you, move the microphone, it goes out of sync.
So one question I had was, how long of testing? You said it was about 2 weeks of testing to get to the least RDT measurement. Was this continuous testing over 2 weeks?
Yeah.
Like all
nothing
the time?
else, just this row.
Okay. Because then that's very prohibitive to explore. You can't do something online then, right?
Yeah, it is. It's one of the points of the paper.
Yep.
You probably don't want to measure register threshold for 100,000 times. I mean, you bought the DRAM chip for some purpose. other than testing. It's the main dichotomy, I think. Okay. We have one question there, one question there.
All right. So I was wondering, you don't see that jump in the minimum observed values, right? There's kind of this consistent interval. So I was asking, what does knowing the exact RDT tell you that the minimum RDT doesn't already tell you? Isn't it like intuitively or naively, like doesn't it already seem very suspicious that a victim row has two neighboring rows and they both have are hammered 34,000 times and at the same frequency probably? Like, I don't know. Wouldn't we already, like, is it easy to mistake legitimate memory access for the minimum cases, like the 34,000 hammers?
Maybe I didn't understand your question actually. Can you maybe rephrase it a bit?
Yeah, I'm sorry. So we are trying to detect whether something is, using the disturbance threshold, we're trying to detect whether something is an attack or not, right? Or like we're trying to see how this value, when a row being accessed is prone to bit flips or not, right?
Yeah, so basically, if you look at this, I think you could say, the moment you see this value, set your defenses to be triggered, but you don't know if that value is smallest yet. And that's the whole point. If you think about it, without understanding this variation, we cannot really make any judgment. Even with a lot of analysis, we still cannot make a judgment about the absolute minimum redisturbance threshold value a row will ever have. So I cannot say confidently that this value will be the smallest one observed across 1 billion iterations.
So is 34,000 hammers something out of the ordinary for like a normal program, or does it happen that a normal computer program can have like this many accesses this quickly?
Yeah, it could have it. I guess we don't do this sort of analysis in this paper, like how many times your program ends up activating an aggressor row. 34,000 is definitely within spec. So you can do 1.4, I might be wrong, between 1.2 and 1.4 million activations in a refresh window before your victim is refreshed. So basically you can do up to this could go up to 1.4 million, and then you could call it standard operation.
Okay, well.
You want to add something?
So I'd like to rephrase the question in a different way. Maybe I'm going to manipulate it a little bit.
Wait, are you done with your question? Okay.
So what if, okay, let's phrase the question this way. So you observe a lot of variation in RDT, but the mean value is around like 34, 36, 35,000 activations.
Min or mean?
Doesn't matter. Like on average, like it's in the span, like from 32,000 to 40,000 is the range, right?
Yeah.
So what if we configure our RowHammer defense to work at 1,000 activations? So do we really care what kind of variation we observe here?
Yeah, I'll get to that actually, but maybe get to that faster. You can use, what you're saying is basically let's use some safety margin at this point, right? Like we characterize our DRAM chip, we didn't find any values smaller than 10,000. And I'm willing to use a value as small as 1,000.
Yeah, also he mentioned the behavior of the benign workloads, right? So let's say benign workloads, if they don't hammer more than 1,000 times, what if we just set the defense to 2,000 or something like that?
Well, you can set the defense to 2,000 is still good. Like, okay, I won't make scientific claims. I will just say, based on experience and reading a lot of papers, 2,000 RowHammer threshold is something you can deal with relatively efficiently today. So if you talk about specific numbers like this, I would say go ahead, do it. And, like in the end, you would still not know if you're going to have a value smaller than that. You cannot say that, I think, based on what we show, that you will never have a value smaller than 2K for any row you test. And if you go look at the scaling of redisturbance bit flips, you'll see that the redisturbance threshold keeps getting lower and lower. At some point, you will have to hit with that safety margin even smaller thresholds. So maybe today's DDR5 chips, which are unfortunately not tested for redisturbance threshold like this rigorously because of a lack of testing infrastructure, we don't really know their redisturbance threshold values. There's certainly higher density chips, and we expect RowHammer to be worse in those chips. So if you apply the same method of adding a safety margin, you might end up with a very low redisturbance threshold value. And at that point, your overheads are considerably high for defenses. So we show this. We look at a bunch of defense mechanisms. These are different defense mechanisms: graphene, PRAC, PARA, and MINT. We see that the 50% RDT margin, which you were talking about, the 10x margin, right? 500% margin. Even a 50% margin at low enough threshold can induce 50% overhead, system performance overhead. This is overhead from preventive refreshes. So your activation count reaches a threshold and you refresh the victim rows. And this is the overhead you pay due to interference with demand requests. So if you rigorously test your, maybe you test your chip for 30 days and you found 10,000 to be the smallest redisturbance threshold, you can apply a 5x guard band, and you can take my word for it that you won't have that 2K RDT value appear after that much testing, but I wouldn't take my word for it. I would do my own study. It's complicated, I think. There's no certain answer. With some input from manufacturers and maybe fabs, we can know better. We can actually understand the physical phenomena that lead to these and model them. But the DRAM industry is not really open to that sort of thing. So we're left with doing these sort of tests. That's a very long answer, but I hope it was coherent. So if you have any questions about that answer, I'll be happy to take them. Cool. One more question over there. So we're taking this to 12 a.m.
So you said if the threshold is too low, the performance overhead will be unnecessarily high. Who pays that overhead? Is it the victim or the aggressor?
Who determines the overhead, you said? Or?
Well, this overhead is for which application? The aggressor application or the victim application?
Well, these for victims. We don't have any. So in this study, the numbers I showed you, they don't have any application that's trying to do RowHammer. All of them are just basically memory traces from spec workloads and other benchmark fits, benign workloads, benign workload mixes. But the thresholds there are low.
And following up on his question, so if you set your threshold to 5,000 and benign applications never reach that threshold, so you don't have any performance overhead. Is that correct?
In that scenario, yes. If that were to be the case, yes. Until you have some aggressors. Well, like basically there's a line of work that shows RowHammer defenses can also be used as sort of agents for denial of service. You can create interference even if you cannot create bit flips. You can have the defense mechanism perform a lot of time-taking refresh operations. Yeah, but at 5,000 RowHammer threshold, the intensity will be low. At 200, very high. Harsh has a question.
Yeah. So back to your slide with 100K measurements.
Yeah. This also has 100K.
Yeah. So let's say I'm limited in terms of time and compute resources or something like that, and I could only do 10K measurements, and I do not capture the global minimum, right? The absolute minimum RDT in that case. can I then like not basically offload that to ECC or something else and get away with small overheads for correction?
We looked at that also. Like here, you could do that, I guess. Like find the minimum after 10K, you already hit the minimum. This specific example, yes, but specific examples maybe are misleading us at this point because we haven't even looked at 99% of the data I was going to show you guys. He's still questioning me in the 61st slide. We have like 200 more slides to present. Anyways, ECC can correct some of these errors, yes. In fact, I mean, from our experimental data, okay, is this what I want to show you? Where is it? Here. Okay. We tested with a 10% guard band, which is relatively small. So what we did is we measured the redisturbance threshold 5 times for a row. This is this is across many rows. I don't know the exact number at this point. And we find the minimum across those 5 measurements. And then we apply a 10% guard band. So if we found 5,000 there, we apply a 10% guard band. So that brings us to 4,500. And we repeatedly test for 4,500 hammers for a very long time. Again, I don't have the exact number of times here. And we collected this histogram. This shows you basically the number of unique bit flips in a row, even after applying that 10% guard band. So you see a lot of rows with 1 bit flips that can be corrected by ECC, no doubt. 2 and more depends on where the bit flips happen. So if you have 2 bit flips happen in the same ECC code word, most frequently used ECC can only detect it, definitely not correct it. If it's in the same chip, chip kill can correct up to n bit flips. Chip kill can basically correct the disappearance of 1 chip in like among, let's say, 9 chips. It's like that level of redundancy. But these bit flips happen across chips, so you can reason about that. So short answer is ECC is still not, I would say, a reliable solution for redisturbance bit flips, even when you apply guard bands. Harsh, yes.
Oh, I don't want to take too much time. In case you're going to discuss profiling approaches or directions, then I will delay my question.
Profiling
in the context of RDT. I mean, variable redisturbance and RDT.
You mean like how we find
how can we find potential directions? Maybe.
I think how can we find is like my next research paper, hopefully.
Then we don't talk about it. I will talk to you in person.
The good question I think to ask is, we're looking at the whole population of rows in this study, but what about the ones that have already the smallest redisturbance threshold values? So that's the next thing.
I think one question I could ask about the characterization is, do you see similar results across like consistent results, correlated results across chips, the same die revision?
That's a good question. Probably no. Let me just try to remember. Same die revision does not show similarity. But we have this observation. It tends to worsen. You will understand this better when I...
I'm sorry again. Yeah.
We'll wait more. Yeah. But this shows you basically with increasing die density and advancing or advanced DRAM technology nodes, hypothetically, there's something to be taken with a grain of salt there because we cannot be 100% sure from information available to us which module is more advanced than the other. But we know which is higher density than the other. So with higher density and advanced technology, the distribution tends to worsen.
The gap I wasn't going along that direction. I was asking questions about one specific die revision. Do you see consistent results across different chips? Different chips meaning different instances of these chips.
Yeah. We don't have. I don't have that in the study. No.
Sorry,
yeah. Yes. I think we were here. No. we were here. Okay. We have another question. Perfect. Data pattern.
Yes. What is the data pattern for the rest of the rows other than the ones explored? Is it zero? Is it zero?
In this one, well, honestly, you're asking me a good question. I don't have it right now off the top of my head.
Okay.
For this data, I don't remember. I mean, for data I'm going to show you next, we have the methodology slide. So I can only try to remember. So these are the data patterns we tested, right? But the ones I've shown you so far, it's definitely in the paper. It's either one of these.
For the rest of the rows, it's one of
so
these.
Basically, this is showing you that.
Oh, yeah.
We don't initialize all of the rows with every test, like every experiment.
Yeah.
We initialize the neighboring 8 rows. So victim row, 4 rows above the victim row, 4 rows below the victim row in logical ladder space, with these data patterns. And the data I've shown you uses either one of these. I don't know which one.
Okay.
Okay, no hands. Yeah. I already described this a bit, but we analyzed the predictability of the next redisturbance threshold value given a sequence of past measurements. We find that this is likely unpredictable. We did 2 things. First, we look at the histograms, the distributions of these values, and they resemble prominent random probability distributions. So some underlying phenomena yields this. Some randomly distributed phenomena yields this, right? That's one thing that hints this could be unpredictable. And we use the other correlation function I've shown you earlier to try and identify repeating patterns, but we cannot distinguish any repeated patterns. So yeah, I mean, for more details, please read the paper, or we can discuss offline, but with the paper next to me. I cannot give you any more than what I gave you in the in the question earlier at this point. Okay. Yeah. So we will take an in-depth look at VRD, and we will look at many DRAM rows, and we will sweep many test parameters. So that was just one row and under one test condition. So we use 4 data patterns here, 3 temperature levels, and 3 different aggressor of one-time values to investigate RowPress and variable redisturbance. And we test many rows in total across all chips, but we measure the redisturbance threshold 1,000 times for each test row. So something had to reduce. So that's the number of measurements. And this is due to time constraints, really. And yeah, I have here an aside how long it would take and what the distributions would look like if we were to test for more than 1 million times. It's good to think about as I present you the results. So these are the 3 key takeaways from this in-depth component of the study. First is that all DRAM rows exhibit variable redisturbance. So to different degrees, but there was no row that was not subject to variable redisturbance. So here we show the coefficient of variation in the distribution of 1,000 redisturbance threshold measurements of each tested row. I'll explain what this means. So this circled tiny pink dot, you cannot probably see it if you're too far back, stands for the DRAM row with the smallest coefficient of variation in its distribution. And that means, for the purpose of this talk, that can mean basically its redisturbance threshold values are very close to each other. So the distribution is kind of small. And we show the rows sorted in increasing coefficient of variation on the x-axis. And this is the whole distribution. We observe that all tested rows exhibit VRD. No row has 0 variation in its redisturbance threshold measurements. And we highlight 2 points in this plot, the median row and the row with the greatest variance in its redisturbance threshold distribution. So this is looking at those 2 rows, but we've expanded on measurements on the x-axis. So these are 1,000 successive measurements. And for the median row, this is the one on the left, we see that the maximum observed redisturbance threshold is 1.2 times higher than the minimum. And for the other row, the row with the greatest variation, it can reach a relatively high factor, that's 3.5 times. So the biggest or the largest redisturbance threshold observed for that row is 3.5x, the smallest observed for that row. And do you have any questions? Oh. Okay, cool. So that's a big number, a big variation. The second takeaway is that relatively few measurements are unlikely to yield the minimum redisturbance threshold of a row. And here we're trying to answer this question. So how likely is it for us to find the minimum observed redisturbance threshold across 1,000 measurements using only n measurements where n is smaller than 1,000? We use Monte Carlo simulations and plot the probability of identifying the minimum redisturbance threshold value over varying n for all tested rows. So n equals 1 measurement here has a very low probability of yielding the minimum redisturbance threshold value across 1,000 measurements. It's only 0.2%. And we observe that this probability increases with n. It goes up to 75% for the median row, but it does not reach 100%, again, for the median row, even for n equals 500 measurements. So this is one major result. Again, I would, if you have any thoughts, I'll take a stop. Okay, no, cool. And to gain more insight into variable redisturbance, we devise another metric, and this is called the expected value of the minimum redisturbance threshold. It's to quantify how higher of an RDT value we expect to find with n smaller than 1,000 measurements. So I'll describe this pictorially. This line depicts the minimum redisturbance threshold value across 1,000 measurements. And these are 5 random samples from the set of 1,000 measurements, and the minimum across those. And the metric we're devising here quantifies the distance between these two minimums. And these 5 samples are taken randomly, right? And the number will change also, vary, that's n. So we plot this new metric on the y-axis and the probability of finding the minimum RDT on the x-axis, that's the previous metric. Each point on this plot stands for one DRAM row. And this point is showing you that there is a row where we expect to find a redisturbance threshold value using one measurement, and that value will be 3.2 times greater than the one we would find if we were to test for 1,000 times. Okay, it went a bit too fast. So a good way to interpret this plot then, based on that, is that we want to have a small y-axis value. Small y-axis values indicate tighter redisturbance threshold distributions. And you want your distribution to be as tight as possible if you want to, I don't want to use the word predict, but at least predict what the lowest value, or based on one measurement, you can predict that the smallest expected value will be not so far away. So we want something like that. So this is the full plot. And we highlight the rows with smaller than 0.1% probability of finding the minimum RDT. These rows, for these rows, the minimum redisturbance threshold value appears only once in the series of 1,000 measurements. And they can have up to 1.9 times expected normalized value of the minimum RDT. So very wide distribution, and the minimum appears only once in a series of 1,000 measurements. And we conclude that the minimum redisturbance threshold across 1,000 measurements is significantly smaller than the one expected to be found by n equals 1 measurement. And with increasing n, we expect to identify a redisturbance threshold value that's closer to the minimum value across 1,000 measurements. So these blue dots show you the new devised metric for n equals 500 measurements. And finally, data patterns, temperature, aggressor at one time all affect VRD. And I think I'll go over them relatively quickly because we discussed some of these already. Yes. Not this slide. Should I go a bit? Yes. This analysis does not, I think, cannot answer that question. We cannot answer that question without testing 1 billion times. I mean, you could say something about, basically, I've seen that the distribution for this row looks like, the reducer threshold looks like this, like imagine something. You could say that that distribution will remain, and based on that distribution, you could make some statistical inferences, but that distribution seems to shift, and it seems to happen rather unpredictably and more wildly and less frequently, which is terrible. Yeah. We can come up with models that will have some predictable capability, yeah, prediction capabilities. But I'm trying to do this actually, right, as part of my next work. But it's terribly difficult to basically answer a question like that. I honestly, at this point, I don't know how you would answer that question. Like, I have a model based on n measurements. How accurate is that moving forward? Like, you gotta keep probably testing and update your model. Yeah, yeah. Yeah. We have to go forward, not back. Mm-hmm. From 50 to 500, I mean, I didn't look at intermediate points, so I wouldn't be able to say, but the jump from 10 to 50 is 5x. The jump from 50 to 500 is a numerical value is 10x, so it's like, yeah, so I don't think the median jumps by 10x. No, there's no way. Well, there's some way, but it's unlikely. So this is not completely unexpected. I see. So I cannot answer that question right now confidently. Very good. Oh. So that maybe it has a straightforward answer. Maybe others can see the answer at this point. But I can't. Yeah. I'll rather do some.
Yeah, it may be good to do that analysis.
Yeah, do some analysis.
Okay, cool. Now we can move forward.
Yeah.
Unless someone has a question.
No hands. Oh, yeah, I went too far. There you go. So some observations about data parent aggressor one-time temperature. So we show the expected normalized value of the minimum RDT. That's the second metric we devised. For 4 tested data parents. And we observe that the distribution changes with the data parent. Here we show the median values to quantify that change. So there's some, the data parent has some effect on VRD distributions. And across all tested modules and manufacturers, there is some effect, and no single data parent causes the worst distribution according to this analysis, across all tested DRAM chips. So some data patterns tend to yield the worst distributions in some DIMMs or some chips, some others in some other chips. Here we show the effect of aggressor on time. We see that the distribution, the RDT distribution changes with aggressor on time. Again, a rather straightforward observation. It can become worse or better with increasing row on time. There is no single relationship that we could identify. So you can see that in some cases it has a reducing effect. In some other cases, it's some sort of increasing the redisturbed threshold distribution. And you look at the effect of temperature as well, but we don't investigate it too much because from a simple look, the distribution tends to change with temperature, but there's no clear relationship again. So these are the sort of three takeaways from the sensitivity study. And I want to show you this also. I kind of highlighted this earlier, but here we look at the effect of dye density and dye revision. We plot again the same metric over the y-axis. Here we show 3 different dye revisions and dye density combinations. And we observe that the redisturbed threshold distribution worsens with increasing dye density. So when I say distribution worsen, it means that we expect to find a larger redisturbed threshold with less than n smaller than 1,000 measurements. And we consistently make this observation across all tested modules. So the distribution is becoming worse as dye density node technology advances, manufacturing node technology advances. The RDT distributions worsen. Okay, that's all about the sort of experimental study component of VRD. Like that's all about redisturbed threshold values themselves. Now we'll move on to the implications we thought were important for system security and robustness, implications of variable redisturbance. So I'll summarize these. Security guarantees provided by defenses or redisturbance mitigation techniques rely on accurately identified redisturbance threshold value. And we show that accurately identifying these values is extremely challenging. And we evaluate a short-term solution that is to combine a guard mount for redisturbance threshold with error correcting codes. And given our limited empirical bit flip data set, we show that this combination could prevent VRD-induced bit flips at some performance cost, non-negligible performance cost. And our results call for future work. We think that it calls for future work on online redisturbance profiling and runtime configurable redisturbance mechanisms. And we will hopefully motivate that in the next slides. I'll again stress an important caveat. The results I presented in this last slide, and I'm going to present in the next slides, are based on only a limited number of redisturbance threshold measurements. And I think you can be pessimistic about this and say that more redisturbance threshold measurements could yield worse results. And it's good to think about what millions of or billions of or more redisturbance threshold measurements could yield. And that was the summary. So let's dive a bit deeper and explain why it's difficult to identify the minimum redisturbance threshold value. The variation in redisturbance threshold can reach 3.5x and may not be bounded. This variation is not guaranteed to be bounded. The distribution in redisturbance threshold values is affected by many parameters, and comprehensively testing for redisturbance threshold values is time intensive. And one number to quantify that, basically if you want to test the redisturbance threshold of each row in a bank of 256K rows, only once, it can take 39 minutes, and you have 32 banks in a DDR5 module. So testing all rows once already takes hours. And in fact, we show that if you want to be even more comprehensive, testing a DRAM chip can take tens of hours if you want to measure the redisturbance threshold multiple times, but only under one test parameter set. And in the paper, we have a much more comprehensive analysis for testing times. So I refer you to that if you want to see some very large numbers, like years. Yeah. Because it's so time-consuming to comprehensively test for disturbance bit flips, you as a system designer might measure the redisturbance threshold a few times and then take the minimum across those measurements and then apply a guard band with hopes of covering the absolute minimum across eternity redisturbance threshold value. So this plot shows you the probability that n measurements displayed on the x-axis plus the guard band we show above will cover the minimum redisturbance threshold value across 1,000 measurements. So we show both the average value across all tested rows, those are the circles, and the minimum across all tested rows, that's the bar. It's a bit of a different plot, but hopefully this is easy to understand. So the pink bar, what it means is that there is a row where you don't expect to find the minimum redisturbance threshold across 1,000 measurements with 100% probability, even with 500 measurements. So this is the full plot. And we observe that a large guard band does not guarantee that you will identify the minimum redisturbance threshold value, or identify as in the minimum redisturbance threshold value will not appear in within the guard band you applied. So we conclude that guard bands alone are likely not effective, right? Because some redisturbance threshold values might escape. You could say that I will increase the guard band even further, but 50% guard band is quite large already, right? Again, if you say that you want to increase the guard band even further, this is another reason why you probably shouldn't do it. Large guard bands can introduce significant performance overhead. With the previous reason combined with this reason, we don't recommend using guard bands alone. And we evaluate error correcting codes as a complementary technique to using a guard band for redisturbance threshold. And I've described this already, so I'll take questions if you have any. But the bit flip rate we observe suggests that widely used ECC schemes, relatively cheap ECC schemes today, with 10% guard band for redisturbance threshold is likely unsafe. And that depends on how the bit flips are located in the end. Using a guard band of 20% or larger than 20% yield only one unique bit flip in the row. And the bit flip patterns we observe could be prevented with larger than or equal to 20% guard band combined with these ECC schemes used today. But we think that more detailed analysis, likely following a large-scale study, is needed to make a definitive conclusion about the effectiveness of guard bands in ECC. And I could potentially disclose that, like, with further testing after the publication of this paper, I wouldn't trust the 20% guard band so much anymore. Yeah. It's all about, I think, how long you allocate to testing. Yes.
And how much of guard band do you trust?
Right now, 30. I bumped it up to 30%.
Okay.
It might change tomorrow. It could be 40. I don't know.
As you test more and more, guard bands should go up higher and higher.
It looks like that. So the 20%. So this was limited testing, right? So we, I think, we did this in the rebuttal timeframe. So we submitted a paper with field reviews. This was one of the things we wanted to address. We tested for a week, less than a week or so. We did this ECC experiment then, basically, in a short time window. And in that short time window, we couldn't apparently cover all the bit flips we could have possibly covered, which is reasonable, and which will increase, I think, with more testing.
Doing more testing now?
Yes.
As we speak?
Yes.
Okay.
Should I not?
No, it's good to do more testing.
You know?
So how do you know that the new bit flips you get are not due to some other effect?
Some other effect, as in like, I cannot think of any other effect right now.
I don't know, some sort of aging.
Well, aging is always a. I think aging, something should have, like, we should have something about aging now, because it's difficult for me to reason about aging.
Yeah.
There's no redisturbance, like there's no work that shows how redisturbance would behave with aging. So I cannot really make any scientific comments on that.
Yeah.
I think.
But that's true for that is true for VRD also at the low levels.
Yeah, it could be. Yeah. One thing I could say is if the research threshold value reduces to some value and goes back up again, maybe that's not exact. You could say that that's not aging.
Mm-hmm.
You could also say that that's aging.
Yeah.
I don't know what to say about aging.
Is that what's happening in all of the cells that you keep testing?
So I've not seen so far something that permanently have a reduced redisturbance threshold. It's more like variable retention time, really. Cells seem to have multiple states that they can be in, and we don't know how they choose to be in one state or another. Yeah.
Okay. I think that's great to keep testing. It's good to see what happens. And it's good to update also to the numbers in the paper.
Yeah, we definitely get
as
back
we
to
get more data.
Yeah. Furkan, yes.
So you said there is not a permanent trend at large scale swings, right? But you also mentioned a second swing that's more local within those higher level trends.
Yeah.
This smaller swings within segments, let's say.
Yeah.
So do you see a like permanent trend over there? Are those local swings getting more noisy, for instance?
I haven't looked at it in so much detail. The visual inspection, no. Maybe some significant change happens, but I cannot see visually by inspecting the distributions.
Okay.
But I haven't looked. I haven't thrown statistics at it for this specific problem. One more question.
So, have you heard about this paper called Avatar, who got the Test of Time Award for the retention time? So, can we apply a similar solution here? Let's say we have a more capable error correctness scheme. Maybe we can even use message authentication codes like CSI RowHammer, and then whenever we see bit error rate increasing, we can increase guard bands. So have you looked into that?
You can do this. Yeah, I think multiple people are looking into it, so I don't recommend more people to look into it.
Okay.
I mean, people can, of course, look into whatever they want to look into. Yeah, but the idea is, should I describe it? I don't know if I should. You just described it, so makes sense, yes. The issue is there's not enough experimental data, I think, yet, which is something we could close, like a gap we could close, yes. Because you don't know if, like I've shown you this, that you could do something with this data. But then I told you, like, okay, this seems to be outdated, right? So I think that sort of a study needs to really have a lot of experimental data backing it up. What we presented in VRD might not be enough for that. Okay. There are other things in the paper that I didn't cover. Like, I covered the hypothetical explanation to some extent. We also look at the effect of true anti-cell layout, and we didn't observe a significant effect from the presence of true versus anti-cells, at least in one module. so we don't conclude anything. It's just a preliminary study. But it looks like there might not be an effect. Redistribution mitigation evaluation methodology, probability of errors at the worst observed bit flip rate. We have a error rate estimate based on our empirical data that shows you how likely uncorrectable errors are to happen. For example, if you use SecDed and so on. And more data on redisturbance testing time and energy consumption. These are in the extended version in archive, not in the conference publication. This specifically the fifth bullet, and some more detailed information on test modules and chips. So you can find those details in the paper. And I'll conclude VRD. So we demonstrated variable redisturbance, showing that the redisturbance threshold of a DRAM row changes unpredictably or across over time. We show VRD's interesting characteristics through detailed experimental characterization. And VRD has implications for system robustness and security. First, we evaluate short-term solutions against VRD. Given our limited bit flip data set, relatively large guard bands and ECC may prevent VRD-induced failures, but we think there's more data and analyses needed to make a definitive conclusion. And we're working on that, I would say. So we call for future work on efficient solutions for VRD and future work that will develop our understanding of the inner workings of variable redisturbance and redisturbance in general. An extended version of the paper is on archive. And that's it for VRD. So if you have any sort of questions about VRD, you can take them again now. Later is also fine. It's 3 p.m. Do we have anything scheduled now? Like the coffee break? I don't know when the coffee break is.
Coffee is out there.
So maybe we can go there then.
And then come back.
When we come back, you will cover what?
Redisturbance in high bandwidth memory, abacus, and self-managing DRAM.
Very good.
Or maybe a selection of those three.
I think it's a good time for coffee break.
Yes. So we will be back in 15 minutes. 3:15. 30 minutes.
Up to you guys. Okay.
20?
I can okay, 20.
20.
So we'll be back
2.5.
We'll be back in 2.5, no, 20 minutes.
That sounds like VRD. Variable time determination, VTD.
How do we share the whiteboard again? Oh no. Oh no, again. on YouTube. Is it fine? Okay, I'll continue. So the next part of this talk is I'll be covering read disturbance in high bandwidth memory, a detailed experimental study on HBM2 DRAM chips. And this was published in Dependable Systems and Network Conference in 2024. So introducing this work in a different way, this is a non-exhaustive list of back then recent work that demonstrated read disturbance bit flips in commodity DRAM chips on a timeline not to scale. And many LPDDR4 and DDR-X chips, old and new, are vulnerable to read disturbance bit flips. In our work, we ask and answer, what about read disturbance in new high bandwidth memory DRAM? Does read disturbance exist in high bandwidth memory? And if so, how does it look like in high bandwidth memory? So our goal is to experimentally analyze how vulnerable modern high bandwidth memory chips are to RowHammer or read disturbance. And therefore, we experimentally characterize 6 HBM2 DRAM chips in 2 different FPGA boards. These are the 4 key results from the 23 new observations we make in the paper. We see that the read disturbance vulnerability varies across 3D stacked channels and DRAM rows in each channel in high bandwidth memory. On average, across all tested DRAM rows, you may induce 10-bit flips with an activation count fewer than twice the activation count needed to induce the first bit flip. And this will make more sense as I describe it to you in more detail. We show that RowPress is widespread across the tested HBM2 DRAM chips, and we completely uncover the inner workings of an undisclosed on-DRAM die RowHammer mitigation technique in one of the tested chips. We draw several implications for read disturbance attacks and mitigations, and we hope that our work inspires and aids future works. And all data and sources for this work are open sourced at the link below. So this is the outline for the second part of my talk. I'll give you a short background on high bandwidth memory DRAM specifically. So we already know about DRAM, but HBM is a bit different. High bandwidth memory chips are exhaustively used or extensively used in important system infrastructure of today. You may know some examples to these. Several popular machine learning applications of today rely on high bandwidth memory systems. And a typical high bandwidth memory DRAM system consists of a compute chip and on multiple HBM2 chips. So I'll use HBM2 and high bandwidth memory interchangeably in this talk. So all of these chips are integrated into a single package to form the HBM2 system. This is a different view of the same system. The FPGA and the HBM chips, HBM2 chips in our case, reside in the same package and are connected by a silicon interposer. The memory controller in the FPGA communicates with the buffer die in the high bandwidth memory chip over the HBM interface. The HBM chip contains multiple 3D stacked DRAM dies, and each DRAM die contains one or multiple channels, and there are high-speed through silicon vias that connect the channels to the buffer die. So let's look at what's inside the channel, but you already know about this, so I'll skip this. This is a regular DRAM chip, basically, almost, with some small details, subtleties like pseudo channels, but that's not so important for this talk. So we'll look at a cell, its leakage and read disturbance in a bit more detail. I really like these slides. I'll go over them even though you already have the idea. But each cell encodes data in fundamentally leaky capacitors. This is a simplified diagram of a DRAM cell. The capacitor in red stores data, and the access transistor determines if the cell is being accessed. And the important thing here is basically stored data can become corrupted if too much charge leaks. That's to say the capacitor voltage degrades too much. So this is a simplified diagram of the capacitor voltage over time. We see that the voltage decreases over time in an exponential decay. like that. And there's a threshold Vmin, under which we can no longer guarantee that we will read the data that was originally stored in the cell. So as long as the cell's voltage remains above this line, this is a retention success. But if your voltage drops below Vmin, it's a failure. And in order to prevent those failures, we issue periodic refresh operations to make sure that the charge in the cell is restored. And we refer to the interval between these commands as the refresh window here. Although there's a bug in the slide that the correct term to use here will be refresh interval. So if you look at the same cell or the diagram in context of a redisturbance attack, if you issue enough activations to a nearby row, you can accelerate charge leakage to a point of failure before the next refresh operation is issued. So the moment, if you see here, by the time the refresh operation appears, it will read, quote unquote, read the incorrect value of the cell and restore that value back to the cell. So this is a bit flip, it shouldn't happen. And this is one way of looking at redisturbed bit flips. I think it's nice, that's why I wanted to cover it, even though you know already at this point all about redisturbance. So I'll introduce the testing methodology we used in our analysis, and surprise, surprise, it's DRAM Bender. We adapted it to work with HBM2 chips for the first time in this study. And we open sourced that at the link on the bottom. So this all DRAM Bender setups are open source. So to talk about this a bit more, this is an FPGA board that have an HBM2 chip, we control the heating pad and the cooling fan. This is the cooling fan, using an Arduino temperature controller to keep the main function of the temperature controller is to keep the temperature stable. And this setup gives us fine-grained control over DRAM commands. We can issue DRAM commands with as small a latency of 1.67 nanoseconds between each command. And I'll take some time at this point to describe DRAM Bender, like inject DRAM Bender into my talk. DRAM Bender is an extensible and versatile FPGA-based infrastructure to easily test state-of-the-art DRAM chips. I'll try to motivate DRAM Bender first. So there are many factors that affect DRAM reliability and latency, and we cannot properly model these. And we need to perform experimental studies of real DRAM chips to understand such phenomena. And there are open source DRAM testing infrastructures that allow us to conduct these experiments. They're publicly available and freely available, so you could start using these today. And they're relatively low cost. So you only need an FPGA board and a few DRAM modules, which is relatively cheap compared to doing this maybe in a specialized circuit using a specialized tester. However, they have several limitations that essentially make it difficult to use them as flexible, accessible, and extensible platforms. And DRAM Bender's goal is to overcome the limitations of prior testing infrastructures. It gives the user the ability to test any combination of DRAM commands and timing parameters. And it's very easy to use to conduct experiments on real DRAM chips because, I mean, one reason is we provide a simple C++ API that the user can construct their test programs with. And DRAM Bender's hardware design, which is not as popular as its software API, is actually modularly designed, and it's easy to extend to support different FPGA boards or different standards. So these are the prototypes that we support out of the box. We say 5 here, but I think the correct number is 6, and I always forget updating this slide. We have 6 out of the box FPGA prototypes. 2 of them are HBM2. 3 of them are DDR4, and 1 of them are DDR3. So in the paper, in DRAM Bender's paper, we evaluate DRAM Bender using 3 case studies, all to show that it supports many different types of experiments flexibly. But I mean, in the paper we had to do this, but I think DRAM Bender, like many other works, okay, I will cover them. So there have been many works that use DRAM Bender to uncover new phenomena or test real DRAM chips that speaks to the platform's flexibility itself in a better way, I think. So in the paper, we have more details about DRAM Bender design, its API, programmer interface, and the detailed results for the 3 case studies and some future works and improvements. And it enabled a lot of research, which I'm proud of. And it also, so it's not just us who did these, like this is basically an exhaustive list. Well, at this point, it's a non-exhaustive list because it's cut at 2024 of research papers that we use DRAM Bender in some way. And there are even more from other research groups that DRAM Bender and its prior versions enabled. Well, I would highlight RowPress, but RowPress already presented, so I'll skip that.
Is that list up to date?
This one?
Yeah.
Not sure. This one, for sure, it's not up to date.
Yes, okay. Well, the other one's probably not up to date either.
Yeah.
Okay.
Probably not.
Be good to update it.
Yeah, yeah. Yeah, so RowPress, you already know. I'm not gonna talk about RowPress. So in summary, DRAM Bender is the first publicly available DDR4 and HBM2 characterization infrastructure or testing infrastructure. It's flexible and easy to use, and it's available on GitHub. And we hope that it will continue to enable many studies and ideas and development of methodologies in the design of future memory systems. So that's it for DRAM Bender.
I'll make a comment, can I?
Yes.
I think it's great that you presented DRAM Bender because this and the predecessor, SoftMC,
yeah,
and its unnamed predecessor that we developed has enabled a lot of research,
yeah,
and a lot of discoveries. And this infrastructure, building this sort of infrastructure is extremely important to do cutting edge research. And unfortunately, this sort of infrastructure is not valued by these top conferences because DRAM Bender was submitted how many times to top venues? 3, 4?
3, 4 sounds reasonable.
3, 4 sounds reasonable.
But yeah, I mean, around that somewhere.
Yeah, people don't seem to find novelty in these infrastructures, even though they enable a lot of research.
Yeah,
I think this probably points to something wrong with the mindset of these top conferences. But I'm not asking a question. It's a comment.
I agree.
Yeah. There's a question maybe somewhere. Okay, go ahead.
Maybe wait because Rahul is halfway there. Yeah, Furkan has a mic, but I think we realized too late. Can you maybe wait a bit?
Okay. Yeah. So how do the other groups work on top of DRAM Bender? So if I understand correctly, it's like a hardware infrastructure, right? So how do you provide access to it? Or is it just like you open source the API and then they build the infrastructure and adhere to the API?
Yeah, so everything about DRAM Bender is open source. So you just need an FPGA board. Just is maybe underselling the requirement, but I would say it's easy to get into in terms of resources. Like it's an FPGA board, and once you have that FPGA board, you need a desktop machine which runs Vivado. And once you have that, you can download the GitHub repo and you can run a script. Literally, you don't need to do anything else. That will compile DRAM Bender for you if you're not satisfied with the pre-built downloadable bitstreams we provide. And then you can run your experiments. It's very easy to get into once you have the resources.
Thanks.
And the resources are $3-4K US, the cheapest one.
But you have to build like a similar infrastructure is the one we see on the slide, right?
Yeah, so for this one, the temperature controller is, I believe, not open sourced, the design. Also, maybe you know better. We don't open source the temperature controller component of DRAM, right? Yeah. No, not about novelty, but about like reproducibility. I mean, if someone's very interested in building the setup looking exactly like this, we would be happy to provide them with designs. Yeah.
There's some other groups that also use it. Your brand, they build their own template.
Yeah, it's not.
It's not super.
Yeah. Cheaper also than the board. Okay. So we'll continue with HBM redisturbance. I described this slide, so we'll continue. The testing methodology we use, again, is the methodology used by many other prior work for characterizing the redisturbance vulnerability in the DRAM chip. And it's the same methodology we use in VRD. So I won't describe this in detail again. We have two metrics. We measure two metrics. The first one is the bit error rate. It's the fraction of cells in a DRAM row that exhibit RowHammer or redisturbance bit flips. And for this, specifically, we use a hammer count of 256K. We say that the redisturbance vulnerability worsens as this metric becomes higher. So there are more bit flips in a row. And the second one is the minimum hammer count needed to induce the first bit flip in a row, in a victim row. And as this metric becomes smaller, it means that you need a shorter time to induce the first bit flip in a DRAM row. And we use the data patterns depicted in this table to initialize DRAM rows prior to performing RowHammer or redisturbance tests. So I'll explain how data gets laid out onto DRAM rows based on the first row stripe 0 data pattern. We fill the victim row with all zeros, the aggressors with all ones, and 7 other rows neighboring each aggressor row with all zeros again. So this is what happens when you change the data pattern from row stripe 0 to checkered 0. And we use these 4 data patterns, and we also determine a worst case data pattern for each DRAM row as the data pattern that causes the smallest HC first or smallest minimum hammer count needed to induce the first bit flip for that row. And this worst case data pattern is always one of these 4 tested data patterns. It's not something that you don't see here. It's either one of these 4. Sorry. So I'll show you the results of our characterization study, starting with an analysis of the spatial variation of redisturbance. We make 3 key takeaways from this component, this part of the study. First, different 3D stack channels exhibit different redisturbance vulnerability. Second, DRAM rows near the end and in the middle of a DRAM bank experience smaller bit error rate than other rows. And third, the activation count needed to induce the first bit flip changes with the data pattern and the physical location of the DRAM row. So I'll start with the first one. This figure depicts the bit error rate on the y-axis. These are distributions, bit error rate distributions across tested rows. And the data patterns we use on the x-axis. And different boxes show you the distribution in different channels. To make 2 observations from this, we see bit flips in every tested DRAM row in all tested channels, which is what you would expect to see at this point. And we see that the bit error rate varies across channels. And we identify groups of 2 channels highlighted here in different colors that have different bit error rates compared to other groups. This is a larger version of the figure that shows more data patterns. We see that the data pattern affects the bit error rate distribution. And we observe up to around 247 bit flips. That's the maximum number of bit flips we observed across all tested rows. In these rows are 8 kilobits. This is different from DDR4, DDR5. at 256K hammers. So this is a different version of the same figure that shows data from multiple chips. Using the worst, this time we're using the worst case data pattern. And we observe that the most vulnerable channel IDs are different across different chips. So in one chip, if you found the worst case hammer count, it's not necessarily you're going to find it in the same channel in the other chip. Yes. This one. Right. This one. Okay, he beat me to it.
So
let me see.
Do you want to show something? Oh.
I was gonna check what each data pattern actually is.
Okay, okay.
So, I mean, I can go back once you.
Yeah. So I just want to ask that, like, is the difference between the number of bit flips, let's say between the checkered and the row strip pattern, is it caused by the different numbers of zeros and ones in the victim row? Because, like, let's say if we hammer for sufficiently high amount of times, then like we will have more 1 to 0 to 0 to 1.
I think that could be the case, but for row stripe, either one of them, row stripe 0 or 1, you don't have ones, right? I don't know which one, but
okay,
it shouldn't be that the bit flip direction is the bit flip direction does not seem to explain this distribution. At least it's not straightforward to me.
I see. Yeah, maybe we can also discuss this in more detail offline. Yeah.
Because I mean, if the bit flip direction was in one way, then you wouldn't see bit flips in either row stripe 0 or 1.
No, so there should be both bit flip directions, but there should be more 1 to 0 than 0 to 1 if you hammer, let's say, for enough amount of times. Yeah, so let's say
but then we should see a bigger difference between row stripe 1 and 0, right? With that reasoning.
So what's the hammer count here?
256K.
So that's like,
and the minimum hammer count for these across everything I tested was 14K. So these are a bit resilient, I would say.
Wait, so for this test, the hammer count is 14?
256.
Okay.
256K.
And it's double-sided.
Double-sided.
Yeah, so it's like close to this 32 millisecond refresh window.
Yes.
Okay. It's a bit interesting because maybe that's another difference between DDR4 and HBM2, because like I would okay, let's say for row strip 1, I assume the victim has 1 and aggressor has 0. Is that the case?
Yes.
Seems like it. Okay. Yeah, the bit error rate isn't significantly higher than the 0 case.
Yeah.
I see. Yeah, maybe we discuss in more detail offline. Yeah, thank you.
So it seems like the data pattern has an effect in.
Yeah.
Okay, so 2 questions. The first question is there a fundamental explanation on why
Well,
this is the case? Or an intuition as to why?
There are some device level papers that show for a certain RowHammer or redisturbance access pattern, you would expect to see bit flips in one direction versus the other. And Hassan presented a paper that showed the discrepancies between that work and real life. So I wouldn't say we have a comprehensive explanation for all of these yet.
And the second question is, would it make a huge difference in the error rate? Would it be interesting to do a search essentially of data patterns that maximize, or would it make a huge difference if you had the specific data pattern, especially in the aggressor row, which can be controlled?
Yeah,
that would change this threshold a lot, and it would essentially go through the defenses that take variable refresh rate.
Yeah, I mean,
and could this be a case? Could this change?
I think you would want to look at HC first for that bit error rate. So it's for HC first. So this is now showing you the redisturbance threshold. Y-axis is redisturbance threshold, and different data patterns. If you look at the minimum values, I don't know if it's quite clear. They're about the same across different data patterns.
So it's not as likely to create an outlier that bypasses the defense.
Yes. Okay. But bit error rate is affected more significantly.
Yeah.
Data. No explanation. A lot of data. Well, some explanation. Okay, we've covered this. Any questions? Cannot see any. Okay. So this is a bigger picture of the previous plot, right? You have more data patterns and from more chips. So basically, we see that the bit error rate consistently varies across channels in each tested chip for each data pattern. Just to show that. We also look at variation in bit error rate from a different perspective. So this plot will show you the mean bit error rate and the variation in bit error rate across all rows in each tested bank. So as we go left on the x-axis, the variation in bit error rate decreases, meaning that the bit error rate of rows in the DRAM bank become closer to each other, So this is one example bank and where it resides on the plot. So we use different shapes to indicate which pseudo channel and different colors to indicate which channel and the bank which channel the bank comes from. So therefore, this point on this plot is in channel 6 and pseudo channel 1. So we plot 1 point for each bank in all channels and pseudo channels. So this is the complete plot. The first thing you see here is there are 2 clusters. But before that, we see that the banks in the same channel have similar variation in their bit error rates. So I highlight 2 different banks in the same channel as an example. And to visualize this observation, these are 2 different lines that show the distance between 2 banks from the same channel and 2 banks from different channels. So this one is from the same channel, different channels. So the points for banks in the same channel, again, are significantly closer to each other than banks in different channels. All that is to say is bit error rate varies similarly across banks in the same channel than across banks in different channels. Yeah. So I'll move on to the second takeaway, which the DRAM rows near the end and in the middle of a DRAM bank experience smaller bit error rate than others. So this plot shows the bit error rate on the y-axis and row addresses on the x-axis, and different lines show you the bit error rate for different channels. And as we go right, the row addresses increase such that the rightmost point in this figure corresponds to the last logical row address in the bank. And we display only the last 4 subarrays in this figure. And the dashed vertical lines indicate reverse engineered subarray boundaries. And this is the last subarray, basically, this red one. So this is a bigger figure that spans all rows in a bank in chip 1. We observe that the bit error rate is substantially smaller in the last and the middle subarrays compared to other subarrays. And we see that the bit error rate goes up and down as row addresses increase within each subarray. So the bit error rate is the highest in the middle of a subarray and lowest at either ends of the subarray. And we have some hypotheses that explain this, but I'll cover them later. So this is the same figure for all chips. So we observe this behavior in all chips. It's not coming from a single chip. It's not an outlier. Now I'll make the third takeaway very quickly. That's about the hammer count. So this plot shows the HC1 distribution. We covered this a bit, so I'll go a bit faster. The important thing here is we observe that HC1 is as low as around 14,000. And that means you can induce a bit flip in around 1.3 milliseconds. And we see that the HC1 distribution depends on the data pattern we use to initialize DRAM rows. The minimum values might, be similar, but the total population or the distributions are still heavily affected by the data pattern. And this variation exists across channels in every tested chip. So I'll move on to the second analysis now. If you have any questions so far, I'll be happy to take them. No? No questions. Okay. So I'll move on to the second analysis then. This is the analysis on RowHammer's sensitivity to hammer count. So we look at the hammer count needed to induce up to 10 bit flips in a DRAM row. And to do so, we develop 9 other metrics that are based on the hammer count needed to induce the first bit flip. So these are hammer counts needed to induce 2, 3, 4, and so on until 10 bit flips. So HC first, second, third, fourth, and so on. We have 2 takeaways. First, we find that on average, fewer than 2 times the minimum hammer count to induce the first bit flip is enough to induce up to 10 bit flips. So if your HC first is 1, hypothetical, your HC 10th is on average 2. And second, we find that if it takes many hammers to induce a bit flip in a row, it likely takes fewer additional hammers to induce more bit flips in that same row. So let's start with the first takeaway. Now, this plot shows the hammer counts needed to induce up to 10 bit flips. That's over the x-axis, normalized to the hammer count needed to induce the first bit flip. And we have 4 boxes, 1 for each tested data pattern. Here are 2 boxes that show the values for the hammer count needed to induce 2 bit flips. And this means we need, on average, approximately 1.2 times HC first to induce the second bit flip in a row. And this is the complete plot. And we observe that the hammer count needed to induce up to 10 bit flips. It varies between rows. And each box shows you the degree of variation for a single data pattern. And on average, again, the same thing I mentioned, fewer than 2 times HC first is enough to induce 10 bit flips. And the second takeaway, to show that, we will look at the previous data in a different way. The x-axis here shows you the hammer count needed in the first bit flip, and the y-axis shows you the additional hammer count over HC first that we need to induce the 10th bit flip. So the value you see on the x-axis, let's say 100K, plus 100K, that's 200K, that's the 10th bit, that's HC 10th. I'll have an example. So this is one DRAM row, an example point in this plot. It represents a row that exhibits a bit flip after 30,000 hammers. That's where it intersects the x-axis, and 9 additional bit flips after 80,000 more hammers. That's where it intersects the y-axis. So HC 10th will be 110K. This is the complete plot. And we look at how x and y axes correlate. And we find that increasing HC first is, I will use the word somehow, correlated with decreasing additional hammer count to induce the 10th bit flip. Now this shows that if a row can endure many hammers before it exhibits the first bit flip, we can likely induce more bit flips with fewer additional hammers. And this is consistent across tested chips. And you can see the correlation coefficients. So again, I use the word somehow. I don't know what the proper correlation qualifier for 0.39 is, but it's not correlated. It's not strongly correlated either. There's some correlation. Any questions? No. Perfect. We can make some progress. So lastly, we will look at how read disturbance changes with the amount of time a row is kept open. That's RowPress. We already know RowPress, but the basic idea is you keep a row open for longer instead of repeatedly activating it many times. Two takeaways: the bit error rate increases with aggressor row on time, and as we keep the row open longer, DRAM rows experience bit flips at smaller activation counts. There's nothing particularly surprising about HBM2 that's so much different than what the RowPress paper shows. So I think I'll skip these and only answer questions if you have any. Do you have any questions? Nope. Okay. Yeah, I mean, as I said, that's it. 649 rows. Oh, this one is basically showing you the number of rows plotted in this figure. The 600. So we look at, I don't remember the exact number, but let me try to figure this out. I think 256 rows from three different subarrays in total. So 256 rows in each subarray. What we do here is, you can see on the x-axis the aggressor at one time. So we're trying to figure out how the activation count needed to induce the first bit flip, AC min or HC first, or RDT, changes with aggressor row on time. And we've tested 768 rows, but some of them don't exhibit bit flips in the standard 32 millisecond refresh window across all tested aggressor row on times. So we excluded those rows, and that's the population we're showing here. And the observation here is basically you see what we see in RowPress. You can induce bit flips with one hammer. Yeah. Yeah, sure. And as your aggressor one time increases, your AC min reduces. HC first, RDT. All of them are the same.
So did your earlier VRD study also cover these HBM2 chips?
Yes.
Was there anything different for HBM?
Not
I don't remember
particularly
that.
different. No, I mean, yeah. It's like the VRD exists in HBM2 as well.
Similar DDR4.
Yeah. Furkan does not have a microphone.
So you mentioned that some rows did not show any induced bit flips in the standard 32 ms window, right?
Yeah.
Refresh window. So what's the most endured time? Like, what's the maximum TAG on, basically? Is there such a thing among those rows? If you were to extend the 32 ms.
Yeah, I mean, I didn't look at that.
Oh,
so
okay.
I wouldn't be able to answer that. But it's not that you don't get any bit flips in them within 32 milliseconds. At some tested, like either one of these tested aggressor one times, you couldn't get the bit flip in 32 milliseconds. Because you remember earlier, Haosong showed, like as you increase row on time, the time to bit flip also tends to increase. Because your activation count does not reduce proportionally, like it reduces with aggressor one time, but not in a way that you would guarantee you would get the bit flip in the time it would take you to get the bit flip with double-sided RowHammer. It might take you longer to get the first bit flip with fewer activations, but you keep each row open for longer. So, yeah.
Okay.
So if I remember, row size is smaller in HBM, right?
It is,
compared
yes.
to DDR4. And in a more realistic system level scenario, you would need to access different columns to keep the row open. And you have fewer columns in HBM in that case.
That's correct. You have 32 columns in HBM2.
Okay.
The column size is also bigger in HBM2.
Oh, okay.
Yeah.
So then RowPress can be less of an issue for HBM. Can we say that?
RowPress could be less of an issue for HBM. Maybe
Because it's harder to keep rows open?
The problem is, I think answering that requires insight into the workloads.
Okay.
And we lack that insight, right? So we don't know how an average HBM2 workload, how long it would keep the row open. But the absolute maximum time a row can be kept open to stream through the data should be lower for HBM2 than DDR4.
Okay.
I think. But GPU workloads probably have regular access patterns. That means the rows are going to be open for longer, right?
Yeah, you can just stream through some row, but
yeah, if you open
have
a row,
smaller amount of data, then you would just read it and then close it to move to another row.
Yeah, but at least as far as I think, like those regular LLM blah blah workloads considered, I think once you open a row, you're streaming through it for those workloads. So that means you're keeping it open until the end, until you read the whole row.
Maybe we should run those workloads somehow.
Andreas? Did you catch what Giray said? Okay.
It's okay.
You can watch the recording. Fifth hour into the recording, you should. Okay.
Are you planning to present EasyDRAM in future?
Yes.
Okay.
In the future.
In the future, yeah.
Yeah, maybe 2026,
Not today, yes.
maybe 2027.
Okay.
Yeah. What's about EasyDRAM?
Maybe we can discuss when you.
Oh yeah, sure.
Yeah, it feels like somewhat relevant. Like you can put real workloads.
Real workloads with real DRAM chips, yes.
Yeah.
We have another platform that we recently developed and published in DSN just a month ago, where that allows users to experiment with DRAM techniques that are, not implemented in real systems, but have huge promise to deliver better performance, energy efficiency, reliability, and using real chips, really. And the key trick we apply there is, it's an FPGA-based platform, so you have access to real DRAM chips in an interface that's as powerful as DRAM vendor, and you also have the ease of use of something like a software simulator. So you can program the memory controller in the FPGA board with C++. So in theory, you could implement RAM emulator in this FPGA board and implement whatever technique you want to implement there and test things out.
Okay, let's not get into that.
Yes. So that's EasyDRAM. That's the 6th paper in this talk. And I won't talk about it more. We have some hypotheses that explain some of the behavior we see. We attribute the similarity in bit error rate and HC1 within groups of 2 channels that are highlighted here to their physical placement inside the HBM chip. We think that groups of 2 channels share the same DRAM die. We cannot validate this hypothesis very easily. Second, the bit error rate changes with the row's proximity to the sense amplifiers. We think that the significant drop in bit error rate in the middle and last subarrays could be due to the subarray's proximity to bank I/O logic. Maybe the subarrays closer to bank I/O have different voltage profiles for some reason. It's not completely unlikely, but again, something we cannot validate very easily. And we have alternative explanations for these observations. So you can read the paper. And now an alternative explanation for the reduced bit error rate in the last, in the middle subarrays is these are at the end of your bank, and those subarrays that are at the end of your bank have what we call dummy bit lines. So you might remember in some pictures presented today, the differential sense amplifier has two ends, basically, two terminals, bitline bar and bitline. For these subarrays, you only have bitline bar. So the amount of bit flips you can expect is lower. So that hypothesis also could explain this behavior. But again, I'll refer you to the paper for details on these hypotheses. Okay, so based on the key observation that I show you here, we draw two implications for redisturbance attacks and mitigations. The observation is that bit error rate and HC first varies across channels. First, attacks can use the most vulnerable channel to accelerate their preparation and attack phases. And this could allow an attacker to take over vulnerable systems more quickly. You could argue that first you need to identify that channel with the worst bit error rate. Perhaps that can be done relatively easily by sampling some rows, right? And second, mitigations can allocate fewer resources to protect redisturbance resilient channels and more resources to protect redisturbance vulnerable channels. So you would be allocating your resources more efficiently and end up with more efficient redisturbance mitigation mechanisms. A different version of this idea, I think, SaLWo already implemented and explored for, like at finer granularity at row level. So something like SaLWo, but at a coarser granularity, you could do for HBM2 chips. So I'll now describe the second analysis we have on DRAM die RowHammer mitigations. We see that the chip we test implements an undisclosed on-DRAM die RowHammer mitigation mechanism, and a specialized access pattern can bypass this mechanism actually to induce many redisturbed bit flips. So there is something defined in the standard called target row refresh. Target row refresh mode, TRRM, something like that, where the controller and the HBM chip cooperate to prevent RowHammer bit flips. But we also know from prior work that real DDR4 chips implement on-DRAM die mitigation techniques that are not disclosed, and they take actions in a memory controller transparent way, typically hidden behind the latency of a periodic refresh operation. And we want to understand if a similar hidden mitigation mechanism exists in our HBM2 chips, not the one that's already defined in the standard. So we use the methodology presented in this paper, where the key idea is to use data retention failures as a side channel to detect when a row is refreshed by an on-die mitigation mechanism. We reuse the source code that's publicly available on this page. And our experiment first finds a DRAM row R with a retention time of T. So this means that the row will exhibit retention failures if we don't refresh it for T units of time. Arbitrary units, doesn't matter. And on the bottom, we have a timeline of actions taken by us and the currently hypothetical on-die mitigation mechanism. So initially, the row is refreshed. It can retain data correctly until time is T. We wait for half T, and then we activate and pre-charge R+1 adjacent to the victim row once. And let's look at what a hypothetical mitigation could do. So it will sample this hammering of R+1 as an aggressor row activation. And then we issue a periodic refresh command
to trigger the mitigation to take an action. And if the mitigation sampled R+1 as the aggressor row, it will refresh R as the victim row. And then we wait for another half T, read row R, and check for bit flips in row R. Row R will not experience any bit flips, only if there is an on-DRAM die mitigation mechanism and it has sampled the activation of R+1 and refreshed R at half T. In contrast, row R will experience retention bit flips if there's no on-DRAM die mitigation mechanism or it didn't sample the cell, the activation, because it was not refreshed for T units of time, right? So that's the basic idea. And we perform this, the experiment is a bit more involved than this. You have to deal with or factor in variable retention time, which is a pain. And I've been told by our contributor, Yahya, who did these experiments, that it was a very painful procedure. So we performed this experiment and find that the HBM2 chip implements an undisclosed on-die mitigation mechanism. This performs a victim row refresh, also called a TRR refresh, every 17 periodic refresh operations. It refreshes both of the adjacent rows of an aggressor row, so both victim rows. And it identifies the first row that gets activated after a TRR refresh and the row that receives more than half of all the activations between two refresh operations as aggressor rows. And we developed several access patterns that we designed to bypass the mitigation mechanism. And this plot, I won't explain it in detail. We show that the specialized access patterns can basically trick the TRR mechanism into thinking that dummy rows are aggressor rows, while real aggressor rows go unnoticed and induce RowHammer bit flips. So we have other things in the paper. We have two preliminary analyses of the effects of aging on bit error rate and the effects of passing time on the minimum hammer count to induce a bit flip, which later evolved into VRD actually. The effect of aging goes both ways for bit error rate. There are almost an equal number of DRAM rows with higher bit error rate and lower bit error rate after 6 months of leaving the HBM2 chip powered on. I will be happy to take questions if you have any on that. As for the effect of time on HC first, you've seen details in my VRD presentation, so I won't go into them. We also analyzed the effectiveness of ECC. We find that relying on ECC alone is not good enough to prevent RowHammer bit flips in HBM2. It turns out to be a very expensive solution. You need 75% redundancy if you want to tolerate all of the bit flips to be observed. We have more implications for attacks and mitigation and more hypotheses that explain our observations in the paper. So this last bullet, I already described it and forgot to remove from this slide. So that's not an additional thing. You've already seen it. So briefly summarize, we provide the first detailed experimental characterization of read disturbance in modern high bandwidth memory DRAM chips. We show that read disturbance spatially varies across cells, channels, and rows in the HBM chip. And we also see that read disturbance resilient rows exhibit multiple bit flips with fewer additional activations. And we've seen the effects of, or we have shown the effects of RowPress. We've also uncovered the details or inner workings of a modern HBM2 chips on the DRAM die mitigation mechanism, RowHammer mitigation mechanism. And we think that our observations could enable faster and more effective attacks and also more efficient mitigations. And an extended version is available on arXiv, and all the data and code we used for HBM read disturbance is available at this link. And that's it for the second paper of my talk. 2 more to go. Almost there. But this basically, now we're gonna switch gears and we'll talk about mitigations. This was the last analysis, read disturbance analysis paper presented today, I think. we have 2 questions there. I don't know, like you can, Vlad, you can start. I'm sorry.
So, are there any prior works before DRAM Bender that did this kind of characterization, like experiments? And if so, how did they manage to do that? Because it seems like kind of impossible to do it without the infrastructure. And I'm wondering if people reverse engineered or bypassed somehow the virtual memory system, let's say, to do it.
Yeah, that's a good one. The first, I think RowHammer flipping bits paper does not have. Okay, this is making too much noise. I don't think they had access, or they used this sort of an infrastructure to perform that testing. I think they used real systems, but disabled refresh. Okay, both of them. There you go. Okay, yeah. So there was an even earlier version. Basically, there was SoftMC, but even before that, Onur mentioned it before he left. I believe I've not seen that infrastructure. A more sort of hard-coded version, again, an FPGA-based infrastructure, but imagine your tests were written in Verilog, something like that, which was harder to program and run experiments with, but there was some infrastructure. But even before then, maybe, yeah, it would be hard. The easier it's to program and use these infrastructures, the more people have access to them, which is why infrastructure like DRAM Bender is, I think, important to develop. Like ease of use is something that the research community does not really value, but
yeah, I assume something like RowHammer also couldn't get the artifact evaluated, right? Like reproducible. I assume no reviewer is gonna spend lots of time to reproduce that, right? If you don't have the infrastructure, I mean.
Yeah, that's correct. I mean, you usually do your best to provide the reviewers with, the easiest way to reproduce everything. So. Actually, yeah, you can hand the microphone over. It's just a comment. For these works, like redisturbance analysis works, when we want to get artifact evaluated, meaning some reviewers reproduce our results, we give them access to our infrastructure remotely, and then they perform all the tests we perform at a smaller scale, because we cannot give all the FPGAs.
So there are also some security groups
that you're right, yeah. Yeah.
I just one example is like one of the universities like one location hammering access pattern.
Yeah.
They were trying to access the same location many times. And then they identified that. And then after also RowPress and other they were asking the question like, is this the same thing or different? So without actual like this kind of fine-grained observation, you cannot make strong conclusions on the underlying effects. We can understand, we can exploit how you can.
You have one, or yeah.
So I was wondering, just to make clear, to bypass this hidden on-die mitigation in the HBM2 chips, do you need to offload like more than half of your total hammer count to dummy rows? Is that correct?
I won't be able to answer you, I think. I might need to go back to the paper for that. But something like that, you need to do it. Yeah, because otherwise your row will be sampled as an aggressor row.
So you need a certain number of hammers on your actual aggressor rows, and also offload at least as many to the dummy rows.
Yeah, something
but
like
you
that.
can still stay below the refresh period. Is that the case?
Yeah.
I see. Okay.
So if you see here, I cannot navigate for some. Okay, there you go. The x-axis here is number of dummy rows, and the aggressor row activation count in a tier. Yeah, so this is how many aggressor rows, like how many activations we sent, I think, to all aggressor rows, including dummies. But it might also be the real aggressor row. I need to check that. But it's like you see how the bit error rate changes with the sweep, right? So increasing the activation count for the aggressors to the aggressors increase the bit error rate the most. Whereas number of dummy rows don't really change things so much beyond 4. Before 4, weirdly, without 4 dummy rows, we cannot induce bit flops. Yeah. So that's another thing. Maybe there's a disconnect between how we think the defense mechanism works and how it actually works, because yeah, I mean it's a bit difficult to uncover every single detail. Yeah. So we'll move on, or should we take a break, or I don't know. Vote for yeah, go ahead. Yeah.
Can we change the order a little bit?
We could.
To have some.
Yes.
So Nisa can go now with leaky hammer, and I can come back for abacus and assembly. How about that? No.
If we take a break, yes. If we don't, no. Yeah, like a 5-minute, 10-minute break, maybe.
Yeah. Take a 10-minute break.
So we'll not 10, even 5. 5 is okay.
Okay.
Yeah. So basically, we continue at 32. Past 32. So the camera is.
Yeah. No, not the camera. Comment.
Okay, we're getting started with the next part of. So I've been criticized by some people saying that I am about to fall asleep. I'm not about to fall asleep. I can still go on. I have 2 more papers to cover, and we're shifting gears. So we're talking about defenses from now, mitigation, RowHammer mitigations. And this is one of them. So this is Abacus, all bank activation counters for scalable and low overhead RowHammer mitigation. And this was published in Unix Security 2024, I think. Yes, 2024. So this is the outline of this part of the talk. I'll go through a quick background on RowHammer, basically, again, just highlighting the worsening in read disturbance. So this phenomenon is getting worse. We can induce bit flips with around 100 times fewer hammers compared to 10 years ago. And in other words, the RowHammer thresholds of DRAM chips are reducing. And thus, we need effective and efficient read disturbance mitigations for highly vulnerable systems where only a few hundreds of hammers are enough to induce a bit flip. And there are multiple ways to mitigate RowHammer bit flips, and each offers a different system design point in performance, energy, and area trade-off space. And preventive refresh-based ones are promising because they tend to make more efficient use of resources and induce smaller performance and energy overheads. And the idea of preventive refresh is to refresh a victim row before bit flips from a RowHammer attack can manifest in that row. And that is another way to look at it is preventive refresh resets the disturbance effect. But doing so requires what's called aggressor row activation count estimation or tracking. And activation count tracking gives us a way of determining when to refresh a victim row. And if you look at how prior works estimate or track the activation count of DRAM rows, I'm looking at Nisa because this is her slide. We see 3 main design choices. One activation counter for each DRAM row allows us to precisely track each DRAM row's activation count and refresh the victim rows only when necessary, which induces the smallest performance overhead possible. And this comes at a very large area cost because there are millions of DRAM rows in a modern DRAM-based system, even billions today. And some prior works implement only as many counters as needed to track all possible aggressive DRAM rows, which is fewer than all DRAM rows in the chip. And they do this to reduce the area cost in exchange for performance and energy overheads. And finally, there are other techniques that use one activation counter to estimate the activation counts of multiple rows, or use no activation counters at all and randomly determine potential aggressor rows. And these induce smaller area overheads at the cost of prohibitively high performance and energy overheads. So that's like a brief overview. And we find that no existing preventive refresh-based mitigation prevents RowHammer bit flips at low area performance and energy cost at once. And therefore, our goal in this work is to enable that solution, basically low area, low performance and energy cost RowHammer mitigation. And our target is especially the low end of the RowHammer threshold values, where activating a row as few as 125 times could induce bit flips. To that end, we developed Abacus. Its key idea is, I will talk about it in the next slide, is based on this key observation that we make on how workloads interact with main memory. So we will show what we observe over an example. This is a system with a CPU and 4 DRAM banks. And each DRAM bank has a DRAM row at the same row address, highlighted as row X. And a workload running on the CPU generates this load request targeting bank 0 and row X, and the beginning of this timeline on the bottom. The CPU issues this request to its target bank and row, and it repeats this access pattern for other banks, as you see here. There might be other requests targeting different row addresses, but this does not contradict our observation. Eventually, the CPU accesses the same row address across all banks, and we call the rows with the same row address sibling rows. There are 2 causes for this behavior. The first one is the intrinsic spatial locality in workloads memory access patterns. A program usually accesses neighboring cache blocks at around the same time, and a prominent access pattern that leads to this sort of behavior is streaming through the elements of an array. And the second cause is modern physical address to DRAM address mappings that place neighboring cache blocks into different banks, but in the same row. So they do this to leverage bank level parallelism to get the most out of the available DRAM data transfer bandwidth. We also investigate the sibling row activation count. That is, by the time one of the siblings' activation count reaches the RowHammer threshold of 500, what do the activation counts in other DRAM rows look like? So this shows you the distribution of the activation counts of all sibling rows. And from here, we conclude or observe that if a row is activated 500 times, its siblings are likely activated more than 250 times. And the sibling row with the highest activation count, therefore, yields a good estimate for the activation count of all other siblings. Does that make sense? Do you have any questions? Because that's the key observation that is the foundation of the paper, basically. Okay. And if you reduce this target RowHammer threshold, the sibling row with the highest activation count yields an even better estimate for the activation count of all other rows. So let me quickly introduce an important problem of existing per bank activation counter based mitigation techniques. There are many banks in a DRAM chip, and the number of banks and thereby the number of activation counters increase with newer DRAM generations. We have seen that sibling rows have similar activation counts. And our key idea is quite simple. It's to use one activation counter for all sibling rows. And doing that reduces the number of counters by a factor of the number of banks. So if you had 16 counters, now you have one. Abaqus's objective is to track the maximum activation count across all sibling rows using one counter. If, for example, the activation count of sibling rows look like this, 32, 14, and 97, then Abaqus's counter value for the sibling rows will equal or will be larger than 97. Why? Because if the Abaqus counter is smaller than the maximum activation count, we cannot mitigate bit flip, so this is no longer secure. And if it's larger, then we will have increased performance and energy overheads from unnecessary preventive refresh operations. And because of these two reasons, our key design goal for Abaqus is to keep the counter value equal to the maximum activation count. Before I show you how Abaqus achieves that goal, I will describe its key components. Abaqus adopts a frequent item counting algorithm called Misra-Grease, which allows us to use a few counters to track all potential aggressive DRAM rows instead of having one counter per DRAM row. And Abaqus is implemented as a table of counters. Each counter has a row, it has something called the row activation counter and a sibling activation bit vector. And only one row address or row ID at a time can be mapped to one counter. There's a varying number of counters in a counter table based on the RowHammer threshold value. And I will not describe the relationship because it's a bit involved. And finally, there's the spillover counter. It draws an upper bound for the activation count of any DRAM row that's not mapped currently to any of the Abaqus counters. So this is very similar to, or also it's based on the graphene's implementation, let's say. Graphene is a prior work, RowHammer mitigation technique. And we compare it to graphene, we'll get there. So I'll quickly explain the intuition behind Abaqus's counting algorithm that satisfies that key goal. If you remember, we want to have the maximum activation count across all sibling rows tracked. This diagram depicts another example state where the sibling rows have different activation counts from each other. And the maximum activation count is in bank 15, 97. So we will assume that Abacus currently stores this count. And Abacus remembers the sibling row that last got activated and increased this value to 97, which is bank 15 in this example still. And at this point, and it remembers this from the sibling activation vectors that we didn't describe in detail, but you can, I hope you trust me when I say that it can keep track of that information. So at this point, two different active actions can increase the counter value to 98. The first is if bank 15 gets activated again, or the second action is basically if any other bank gets activated twice. The same row in any other bank gets activated twice. So I unfortunately will leave you with this much detail about how Abacus algorithm operates in the interest of, well, time and complexity. But Abacus needs some small additional state of 1 bit per bank to operate in this way. And we prove in the paper that Abacus correctly maintains the maximum activation count using 1 counter. Giray has the question.
I have several actually. So what if the workload doesn't exhibit bank level parallelism?
If your workload does not exhibit bank level parallelism, as in you're only accessing 1 bank, well, first your workload sucks in a very, well, you cannot get the most throughput out of your DRAM, which is not nice. But assuming your workload doesn't do it, you will have to incur the penalty of number of banks times additional refreshes, because Abacus does not know if you did not activate any of the banks. The moment one row's activation count reaches the threshold, you will refresh the victims of this row ID across all banks.
Okay, that's fair. Second thing, is Abacus only applicable to misragrees?
No. I mean, this is a way to, like, it's a counting algorithm in the end, and you could implement it, integrate it into many other defense mechanisms, as long as they're counter-based.
Okay, like Hydra?
You could think about implementing Abacus ideas, integrating them together with Hydra, but the way Hydra groups counters is fundamentally different from the way Abacus sort of groups counters. There could be a way to make them work together. We compare to Hydra, and Hydra has, like, according to our evaluation, huge overheads because of how it relies on some sort of summary of activations, and then explodes the summary into hundreds of rows. Basically, you keep track of the activation of hundreds of DRAM nodes using 1 counter, and at some point, so that's coarse grain tracking, and at some point you have to do fine grain tracking because you don't want to refresh a group of 200 rows at once. But that means there's some huge inaccuracy in activation counts. I'm speaking about Hydra, and we'll get there later. So yeah.
Okay. Another thing, in the morning we talked about this per row activation count in prac.
Yeah.
So I know that prac came after this paper was accepted.
Yeah.
Not presented. But yeah, it was already done. So if you would give an update to this paper, is it possible to implement with prac? It's also counter-based. And
yeah,
what kind of benefit would you get from that?
Again, like speaking to Abacus's key idea is the fact that your counters move in DRAM doesn't change the fact that sibling rows have this sort of activation patterns. So if you can leverage this observation, I think you should leverage it because it makes sense. Integrating it into prac is a bit difficult. I've thought about it. The main issue there is, and we can discuss this in detail, you want a centralized place for these counters in DRAM. That means you want a centralized place for your counting algorithm. The way PRAC is implemented is you will have counters per bank. That has some overhead, but it's not extremely, or it's not easy to get rid of all the counters, while getting rid of most of those counters in the way we suggest here would reduce the counter overhead. It's difficult to think about how we would design the DRAM chip in a way that still minimizes the area overhead of those additional counters without having them in each bank for PRAC.
So maybe you don't implement them inside banks anyway. It can be some additional array, like an extra bank, but smaller, something like that.
Something like that would help. Yes, I agree. Somewhere other than a particular bank.
Yeah, the target row refresh mechanisms are implemented in that way anyway, right?
Yeah,
they are outside of the banks.
Yeah, exactly. The disadvantage is you need, the benefit of PRAC is you implement your counters as DRAM cells. So how can you implement a centralized array of counters in DRAM without disorganizing the regular structure so much is a challenge, I think, with DRAM cells. And integrating SRAM into a DRAM chip is very high overhead, right?
No, I think that's out of discussion. It doesn't make sense, but...
So you want basically a DRAM array to store the counters still,
yes,
and not break the regular structure of the DRAM chip.
I still think that it should be practical, but...
It can be. So you don't need so many bits. It's like, let's say you have 256K rows and 8 bits, let's say. 8 bits for the counter. That gives you, I cannot compute, 218, 3.
That's fine. We can discuss design details later.
2 megabytes of DRAM you need. It's like a subarray or more than a subarray. How large is a subarray? Okay, so it's much smaller than a subarray. I think it's doable, but also it's changing the DRAM chip, so it's a trade-off. In a different way than PRAC. PRAC is like potentially less intrusive because you're just, at least the way you store the counters is straightforward. How you operate the counters is a bit less straightforward, more invasive. But if you're proposing to add, a 2 megabyte large DRAM array elsewhere, that could be intrusive.
Let's discuss it later on.
Yeah. Again, like it's a lot of speculation. Right? The fundamental observation doesn't change. It's still useful no matter what sort of counters you have. And you can benefit from it if you can design your system in a way that exploits this. Okay, so let's see how Abacus performs. We use a cycle level memory system simulator that's RAMulator, configured in the way that's displayed here. And we compare Abacus to 4 state-of-the-art preventive refresh-based RowHammer mitigations. These are namely Graphene, Hydra, Vega, and Para. Graphene is the highest performance mechanism. Para is the lowest area overhead mechanism. And Hydra and Vega offer interesting trade-offs between area and performance. And we execute 62 single-core and 8-core multi-programmed workloads from major benchmark suites. We show the system throughput on the y-axis across all single-core workloads for the RowHammer threshold values that we display on the x-axis. But the higher the bar here, the better the performance. And this is the DRAM energy overhead. Here, a smaller value is better. And we conclude that Abacus prevents bit flips with very small performance and DRAM energy overheads compared to a baseline system with no RowHammer mitigation. And this plot will eventually show the 8-core multi-programmed performance distribution across all workloads on the y-axis. For Abacus and the 4 state-of-the-art mitigation techniques. So higher values are better. This is the plot. And here are the boxes for Abacus that show the distribution of performance across all tested workloads. So each point here is a workload. And the red boxes show the mitigation and RowHammer threshold configuration sets, basically, which Abacus outperforms. So the red bars are outperformed by Abacus, the red rectangles. And you observe that Abacus outperforms Hydra and Para at all RowHammer thresholds on average across all workloads. We also see that Abacus incurs a small performance overhead over graphene, which we attribute to Abacus's unnecessary preventive refresh operations due to its low-cost tracking aggressor row activation count tracking scheme. So there are some false positives we induce. We talked about, Giray asked me about the workload that doesn't have bank-level parallelism. So if you think about it, if you have such a workload, you have in the worst case, which doesn't usually or never happen according to our traces, in the worst case, you have 16x preventive refresh overhead for Abacus. So this is the same plot, but for DRAM energy. We observe that Abacus consumes less energy than Hydra, Rega, and Para at the tested RowHammer thresholds, smaller than 1,000. And for example, here, Abacus consumes approximately 2070 and then 34% less energy than Hydra, Para, Hydra, Rega, and Para in that order at a very low RowHammer threshold of 125. And Abacus performs similarly to graphene in terms of DRAM energy, and that's only 4% higher at the same RowHammer threshold, at the very low RowHammer threshold value. We analyzed Abacus's area overhead, and you observe that at a RowHammer threshold of 1,000, Abacus induces a significantly smaller area overhead than graphene, and it takes up smaller area than Hydra. At a smaller RowHammer threshold of 125, Abacus takes up significantly smaller area than graphene. Hydra's overhead at the 125 RowHammer threshold is relatively smaller compared to Abacus. However, it comes at a significant performance overhead that I showed you earlier. And we excluded Rega and Para from this analysis because they don't incur processor chip and area overhead, processor chip area overheads. However, Rega requires intrusive DRAM chip modifications, and Para needs a secure random number generator. So we have more details and analysis in the paper that I don't cover here. The paper presents a security analysis of Abacus, which shows that it guarantees to track the maximum activation count among all sibling rows and securely mitigate RowHammer bit flips. There's performance and energy comparison for less memory-intensive single-core workloads, circuit level performance, latency, energy, and power estimation based on a functional hardware Verilog model of Abacus. And for example, we showed that Abacus' circuit latency is approximately 1.2 nanoseconds, which is significantly smaller than the minimum allowed delay of 2.5 nanoseconds between two activate commands. That's the bullet that says the same thing. We also evaluate Abacus' performance under adversarial workloads that aim to exacerbate the preventive refresh, the number of preventive refreshes, by rapidly incrementing Abacus counters, and our alternative Abacus design that defeats these workloads, which is the integration of Abacus into a different baseline mechanism, not Misra Greece, but we have basically counters for every DRAM row. And Abacus's performance and energy sensitivity to important system variables, and finally, a discussion on how to account for RowPress. You can find that in the paper. But if you have any questions, I'll be happy to answer those after I conclude. So based on the key observation that many workloads access the same row address in different DRAM banks at around the same time, we developed Abacus, which uses one counter to track the activation count of many rows with the same address across all DRAM banks. And we show that Abacus induces small performance and DRAM energy overheads at very low RowHammer thresholds, such as 125, and it outperforms the state-of-the-art mitigation techniques. And Abacus is similarly to all other work, all all our other work has its extended version available on archive, and it was open source and artifact evaluated. Yeah, if you have any questions about Abacus, I can take them now or later. Ismail, you have a question? No. Okay, then I'll continue with self-managing DRAM. This is the last paper that I'm going to present. This is self-managing DRAM, a low-cost framework for enabling autonomous and efficient DRAM maintenance operations. Should I continue? Was there okay, I'm continuing. Okay. So I'll start with a summary. Implementing new in-DRAM maintenance operations, such as better RowHammer protection, implies changes in the DRAM interface and other system components like the memory controller. Modifying the interface, however, is quite an involved process that typically takes multiple years. And our goal is to ease and accelerate the process of implementing new efficient in-DRAM maintenance operations. Our key idea is to propose a simple change in the interface such that the DRAM chip can reject memory accesses that target an under-maintenance region in DRAM. The single change in the interface allows DRAM designers to implement new maintenance mechanisms without any further changes to the interface and to other system components but the DRAM chips themselves. We implement 3 in-DRAM maintenance mechanisms in SMD to show that SMD is useful and versatile. And our evaluations show that SMD enables performance and energy efficient maintenance operations, not mitigations, at small area cost. And all our sources and data is open sourced at the link on the bottom. This is the outline of the of SMD. I'll continue with some background and motivation. So let's see at a very high level what the DRAM interface looks like today. A DRAM chip communicates with the memory controller over the DDR-X interface, where the memory controller issues DRAM commands over this unidirectional DRAM command bus, and the memory controller and the chip exchange data over the data bus. Using this interface, the memory controller orchestrates all DRAM operations by sending commands to the DRAM chip, and the DRAM chip executes all DRAM commands without question. Thus, today's DRAM interface is completely controlled by one side. And an important type of DRAM operations is those performed by maintenance mechanisms. So DRAM is subject to many error modes, such as the ones that I showed there, that necessitate maintenance mechanisms, and we discussed one of them extensively today. DRAM maintenance mechanisms at a high level maintain data integrity. And another prominent example, let's say, is periodic refresh, where the memory controller periodically issues refresh commands to prevent data retention failures. As manufacturers scale storage densities, these error modes cause memory error rates to increase. And the key point that I'd like to highlight here is that continued process variation, continued process scaling necessitates new efficient maintenance mechanisms. And maintenance mechanisms are defined as part of the standard DRAM specifications. JEDEC, composed of more than 300 companies, defines the DRAM standard and produces devices that obey the standard. And the DRAM standard poses a barrier to entry for new efficient maintenance mechanisms because adding new or modifying existing mechanisms require modifying the DRAM specifications and other system components, such as the memory controller, that obey the specifications. The key reason for the barrier to entry is that the DRAM interface is rigid. It's also not easy to release a new DRAM specification because doing so requires a multi-year effort by a JEDEC committee, and thus introducing new maintenance operations takes a very long time. And for example, the recently released DDR5 standard introduces 3 maintenance techniques that improve bank-level parallelism, performance, and system robustness and error tolerance. Introducing these mechanisms was only possible after the 8-year time duration between DDR4 and 5. However, if new maintenance mechanisms could have been more rapidly released, these improvements could have also been released much earlier or at different times. Now let me reiterate the problem and our goal based on what I already explained. Introducing new maintenance operations or mechanisms take a long time, and our goal is to ease and accelerate the process of implementing new efficient in-DRAM maintenance operations. Now, before I explain you our solution approach, let me quickly categorize DRAM operations into two simple classes. That's access and maintenance. Access operations serve memory requests, typically relying on information available only to the memory controller, whereas maintenance operations maintain DRAM data integrity, typically using information available only to the DRAM chip. A key observation we make is that a DRAM chip has all the information it requires to maintain itself. And a DRAM chip should also maintain itself due to two other reasons. First, you can implement maintenance mechanisms more easily and possibly faster, because doing so would not require changes in the interface. And second, it enables DRAM manufacturers with breathing room to perform architectural optimizations without exposing any DRAM internal proprietary information to other parties. Our solution approach is to enable autonomous maintenance operations in DRAM chips. However, the DRAM interface definition is too rigid to accommodate autonomous in DRAM maintenance operations. In particular, the DRAM interface is designed in a way that yields all control to the processor. So whatever is on the other end of the DRAM interface, then the DRAM chip. And our goal is to make a simple one-time change to the DRAM interface and enable autonomous maintenance operations. Another way to look at this is we aim to give breathing room to DRAM chips so that they can perform their operations autonomously. And to that end, we develop self-managing DRAM. In our work, we introduce autonomous in-DRAM maintenance operations, in which the DRAM chip has a full control over in-DRAM maintenance operations. This allows us to add new maintenance mechanisms inside the DRAM chip without modifying the standard and without exposing DRAM internal proprietary information. And one problem that autonomous in-DRAM operations introduce is access maintenance conflicts. These happen when the memory controller accesses a DRAM region undergoing maintenance. Our solution to this problem is to make a simple change in the DRAM interface that allows the DRAM chip to reject access commands. Specifically, these will be activate commands that target under maintenance regions. So in summary, SMD enables autonomous in-DRAM maintenance operations with a simple change in the interface. And SMD divides the work nicely between the memory controller and the DRAM chip, such that new maintenance mechanisms can be implemented without modifying the DRAM standard. So we'll take a deeper look at SMD, starting with SMD bank organization. And to better understand SMD bank organization, you would normally require some high-level overview of a DRAM chip, which you already know at this point, so I'll skip. So this is what a DRAM bank with SMD looks like. We introduced the concept of lock regions, and lock regions define the granularity of maintenance operations. And the lock region bit vector indicates the regions that are undergoing maintenance. There's a lock controller. It orchestrates the locking and releasing of DRAM regions. And this is the point of the talk where I keep saying lock, lock, lock again, and people make fun of me because of doing that. So I'll say a lot of locks in the next 4 or 5 slides. So it's support for SMD in a DRAM bank. We lock a region before starting maintenance operations in that region. Let's see how exactly regions are locked and released. Oh, you go ahead. What? Oh, no question. Oh, you're counting the number of, okay. So in summary, there are 4 steps. First, the maintenance operation locks the region it targets, right? And second, the memory controller can access regions that are not locked. Third, if the memory controller accesses a locked region, a lock region, it receives a negative acknowledgement. So that region is undergoing maintenance. And fourth, the maintenance operation releases the lock. So let's take a deeper look, starting with the first step. We have our lock regions on the right. Those are multiple subarrays. And the lock controller on the left. and the lock region bit vector on the bottom. So all regions are in the not locked state currently. So this bit vector is full of zeros. So I'll refer to lock regions as regions, right, to reduce the number of locks, I say. A maintenance operation attempts to lock region 0, and the region is not locked. In this case, the controller, the lock controller, acquires the lock for region 0 by setting the corresponding bit in the bit vector. So then the maintenance operation can proceed in region 0. If the memory controller wants to access a not locked region, such as region 1, it checks the corresponding bit in the bit vector, and it is not locked, so the access can proceed. You can do maintenance in one region while accessing another region. Here, the memory controller tried to access region 0. It would receive a negative acknowledgement because that region is currently locked. And we will discuss how the memory controller deals with negative acknowledgements a bit later. That's the negative acknowledgement. So once the maintenance operation ends, the lock controller releases the lock by setting the corresponding bit in the bit vector to 0. And that's how SMD locks and releases regions. Is there anything you want to ask? It's quite simple, yes. So let's see how we control an SMD chip. What changes are required to the memory controller? All access operations work like they would in today's DRAM interface, with the exception that some activate commands may get rejected. And the memory controller needs to retry these rejected commands. It can attempt to access other lock regions that are not undergoing maintenance. And the SMD chip and the memory controller ensures that no request is rejected forever, right? So we'll start with the first step, how to handle command rejections. And you already know about the activate command, so I don't need to introduce that command to you. Let me just quickly see. Yeah, we have timing parameters that define the minimum intervals between successive commands on the DRAM bus. So you know about these at this point. So we can continue. So we're looking at activate command rejections that happen when we have access maintenance conflicts. This is an example conflict, example command sequence that target region 0, and it leads to an access maintenance conflict. Now, what does the memory controller do? It has to retry the rejected activate command sometime near in the future. And the memory controller is already used to working with timing parameters. So we simply introduce a new timing parameter called the retry interval, after which the memory controller retries a rejected activate command. We determine this parameter empirically. While the memory controller waits for retry interval to pass, it can issue activate commands to another lock region and overlap the latency of maintenance in one region with a useful operation in another region. So the design component in SMD that enables this operation or maintenance access parallelization builds on the basic ideas proposed in prior work, in particular SaLWo. And you can see that paper linked there for more details. Now, you might be thinking about repetitive rejections leading to resource starvation issues. I won't go into details of how, but we prove that SMD ensures forward progress for memory requests in the paper. And we can talk offline if you want to see or have questions about the proof. So I'll describe how we use SMD to implement efficient in-DRAM maintenance mechanisms. We describe and evaluate 3 use cases in our conference paper to demonstrate SMD's usefulness and versatility. These are namely fixed rate refresh, deterministic RowHammer protection, and memory scrubbing. And the extended version of the paper evaluates 2 additional mechanisms and discusses also how SMD can be beneficial for many other use cases or applications. So those are mentioned also in the conference paper. So I'll briefly talk about fixed rate refresh, and for other mechanisms, I'll refer you to the paper. We already know why we need to do refresh at this point, so I'm not going to talk about it. But to do a refresh operation, you need to send a refresh command. where you see many refresh commands all the time. Clearly, you don't need to do this if you have autonomous operations, maintenance operations. Let me talk about the drawbacks of doing refresh this way. The first thing, the obvious thing is, it induces energy overheads and creates contention on the memory bus because you cannot send another command while you're sending a refresh command. And during refresh, an entire chip or a bank is inaccessible for a relatively long period of time. So SMD gets rid of the first drawback by autonomously performing refresh inside the DRAM chip. And the second drawback by, to some extent, by allowing access to lock regions that are not undergoing maintenance. So SMD-based fixed-rate refresh has three main components. The pending refresh counter counts or indicates the number of refresh operations we have waiting to be done. So we can pull in some refresh operations, we don't pull in, but we delay some refresh operations that the way standard allows you to. The lock region counter points to the lock region we must refresh next. And the row address counter points to the DRAM row we should start refresh operations from in that lock region. And we increment the pending refresh counter every refresh period, and that happens typically approximately every 7.8 microseconds. SMD fixed rate refresh tries to do a refresh operation whenever this PRC, pending refresh counter, is greater than 0. It attempts to lock the region corresponding to the lock region counter. If it's not locked, you will try again. If it's locked, you will refresh granularity number of rows that's configurable. And we evaluate this as a parameter sensitivity as part of a sensitivity study. Now, after the refresh completes, you will release the lock, increment the lock region counter and row address counter, and decrement the pending refresh counter. And that's a simple, basically state diagram that shows how SMDFR works. For the implementation details of other mechanisms, I have to refer you to the paper because they're quite mechanical and too many steps to cover. So I'll move on to SMD's evaluation. We'll look at SMD's hardware implementation and overhead first. It requires one modification in the DRAM interface. That's the addition of the negative acknowledgement signal. Now, if you think about it, there are two options to do this. The first one is to use a signal called alert N that already exists in the DDR4 and DDR5 interfaces. And this comes at no additional pin cost. The second option is to add a new pin for each rank of DRAM chips in the system, which comes down to about 1.6% pin count overhead for a modern many-channel system. And again, SMD proposes this one-time change in the interface to hopefully prevent future modifications from implementing new maintenance mechanisms. We also find that the DRAM chip modifications introduced by SMD are relatively small. I won't talk about each of them one by one. You can see the paper for more details. And the memory controller also needs some small additional storage to track the regions that are undergoing maintenance. Again, these are relatively small, almost negligible overhead. We use RAMulator to evaluate the performance and, do you have a question? No, okay. The performance and energy efficiency of SMD. This is the baseline system for your reference. I'm not going through this. And you can see the GitHub repo for more details. We configure SMD with 16 lock regions in a DRAM bank, with 16 subarrays in each lock region, and with a retry interval of 62.5 nanoseconds. And these are, again, determined empirically based on a parameter sweep. So we use 62 single core and 64 core workloads from these benchmark suites. And we evaluate the baseline DDR4 system shown in the previous slide, SMD-based fixed rate refresh, deterministic RowHammer protection, memory scrubbing, and SMD combined, which combines all three of these techniques, and a hypothetical no refresh configuration that does not do any maintenance operations. But such a DRAM chip wouldn't exist because you have to do maintenance operations. Just to show like a limit study. Just to do a limit study, we evaluate this. So this plot shows the average speed up across all single core workloads over the baseline system for the tested configurations. And we make two observations here. First, all SMD configurations provide substantial speedups. And second, SMD combined provides a comparable average speedup to no refresh that does not do any maintenance operations. And this plot shows SMD's performance in the same terms for 4 core workloads. The x-axis shows 3 classes of 4 core workloads, categorized based on their last level cache misses per kilo instruction statistics as MPKI as a measure of their memory intensity. Here is the full plot. We observe that SMD provides higher speedups as memory intensity increases. We show the average DRAM energy across all tested workloads normalized to the baseline. So the lower the bar, the better in this case. The x-axis shows the single core workloads on the left and the 4 core workloads categorized into the same categories on the right. So we observe that all SMD configurations provide substantial energy savings. And we find that SMD combined provides more than half the energy savings provided by no refresh. So this is a summary of performance and energy. SMD enables performance and energy efficient maintenance mechanisms and provides comparable benefits to a hypothetical system with no maintenance operations while increasing system robustness. We attribute these benefits to SMD overlapping the latency of maintenance operations with useful access operations and to reduced command bus interference and energy use as the memory controller does not issue maintenance commands. There's much more about SMD in the paper that I won't cover. We have the proof of forward progress, which I mentioned, and discussion of more use cases, which again, I also mentioned. But we also have more discussion about design choices you could make about SMD. We evaluate a policy that pauses maintenance operations when you want to prioritize access over maintenance. If you have a long time taking, relatively long time taking maintenance operation, you can pause that and serve the access operation first. We discuss a more predictable implementation of SMD. We have sensitivity analysis that shows that performance improves with the number of lock regions because the opportunity to parallelize maintenance operation increases. Maintenance operations with access operations increase. And SMD's benefits increase with reducing refresh period, which is interesting because refresh period recently reduced from 64 to 32 milliseconds from DDR4 to DDR5. So the trend looks downwards and we might have lower refresh periods in the future. We also evaluate SMD with different number of cores for workloads. And it provides similar benefits across different number of cores. SMD, we also evaluate SMD based in DRAM scrubbing, compare it to memory controller based scrubbing, ECC scrubbing. And we see that SMD induces a substantial 8 times less overhead at very high scrubbing rates because you don't need to take data outside the DRAM chip to do the scrubbing operations. And you can check the paper for those details. So let me quickly conclude. Implementing basically new maintenance mechanisms require changes to DRAM standards. And we develop SMD whereby we propose a simple single change to the DRAM standard, which enables implementing new in-DRAM maintenance operations with no further changes to the DRAM interface. We showcase the benefits of SMD using 3 use cases. And our hope is that SMD enables practical adoption of innovative ideas in DRAM design, and it inspires better ways of partitioning work between the processor and the DRAM chips. And an extended version is available on archive data and code is open sourced. That's it for SMD. I can take questions about SMD now. 2 questions. Harsh, maybe go first.
I will go back to my question from earlier today, which was, although profiling is not necessarily always a maintenance task, what if the memory controller wants to put the DRAM into maintenance? such that, so as a signal that, okay, I don't have requests coming to you in the near future. Why don't you collect some profiling data so that we can leverage this for future use? This is in the context of course, read disturbance, for example, especially with variable read disturbance.
No, this would be, I think this would be a good use case for SMD. I was talking about this also earlier in the one of the coffee breaks. The parallelism, I think you would need to justify the profiling, essentially. So you don't want to profile your DRAM chip without, so if you enable profiling, you shouldn't disable accesses somehow. So you shouldn't have, you shouldn't tell the user that, oh, you cannot use this DRAM chip for some time because I'm profiling it or some maintenance is running.
The other way around, yeah.
Yeah. So maintenance access parallelization would help, I think. And you want not the access, but the maintenance component of that parallelization to be spent for profiling, I think. So you propose it, I think, somehow the other way around. I'm not 100%. You said something like memory controller could signal the chip to start profiling.
If the memory controller sees that certain banks or certain regions of the DRAM are not going to have requests in the near future, you could put them into maintenance mode.
You could.
Or profiling mode,
but with parallelism, like maintenance access parallelism, you don't even need to wait, I would argue.
Oh, I see. Okay. Okay, I understand now. Yeah.
Because also idleness prediction is a bit difficult, and I mean it's a bit easier to do that if I think your system is either used or unused. Like if it's used, it's difficult to predict idle times. It might not be idle also under high use.
That makes sense. This might be very workload dependent.
Yeah. We had Giray and Andreas next after you. Okay, you can go next.
I want to piggyback on what Harsh said. You cannot profile if it's idle. It has to be unallocated, because if it's idle, it might still have user data. And what are you profiling for? Retention? RowHammer? You will corrupt data if your goal is to profile things. It's not
probably
just idleness.
you want to evict data out of the subarray you're profiling.
So idleness is not enough.
Yeah, exactly. You need support for efficient data movement. Or if you trust your error correction capabilities, and trust yourself that you won't exceed those capabilities with your profiling, that can still work.
Is it only me now?
Yes.
Okay, so the self-managing DRAM is a good design, and it took a lot of time to get accepted. And then later on, DDR5 update came about this PRAC, and it introduced the back-off signal, which is similar to the ACT-NAC signal that SMD defines. So the industry obviously went to this path for read disturbance in particular. But let's say you want to achieve what SMD provides you without further modifications to the DRAM interface, and just using this PRAC's alert backoff functionality. Is it possible to do so?
I think so.
So you don't have the concept of like lock regions or anything like that.
I mean, you would implement that, right?
What?
First, you would implement the concept of lock regions in your DRAM chip, but the alert 10 signal on its own is enough to communicate the back pressure.
Okay. So we can actually, if we would be a DRAM manufacturer, we can easily implement the functions that SMD provides.
I think that, well, that's a different question. It's easily implementable. I'm not 100% sure. Probably there are challenges, but...
Okay, let me redefine without needing any modifications in the interface.
I would say so, yes. Maybe there's some discussion about the alert 10 signal being too slow and so on. Maybe that needs to change a bit, but other than that, like that additional signal is there. you could
Okay.
you could reuse that.
So SMD comes at no addition to the interface.
I would say so. Yes.
On top of the up-to-date DDR5 standards.
Interface does not need to change.
Okay. Good. Thanks.
Yeah. Any other questions? Okay, if not, I'll conclude this part of the talk very quickly with the summary again.
Okay.
Yeah.
I thought you were done.
No, almost done. But I'm practically done. It's just I hope that now these bullets resonate with you a bit better, and I hope that I kind of motivated you that RowHammer is getting worse and that we have a lot more to do. And I wish the rest of the workshop will continue convincing you in this direction. So this is not concluding the workshop yet. It's just concluding my 4-hour-long presentation. Thank you.
I think the audience who survived this much also first another applaud. So please. Okay, so we have Nisa next. Before that, how many people wants to take a break? Just Andreas? Konstantinos as well? Okay. I'm not gonna say the names. Still the minority. Okay, you guys can take a break, then we can continue.
Okay, we're continuing with Nisa, continuing the workshop with Nisa. Nisa Bostancı is a third-year PhD student in the Safari Research Group at ETH Zurich under the supervision of Professor Mutlu. She's broadly interested in computer architecture and tackling interesting problems of current and future systems. Her recent work focuses on memory systems, particularly their security, reliability, and safety, and designing effective and efficient solutions to address robustness issues. Recently, she has been working on low-cost and scalable RowHammer mitigation techniques to improve the robustness of DRAM-based computing systems. She's also interested in exploring the robustness of emerging computing paradigms and future systems, such as processing in memory against vulnerabilities. Nisa, please go ahead.
Thanks, Ataberk, for the introduction, and thanks everyone for staying until this point. You made it. And this is the last part that we will cover today. And the title of my talk is Low-Cost RowHammer Defenses and Their Leak Sites. Okay, so Ataberk already introduced me, but I'm a PhD student at ETH, working with Safari, and I'm broadly interested in computer architecture. And in this part of the talk, I will wrap up the low-cost solutions to, yes. Is it better now? Yes. Okay. So in this part of the talk, I will first wrap up the low-cost mitigations part with presenting COMET, company sketch-based row tracking to mitigate RowHammer at low cost. And after that, I will also describe how we can exploit these low-cost mitigations to leak secrets or to establish covered communication channels. And the title of this part of the talk will be, the paper's title will be Understanding and Mitigating Covered and Side Channel Vulnerabilities Introduced by RowHammer Defenses. Okay, so let's start with the first paper, which is called COMET, Company Sketch-Based Row Tracking to Mitigate RowHammer at Low Cost. I'll start with a brief executive summary. As DRAM becomes more vulnerable to read disturbance, existing RowHammer mitigation techniques either prevent bit flips at low performance cost but with high area overheads, or at low area cost but with prohibitively large performance and energy overheads. And our goal in this work is to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. Our key idea is to use low-cost and scalable hash-based counters to accurately track DRAM row activations. And to this end, we propose COMET, which tracks most DRAM rows with scalable hash-based counters by employing the company sketch technique to achieve a low area cost. And it tracks only a small set of DRAM rows that are activated many times with highly accurate per DRAM row activation counters to reduce the performance penalties. And our comprehensive evaluations show that COMET achieves a good trade-off between area, performance, and energy costs by incurring significantly less area overhead and outperforming the state-of-the-art mitigation techniques. And COMET is open sourced and artifact evaluated, and you can access all our data and source code from this link. And this is the outline of this part of the talk. I'll continue with the background and the problem. And I'm sure you're very familiar with this at this point. Today's DRAM chips are vulnerable to read disturbance where repeatedly opening and closing or activating and precharging the same DRAM row results in bit flips in nearby DRAM cells, which we call RowHammer bit flips. We call the activated or hammered row as the aggressor row, and all the other rows that are affected are called victim rows. And we call them minimum number of activations that cause the bit flip the RowHammer threshold. And unfortunately, DRAM chips are getting more and more vulnerable to read disturbance today, which means that read disturbance bit flips occur at much lower activation counts. And these two More recent works show that the RowHammer threshold has reduced more than 2 orders of magnitude in less than a decade. And this is exactly why we need mitigation techniques against read disturbance attacks that are effective and efficient for highly vulnerable DRAM-based systems. And one way to mitigate RowHammer is to preventively refresh potential victim rows before they experience bit flips. However, doing so requires tracking DRAM row activation counts of these aggressor rows to identify and preventively refresh potential victims. And let's look at an overview of existing RowHammer mitigations that track DRAM row activations. The first approach allocates 1 activation counter per DRAM row such that each counter stores the exact activation count of its corresponding row. And the mitigations that use this tracking approach has very low performance and energy costs because they preventively refresh victim rows when it's precisely required. However, they also incur very high area costs simply because we have many DRAM rows in today's DRAM devices, and we need to implement many counters. The second approach leverages the key observation that an attacker can only hammer a small set of these DRAM rows before these DRAM rows are refreshed and allocates 1 activation counter per potential aggressor row. And this reduces the number of counters that we need in the system. And the mitigations that use this approach have low performance and energy costs because still the mitigation preventively refreshes potential victims when it is needed. However, especially at low RowHammer thresholds, these mitigations still incur high overheads. And this is because first, the number of potential aggressor rows increases significantly as we go to the lower RowHammer thresholds. And these counters are often implemented with expensive structures like content addressable memory because we need to associate each counter with a specific DRAM row using tags. And the last approach allocates less than 1 counter per DRAM row by introducing shared counters that track multiple DRAM rows at once, or by introducing probabilistic preventive refreshes. And basically, they reduce the number of counters needed in the system. So this is why they have low area costs. However, this comes at the cost of high performance and energy consumption overheads because they introduce redundant or not needed preventive actions. And they more and more use the DRAM bandwidth to do the preventive actions. And ideally, we would like to achieve low energy consumption, low processor chip and DRAM area overhead, and low performance overheads. And as you can see from this radar chart with the state-of-the-art mitigations, none of the existing mitigation techniques prevents RowHammer at low area, performance, and energy costs at the same time. And our goal is to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. We observe that there are 2 types of counters that can be used to track activation counts. First are hash-based counters that are low cost, and the second are tag-based counters that are highly accurate. And ideally, we want to get the best of both worlds and achieve low cost and high accuracy at the same time. Now let me explain how these work. Hash-based counters map each DRAM row to a counter in the counter array using fhash function. And they use the row ID as the input for this function and take the output and use it as an index for the counter array. This gives us 2 main advantages. First, hash-based counters can be implemented with low-cost structures because they don't need to store any tags. They just use a function and the output of the function to do the mapping. And second, they can aggregate many DRAM rows activation counts together and represent them with a fixed number of counters. And these 2 reasons make them very low cost. And as you can also imagine, this means that since we have fixed number of counters, this means that we map some of these counters to the same some of these DRAM rows to the same counters. Meaning that in this example, when we activate row 0, we also increment the activation count of row 4. And this introduces some inaccuracies. Tag-based counters are very good in that sense because they are highly accurate because each of these tag-based counters tracks only 1 row's activation count. And we store the tag of the DRAM row associated with the counter, and the counter has the exact activation count. And this is how we get high accuracy. By using this observation, our key idea is to first use low-cost and scalable hash-based counters to track most DRAM rows activations with low area overhead. And second, use highly accurate tag-based counters to track only a small set of DRAM rows to achieve low performance overhead. and we introduced Comet. Let me give you a brief overview. So Comet has two key structures. The first one is called counter table, which maps each of these DRAM rows to a group of low-cost hash-based counters as uniquely as possible by employing the count min sketch technique, which is a frequent item counting technique that I will be explaining in a second. And the counter table triggers a preventive refresh to an aggressor row's victim rows when the aggressor's counter group reaches an activation threshold. And by doing so, the counter table tracks DRAM row activations at low area cost. And the second structure is called recent aggressor table, which allocates highly accurate per DRAM row counters for only a small set of DRAM rows that are activated many times. And by doing so, recent aggressor table reduces performance penalties by increasing the tracking accuracy. Let's look at a high-level summary of how Comet operates. When there's an activation to row A, Comet first checks the counter table that implements hash-based counters and gets an estimation based on the counter table. And at the same time, it checks the recent aggressor table that has the tag-based counters that are highly accurate and gets another estimation from this structure. And Comet uses the recent aggressor table-based estimation when there's a tag match because these tag-based counters are more accurate compared to the counter table. After that, Comet compares this estimation to a preventive refresh threshold and preventively refreshes row A's victim rows if the estimation reaches this threshold value. Now let's look into the counter table in more detail. The counter table employs the count min sketch technique, which is a hash-based frequent item counting technique that uses multiple hash functions and a counter array per hash function. When we have sorry. Was there a question? No. Okay. When we have an activation to row A, counter table first gets the output of the hash function and uses it as an index for the counter array, which basically maps the DRAM row to one of these counters. And in this case, it's counter 0. And the counter table increments that counter. When we have another activation to the same row, the hash function will output the same thing, and we will increment the same counter. When we have an activation to a different row, ideally the hash function will result in a different output, which maps this DRAM row to another counter, and the counter table increments that counter. Since we have a fixed number of counters, sometimes these rows, some of the rows can be mapped to the same counter, and in this example, an activation to row C results in the same hash output and maps it to the same counter as the row A, and increments that counter. And this is called a counter collision. A counter collision causes overestimations because if we were to use these counters to estimate the activation count of row A, we would estimate it as 3, but in reality, we only activated row A 2 times. And we don't want to do that. So to avoid overestimations, counter table implements multiple hash functions that map each of these DRAM rows to different counters in these different counter arrays. As a result, each DRAM row is mapped to a counter group as uniquely as possible, as you can see from this example. And when there's an activation to a row, all counters in the counter group that is corresponding to that row is incremented. They are incremented. And therefore, the minimum counter value becomes an upper bound for the actual activation count. So the counter table estimates the activation count as the minimum counter value within that counter group. And in this example, this leads to estimating the activation count of row A as 2, which is the actual activation count. Comet sets the preventive refresh threshold to timely refresh an aggressor row's victim rows to prevent bit flips. And here we have an activation to row A, and then the counter table estimates the activation count after this activation as the threshold value. At this point, Comet identifies this row as an aggressor row and preventively refreshes A's victim rows. After this point, since the victims are already refreshed, we would consider resetting these counters, right? Because they are now refreshed and we can start over. However, doing so affects the shared counters such that, for example, the row C's counter group could be affected by that, and we could estimate the activation count of row C as 0, even though it is activated many more times. To avoid this, Comet does not reset counters after preventive refresh and employs a secure periodic counter reset mechanism that is explained in more detail in the paper. Since Comet does not reset any counter after preventive refreshes, this means that these counters saturate at the threshold value. And let's say that we preventively refreshed A's victim rows. This means that these counters stays at the threshold value, and when we have an activation row A, this can again trigger estimating the activation count as the threshold value and result in preventive refreshes that are not needed. So this can potentially incur performance and energy overheads. However, if we knew in the past we already preventively refreshed A's victim rows and the actual activation count after the preventive refresh is much lower, we could have avoided that. And the recent aggressor table does exactly that. It allocates per DRAM row counters to aggressor rows to accurately estimate their activation counts after preventive refreshes. Let's say that we identify A as an aggressor row and preventively refresh its victims. We allocate a recent aggressor table entry and start the counter value from 0. And after this point, whenever we activate row A, we would get a tag match, and the estimation would be 100% accurate because this counter is not shared across other DRAM rows. And we only implement this for a small set of DRAM rows to maintain the low area cost of Comet. And this was the overview of how Comet operates. And there are more operational details in the paper, including counter update policy, periodic counter reset mechanism, recent aggressor table eviction policy, and many more other details. And you can check them from our paper. Let's move on to the evaluation. So we evaluate the performance and energy consumption using cycle level simulations with emulator and DRAM power. We use these system configurations and we compare Comet against 4 state-of-the-art RowHammer mitigations. Ataberk also covered those, but let me just go over them. Graphene is the best performing one, but it has high area cost. Hydra is area optimized best performing one, which has, again, a lower area cost and a lower a higher performance cost than graphene. And we also have Rega and Para. And we compare this across many single core applications and many multi-core workload mixes. And all of these can be accessed from this link. Let's first talk about the hardware implementation. We evaluate the storage and area overheads using cacti, and this is the area overhead comparison against graphene and Hydra. And here we have 2 different RowHammer thresholds that are decreasing, and this is the area overhead of Comet. And as you can see, as we go to lower RowHammer thresholds, Comet has a lower area overhead. This is because it needs to store fewer bits for its counters as we go to lower RowHammer thresholds. And this is the area overhead of graphene, which is significantly higher than Comet's area overhead. And this is the area overhead of Hydra, which is pretty much similar to Comet's. And it is good to note here that Hydra also has in DRAM counters. Basically, this is just the memory controller area overhead. And we conclude that Comet incurs a significantly less area overhead than graphene and a similar area overhead to Hydra. We evaluate the average performance and DRAM energy overheads of Comet across single core applications, and this is Comet's performance normalized to a system with no RowHammer mitigation across different RowHammer thresholds. And as the RowHammer threshold decreases, Comet has a small performance overhead due to preventive refreshes as opposed to the baseline that does not do any preventive refreshes. And this is Comet's DRAM energy consumption normalized to the same baseline, and it shows a similar result. And we conclude that Comet prevents bit flips with very small average performance and DRAM energy overheads compared to the baseline with no RowHammer mitigation. And let's look at the performance comparison across single core applications. Again, we have decreasing RowHammer thresholds on the x-axis, and on the y-axis, we have the IPC distribution normalized to the baseline with no RowHammer mitigation. And these are the results for the threshold of 1K. And as we go to lower RowHammer thresholds, all mitigations start to perform preventive refreshes, and they incur more performance overheads. And we make 2 key observations. First, Comet outperforms all low area cost mitigations starting from the RowHammer threshold of 500. And It also incurs a small performance overhead over graphene and outperforms Hydra at all RowHammer thresholds. And we also compare the performance across multi-core workloads, and the trends are very similar to single-core application evaluation trends. Let's look at the DRAM energy comparison across single-core applications. Again, we have decrease in RowHammer thresholds on the x-axis, and on the y-axis, we have the energy distribution. And these are the results. We make two key observations. First, Comet consumes less DRAM energy than all low area cost mitigations for all RowHammer thresholds. And it also incurs a small DRAM energy overhead over graphene and consumes less DRAM energy than Hydra. And the multi-core results, the trends are very similar to the single-core one. Okay, so we have more analysis and results in the paper. We have a security analysis of Comet showing that it prevents all RowHammer bit flips at all RowHammer thresholds. We have a sensitivity analysis sweeping different design parameters of the different structures in Comet. We also evaluate the performance under adversarial workloads, showing that targeted attacks can incur performance overheads for all of these different mitigation techniques. We have a comparison against throttling-based mitigation techniques and other analysis with higher RowHammer threshold values. And these are all in the paper. Again, Comet is open source and artifact evaluated, and you can check our repo. And let me conclude this part of my talk. So our goal was to prevent RowHammer bit flips with low area, performance, and energy overheads in highly RowHammer vulnerable DRAM-based systems. The key idea is to use low-cost and scalable hash-based counters to accurately track DRAM row activations. And we introduced Comet, which tracks most DRAM rows with scalable hash-based counters by employing the count missketch technique to achieve a low area cost. And it tracks only a small set of DRAM rows that are activated many times with highly accurate per DRAM row activation counters to reduce the performance penalties. Our evaluations show that Comet achieves a good trade-off between area, performance, and energy costs by incurring significantly less area overhead and outperforming the state-of-the-art mitigation techniques. And this brings us to the end of this part. Are there any questions? Yes.
So on the slide 33, you show the area overhead.
33. Let me go back. Many slides. Here?
No,
or
33.
Oh, sorry, yes.
Yeah, so my question is, so first, is it safe to assume that when you go from 1K to 125, you will have to do a lot more resets normally, right?
Mm-hmm.
So that would mean you need a larger recent aggressor table.
We looked into different design parameters. We sweep the size, and we did not see that benign workloads need a larger recent aggressor table. Our intuition was the same, that it might be a good idea to scale it for the lower RowHammer thresholds, but we don't observe the need for benign workloads. But for maybe targeted attacks, that might be a good idea to reduce the overheads of counter saturation or increase the benefit of the recent aggressor table.
Okay, I see.
Maybe I can also show you the results regarding that, if I can find them. Okay. So yeah, in the second part here, we sweep these number of recent aggressor table entries, and as you can see, it has some benefits for the worst case performance overheads, but overall the average is very close to each other for these workloads at least.
I see. Then could we say the hash table based counters are doing most of the work then? And RET is not helping much with inducing performance overheads?
We can say that. We can say that for benign workloads, we don't see much evictions because of the capacity of the recent aggressor table. So yes, hash-based counters are maybe doing the heavy lifting, and maybe they're they don't have many collisions that are causing, like more preventive refreshes. Yeah, so.
Okay, I will ask the obvious question.
Yes.
Now we have Prague. Isn't this useless?
So it's not useless, first because Prague is right now an optional feature and it will be only adopted in future DRAM devices. These can be used in for today's DRAM devices in systems that we have today if they are implemented. Also, I guess like we should also see the implementations of Prague to see that if it's like completely secure. And we also we provide security analysis and proofs for these works that are basically memory controller side mitigations. And we know that they prevent all RowHammer with flips, but right now we don't have that for the implementations of Prague.
So you speak very confidently about Prague being optional and not implemented in many chips. So
as far as we know.
So did you test real DDR5 modules and try to see if Prague is implemented or not?
So we checked some metadata that the manufacturers share. It's fairly new, like it was introduced last year in April, right? So we didn't see any devices supporting that. We also looked into other mitigations that are in the specification, like refresh management, RFM. And we also couldn't find many DRAM devices that are supporting that or like requiring that officially. So we did some experiments. We did not see those mitigations are being employed necessarily with our tests. Maybe we were not able to trigger them. Maybe the overheads would be maybe like hidden or something. So maybe we couldn't observe them. But overall, our understanding is that they are not widely adopted right now with the modules that we have available to us.
Okay, that's fair, I guess. So another question is, so essentially we use hash-based mapping here to reduce the number of counters that we need to implement. And the paper widely, I guess, assumes that this is a memory controller-based implementation. So what would it take to implement this in the DRAM chip and like have those hash functions being mapped to some counters in the DRAM array? Would that work? Like it's more like a cheaper version of Prague.
Yeah.
Not in the quality sense, but in terms of like lower hardware complexity.
I think it would definitely reduce the number of counters that needs to be implemented. So in that sense, yes. I don't know if that's like a concern because they're going forward with this like per row activation counters as we know of. But yeah, that would, I think, definitely reduce the area overhead for those counters or like the capacity overhead if they are stored in DRAM rows that can be used for other things. So yeah, I think that would be interesting. Performance-wise, I'm not sure. So having per row activation counters gives us this like perfect tracking ability. So that reduces the unnecessary preventive refreshes a lot from like our experiments with in different papers. But yeah, so these kind of like grouping sort of introduces these inaccuracies by definition. So maybe there's this trade-off there again.
So you would have a larger rate of false positives. Well, you don't have any false positives in Prague anyway. But yeah.
Yeah.
Okay. Makes sense. Yeah. And what would we need to do with RAT if we implement this in DRAM?
That's also a good question.
Does it require some sort of like CAM implementation?
Yeah, so we assume in this implementation that it uses CAM because we need to associate like different DRAM rows at runtime to different counters. So that might be a bit more challenging maybe. Or I don't know, maybe you could store the metadata, and if you can operate with it quickly, maybe you don't need it, but that's again costly, I think.
I see, okay. Yeah, it makes sense. I guess it's worth looking at anyway. Yeah, that's all from me. Thanks.
Okay. No other questions? Then I'll continue with the second paper. So again, this sort of concludes this low-cost RowHammer mitigations that we will discuss in this workshop. Again, we talked about like prac or industry solutions. So the next paper will be focusing more on that, evaluating, understanding and mitigating the vulnerabilities that might be introduced by these defenses. So yeah, let me cover some background as well. So dynamic random access memory, or DRAM, is the prevalent memory technology today, and DRAM stores a bit of data in the form of electrical charge on a capacitor, and to access via a sort of wire called the word line, which enables a transistor conducting the capacitor to another wire called bit line. And DRAM is a volatile memory technology as it leaks charge over time and needs to be periodically refreshed. And accessing a DRAM cell disturbs other physically nearby cells and exacerbates their charge leakage, and this is called DRAM read disturbance. A prime example of this is RowHammer, and I will just quickly refresh your minds. Quickly opening and closing and repeatedly doing so the same row results in bit flips in nearby DRAM cells, which we call RowHammer bit flips, and we call the hammered row as the aggressor row, and the other rows are called victim rows. And why this is important? Because read disturbance breaks memory isolation, which is a fundamental primitive for system security and privacy. With read disturbance, a memory access has unintended side effects on data stored in other addresses. And we would not want to have this because it leads to data loss or corruption, compromise application correctness. It can be used to leak private information or even take over a computer. And these are all demonstrated in prior works that we all mentioned and discussed today. And therefore, mitigating read disturbance bit flips is very important. One way to mitigate them is to preventively refresh potential victim rows before they experience bit flips, but doing so requires tracking the DRAM row activation counts of aggressor rows to identify which rows to preventively refresh. And to make things worse, with technology not scaling, DRAM cells are getting smaller in size and closer to each other, such that we observe significant reductions in the minimum hammer count induced first bit flip. And thus, DRAM cells become increasingly more vulnerable to read disturbance and requiring low-cost mitigations. I'm assuming that you are all sort of convinced with that. This is exactly why recent DDR5 specifications introduced new mitigation frameworks. One of them is called per row activation counting, in short prac, as of April last year. What it does is it introduces or implements this per row activation counters in DRAM to accurately identify aggressor rows. And the second one is called refresh management, which was even introduced before that, before prac. And this one introduces a command to provide DRAM with the time for performing preventive actions. And the problem is the industry has already adopted multiple RowHammer mitigations, yet their full security implications are not known to us. And this brings us to the question that do industrial and academic RowHammer mitigations introduce new covert and side channel vulnerabilities? In this work, we show that, unfortunately, the answer is yes. We make the key observation that RowHammer preventive actions such as refreshes, preventive refreshes, have two fundamental features that enable covert and side channels. First, these actions often result in significantly high memory access latencies for regular memory requests, such that let's say that we have this DRAM module that supports prac. This operation has a high latency, and while the DRAM module is doing this preventive action, all other requests needs to wait for the DRAM to become available again, such that they all experience higher memory access latencies. And the second reason is that preventive actions can be triggered on demand as they highly depend on memory access patterns. That means that an attacker can craft memory requests to the same region in DRAM, practically hammering that DRAM region or that DRAM row, triggering preventive actions. And all other requests that are coming from other applications or from the same application, they also experience higher memory access latencies. And using this key observation, we introduced LeakHammer, which is a new class of attacks that exploit RowHammer mitigation-induced memory latency differences. And the key idea of LeakHammer is to first deterministically impose high latency on memory requests with preventive actions by triggering them on demand. And second, accurately infer victims' memory access patterns that result in preventive actions by observing the preventive actions that are happening in the system. And in this paper, we have 3 case studies. The first 2 establish PRAC and RFM-based covered communication channels. And in the last one, we demonstrate a website fingerprinting attack that leaks which website is loaded by a victim user by just observing the preventive actions caused by the victim process. And before moving on to these case studies, I want to first describe our evaluation methodology. Just now we talked about how these are not widely adopted. These mitigations are not widely available to us. This is why we simulate systems with these mitigations using Gen5 and integrated with Remulator 2. And these are the system configurations that we use to simulate such a system. And in our threat model, we assume that attack processes can first only share the main memory, meaning that they don't share actual data, but they just use the main memory at around the same time. They can flash cache lines and measure time with special instructions. And they can also collocate pages in the same DRAM bank by partially reverse engineering the address mapping. So the last one is not necessary for all types of attacks, and I will describe them later, but it makes explaining things easier, so we will just assume it for now. And let's move on to the first case study, PRAC-based covered channel attack. Before moving on, I will describe PRAC per row activation counting as introduced in the specification quickly. Here we have a CPU with a DRAM module, and inside the DRAM module, we have many DRAM rows. And what PRAC does is it implements one activation counter per DRAM row inside the DRAM to accurately track the activation counts of these DRAM rows. And the PRAC-based mitigation works as follows. So let's say that we have a row that is activated. PRAC increments the counter corresponding to that row and keeps incrementing the same counter with each activation. After some point, this counter reaches a threshold called the backoff threshold, which means that the row now requires a preventive action to prevent bit flips from happening. And PRAC identifies this row as an aggressor row. And after that, the DRAM module sends the memory controller a backoff signal. And upon receiving the signal, the memory controller issues an RFM command, which basically gives the DRAM module the time to perform preventive refreshes. And during this time window, the memory controller does not send any other command, any other regular memory request to the DRAM module. And during this time, DRAM becomes unavailable and performs preventive refreshes. And after these are done, after this time window ends, DRAM becomes available again, and the memory controller continues to issue other commands. So to exploit this for an attack, we first need to verify if we can observe PRAC-induced latencies. We test if an application can deterministically trigger a PRAC backoff and observe higher memory access latencies caused by it. And to do so, we first allocate pages in different rows of a DRAM bank, and let's say address A and B. This means that they don't share any data again, they just share the DRAM bank. And after they collocate their pages in the same DRAM bank, after we collocate these at the same DRAM bank, we basically first flash address A. This ensures that the next accesses will go to the main memory with more chance. And after that, we read address A and measure the access latency to do so. And this results in activating the corresponding row. And in the last step, we do the same for address B. And since these addresses are in the same DRAM bank, but in different DRAM rows, they conflict in the row buffer. And this results in activating each of these DRAM rows. And by repeating this, we increment the activation counters for both of these DRAM rows. And now let me show you what we measured. So on the x-axis, we see a window of 512 memory requests. Basically, it's a random window throughout the execution. And on the y-axis, we have the measured memory request latencies. And these are the results. We split the measured access latencies empirically into 3 categories. From highest to the lowest, we have track backoff, we have periodic refresh, and row buffer conflict latencies. And we make 2 key observations. So first, we can identify backoffs as the highest peaks in this figure, which is consistent with the specifications latency defined. And this can be distinguished from regular memory requests because it is significantly higher. Second, these peaks are exactly 255 memory requests apart, which is 2x of the backoff threshold used in this experiment, which means that activating each of the test rows threshold times results in higher memory access latencies consistently. So this experiment shows that PRAC creates a promising timing channel to build timing-based attacks. And now let's see an overview of the cover channel attack. We have a sender and a receiver process, and the sender wants to send this message. And they collocate their data in the same DRAM bank by basically having pages in different DRAM rows within the same DRAM bank. And they agree on transmitting this message using transmission windows. During each of these transmission windows, the sender will be transmitting just 1 bit, and the receiver will try to determine the value of that bit. And they also agree on an encoding, such as logic 1 value means a backoff, or a logic 0 will be transmitted with no backoff, and so on. And to receive the message, the receiver needs to perform accesses to its own row. Within a loop, it just sends accesses to the same row again and again, and times these accesses such that it will get this sort of a trace of memory access latencies. And then the receiver will use this to determine the bit value. To send the logic 1-0, the sender needs to trigger a backoff. So to do so, the sender hammers its own row. And since the receiver and the sender are active in the same DRAM bank, they create row buffer conflicts, and this results in activations and increasing the activation counters for both rows. And after some point, they hit the threshold value, and the DRAM module sends a backoff signal. And at this point, the receiver will measure a higher memory latency for its own request. And after that, it can understand that there was a backoff and determine the bit value as the logic 1 value. And to send the logic 0 value, the sender needs to trigger no backoffs, meaning that it can sleep for the transmission window. And if the sender is inactive, the receiver will access its own row, but this will result in row buffer hits. And then the activation counter will not be increased by a lot, meaning that the DRAM module will not raise the backoff signal. And in this transmission window, the receiver will have this sort of stable memory access latencies measured. And then it can detect no backoff and then determine the bit value as a logic 0 value. And they continue for all transmission windows to complete the whole message. And we validate this proof of concept by transmitting a 40-bit message. And here we are just visualizing some stuff. So on the x-axis, we have the transmission windows. And on the y-axis, we have the number of accesses measured by the receiver within these transmission windows. So what this means is, if we observe a lower number of accesses closer to the threshold value, this means that there was a backoff. And if the receiver can access the memory many times, this means that there was no backoff and there were many row buffer hits. And these are the results. And they corresponding to the bit values the sender wanted to transmit. And we conclude that the receiver can successfully decode the sender's message after completing these transmission windows. We also measure the channel capacity of this covered channel by sending a longer message with different data patterns. And we observe that the attack achieves a 38.6 kilobits per second raw bit rate. And after that, we evaluate how noise impacts this covered channel capacity or like this transmission of a message. And we use a noise generator micro benchmark to evaluate this. And this noise generator micro benchmark hammers a row in the same DRAM bank used for the attack with varying back-off intensities, basically creating noise in the receiver's measurements. And these will be showing the results. So on the x-axis, again, we have the increasing noise intensities. The lowest value here corresponds to 10x of a 4-core memory intensive workload in terms of back-off characteristics. And when we go to higher values, it gets more similar to a back-off intensity or like back-off memory performance attack. And on the primary y-axis, we have the error probability. And on the secondary one, we will see the channel capacity. And these are the results. We have two key observations. The first one is that at the lowest noise intensity level, these are the error probability and the channel capacity numbers. As you can see, the error probability is fairly low, meaning that we can transmit messages with high rate. Yes. And when we go to higher noise intensities, the error probability increases because there is this noise impacting the receiver's ability to detect backoffs or like extra backoffs to basically make the transmitted bit value seen as a logic 1 value. And again, this level is very similar to having a memory performance attack based on PRAC. So we also don't want to have this in our regular systems anyway. So it is very high. And we conclude that the PRAC-based covered channel attack maintains its capacity until a very high noise intensity value. So yes.
So yes. So in your covered channel attack, you use a one DRAM bank, right? So you locate sender and receiver in the same DRAM bank.
Yes.
So in this case, can we use bank level parallelism to increase the channel capacity, like the throughput that you observe by like collocating, for example, you have 32 banks, right?
Mm-hmm.
Can we just easily say that can we multiply by this value with 32?
So for this covered channel attack, since we are assuming a PRAC-based underlying system, that's not possible because a backoff basically blocks the whole DRAM module. And basically having more sender and receiver pairs in different DRAM banks, we didn't try it, but they would be affected by each other's backoffs. So they would observe the same backoffs in their transmission windows. Does that make sense? Like,
yeah, but what I was asking is like your setup will be increased setup time. So because you'll make 32 banks to near the threshold. And then, for example, in a transmission window, you will count the number of backoffs, something like that. That's what I had in mind, but I don't know if maybe it's too naive.
That could help. Basically, the setup time, you mean like the sender would be preparing some
preparing near the threshold or something.
I think that can work if a backoff. Basically, we need to take the number of preventive refreshes happening inside each DRAM bank into account in that case. But that could also work. At this covered channel example, the sender and receiver execute at the same time. So they create conflicts with each other by executing at the same time. But if we need to prepare rows before that, they might need to synchronize. So that might be a challenge in that case.
It will increase the sync. I see.
That might require an effort, at least.
Okay. And maybe one more thing as well. So I'm not sure if PRAC is like blocks the whole rank or whole channel, but if it's the rank, in this case, for example, there are many dual rank modules, right? So, for example, for that one, we could actually increase the throughput by 2
Yes.
times with using dual rank setup.
Yes. So maybe I can also answer it this way. Since in this example, we are assuming PRAC and assuming that it blocks the whole channel as it is described right now, that it might be challenging to have multiple senders and receivers to increase the throughput. But if we had other mitigations or like other versions of PRAC that doesn't block the whole DRAM module altogether or like just blocks one bank at a time, then we are not bound by that. So the attack can be much faster in that case. So yeah. And the underlying observation of a preventive action being observable from user space applications, it applies to other mitigations as well, not just PRAC. So maybe having another mitigation that doesn't have the same limitation would allow such a high throughput attack.
Yeah, makes sense. Thanks.
If there are no other questions, I'll continue with the second case study, which I will cover relatively faster. So this one is based on, yes.
I actually got distracted, so I'm not sure if I'm going to ask the same question, but I'll ask regardless. So this PRAC-based covered channel attack is based on like trigger and PRAC, right? And like in the morning, I briefly mentioned RowHammer, which was also observing which thread was trigger and PRAC and throttling them down.
Mm-hmm.
So let's say your sender is trigger and PRAC, or like they contribute to each other actually, but yeah, somehow they like the two threads work together on trigger and PRAC, and let's say we have RowHammer implemented in our system. Would that reduce the channel bandwidth significantly?
Yeah, so basically RowHammer would be identifying each of these threads, attack threads or processes as attackers and then throttle them. And I think that would reduce the channel capacity a lot. I'm also thinking, is it possible to leak something based on that throttling action? But I guess that requires more thinking because it's like a process-based thing, right? You would only observe that you are throttled, maybe not other processes. So.
Oh, okay, so being throttled is also another sign for you to convey your message.
Maybe
in a covered channel.
I think that's more challenging, but maybe if you can understand, like, maybe you can construct them like a covered channel based on that. But maybe
Makes
it's
sense.
like isolated to one like receiver. Receiver could understand that it is own like process is being throttled. So maybe that's not very useful, but.
Mm-hmm. I had another question as well, actually. Should I ask now?
Sure.
Maybe now. So, so you say that you observe like PRAC being triggered as the thing again, but at the same time, these accesses also create a higher fraction of row buffer conflicts, right?
Mm-hmm.
So there are also other covered channels that are based on row buffer hits and conflicts.
Mm-hmm.
So what fraction of your channel bandwidth comes from that? Like, because when you measure the latency of your own memory request as a receiver,
Mm-hmm.
you can also detect that as like some increased latency, and maybe they are also helping, you know. So do you know like what fraction is purely coming from PRAC and what fraction is also from row buffer conflicts?
So I think by definition, all of the backups that we observe also include the conflict latency, because it should happen after an activation, and activations usually happen if you are executing a lot of things they're usually happening after a conflict. So I think what we measure already includes the latency of a conflict as well. But since the latency of a backoff is significantly higher than the conflict difference compared to like a row buffer hit, for example, I think it is easier to detect a backoff in that sense. So having a conflict latency on top of that wouldn't make it any more easier to detect, I think.
So does it give you more resilience against noise?
We evaluated. So we compare RowHammer against DRAM, which is like which is the state-of-the-art row buffer-based attack. The difference is that in DRAM, in theory, each conflict could leak a bit, having one conflict even, but that's very susceptible to noise, right? You could measure something else, or like you could have different things and so on. You could have interference as well. This is why they repeat it in transmission windows. So since they're repeating, they're increasing their resilience against noise. And we didn't observe any significant improvement from measuring the backoff latency, but maybe since we are doing this in simulation, maybe we don't see that much noise, even though we use the noise generator benchmark, maybe we are not getting a lot of noise that would make DRAM more prone to noise or like more errors.
Okay. Yeah, I wish that would be like a very like nice fair comparison, like in a real system, probably, but of RowHammer and DRAM, so that we can understand for the like same noise level, for example, which one gets higher throughput or.
Yeah, I think for that we might need the real devices with Prague. I think that would give more insights into like how this is, like if this is significantly worse than DRAM as a security scenario. But I think in this work we also highlight that this is a different timing channel than the row buffer itself. So there are different like trade-offs in the sense of attacks. Like in the side channel, for example, DRAM needs to collocate either at the same row level or at the bank level, which we don't really need to do. We just need to collocate in the same DRAM module, which is a very like low effort in comparison, and we can leak like information to understand like websites and so on, right? And we didn't observe the same capability with DRAM, for example. So I think apart from the covered channel capacity, there are like different things that we can evaluate these attacks with that are not easy to quantify. It's just like different ways of security thinking, sort of.
Yeah, that makes sense. So as long as you collocate your data in the same rank, it should work, right?
Yes.
Or is it in the same channel?
So we double check that like alert and signal. I think it's either in the same channel or even like higher level sort of. Which...
Oh, not even ranked then.
Yeah, yeah.
Okay, it's really like a module. Okay.
Mm-hmm.
Okay, yeah, that makes sense. And you really didn't find any device that implements Prague?
Not yet.
Okay, thanks.
But we're still looking, I guess.
Okay, thanks.
Okay. So, okay, let's talk about the second covered channel attack, which is based on refresh management. So I will talk about periodic refresh management as described in the specification. Again, we have our CPU and our DRAM module. And inside the DRAM module, we have different banks, and inside them we have DRAM rows. And as a difference to Prague is basically in this case, we have per bank counters, which means that all of these DRAM rows are mapped to one bank level counter, since they are in the same DRAM bank. And how this works is, let's say that we have an activations row A, the counter for bank 1 will be incremented, and all other activations to the same DRAM bank will increment that counter as well. And after a point, the counter will reach a threshold called the RFM threshold, which then the memory controller identifies this bank as needing preventive action. So then the memory controller takes the action of sending an RFM command, which gives DRAM the time to do the preventive refreshes, and during which the DRAM module becomes unavailable again. And after this point, the DRAM module does the preventive refreshes. And after that, after the RFM period ends, the memory controller continues to send more requests. So we also exploit this. I will just give a brief overview in the interest of time. And we first verified that applications can deterministically trigger RFM and observe high latencies caused by it. And probably you also thought about it, since we have this bank level counters, this RFM-based mitigation called PRFM is more susceptible to noise, which then required us to change the attack slightly. So we decided to count the number of RFMs within a transmission window from the receiver side and set a threshold based on that. And that cancels out some noise we have. And this is maybe this is too small, but this is the proof of concept. Here you can see that it's very noisy, like we measure different counts of RFMs in transmission windows, even though the sender is doing just one, like one action for each of these bit values. And we were still able to decode the message from the receiver side by setting a good threshold for the count of the number of RFMs observed. And we also did the same noise test for this covered channel. And here what I want to highlight is that the error probability increases to a higher value at lower noise intensity levels. So this means that this channel is really more susceptible to noise, and having more applications or like system level noise generators would impact the channel capacity even more. But again, we were still able to get good capacity for half of this noise intensities that we evaluated. And more details are in the paper. I would suggest you to read it if you're interested in this attack more. Let me talk about the side channel attack, which is maybe more interesting. So this is a website fingerprinting attack based on PRAC. And in this attack, we have an attacker and a victim process. The victim process loads websites using a web browser. They're not aware of anything. And the attacker wants to determine which website the victim loads by observing its own memory latencies. So they share the DRAM module, meaning that they don't need to collocate in the same bank or in the same row or anything, as a backoff affects the whole rank or even like higher levels of the DRAM organization. We first need to figure out how to fingerprint websites. So the attacker first does this test, does this routine, like first it allocates multiple test rows to avoid triggering backoff while observing. So it just creates these, it just has these different pages that it can access infrequently, such that PRAC won't do a backoff just by the receiver doing something. And after this, the attacker accesses the test rows continuously and measures access latencies to detect backoffs and gets a trace similar to the receiver process that we talked about. And in the last step, it creates a fingerprint using the timestamps of these backoffs that it detects. So each line here is a backoff that's triggered, and we just divided the execution to different windows to visualize this. And to prepare for the attack, the attacker first fingerprint many websites using a web browser. And here you can see some example fingerprints for Reddit, Wikipedia, and YouTube. And as you can see, these fingerprints, we have multiple instances of the same website, and these instances look like each other for the same websites. And when you look at like different websites from like the blue one to the red one, you can see some differences even by just checking them. And basically the attacker creates this fingerprint database by collecting fingerprints for the desired websites using a web browser. And let's launch the attack. So again, we have our victim and our attacker, and they're sharing the same DRAM module. First, the attacker gets a fingerprint when the victim loads the website. And here we see the fingerprint in question. And then after that, it just compares it with the database and determines the website. So it is fairly easy. And in this example, the website turns out to be YouTube. And to evaluate this, we created memory traces of a browser loading different websites to simulate the browser process. We currently have 40 most visited websites. We are also incrementing that number by getting more traces. And we create fingerprints using the fingerprinting routine we described. And in this proof of concept, we use the machine learning approach to classify websites. And we train simple and lightweight machine learning models and analyze their test accuracy. And here are the results. On the x-axis, we have the different ML models, and on the y-axis, we have the test accuracy. And these are the results that we got. And the red line here represents the random guess. Yeah, so you can see that using back-off-based fingerprints, we can achieve high classification accuracy with these classical machine learning models that are sort of simple models. And this concludes the case studies that I will talk about today. And one question still remains. It is that how can we mitigate leaky hammer? And in the paper, we proposed two countermeasures against leaky hammer. The first one is called fixed rate RFM, which is a fundamental solution that decouples preventive actions from memory access patterns of the running applications. And the second one is called randomly initialized activation counters, which is a lower cost countermeasure that reduces the channel capacity with the randomization method. So it does not fundamentally solve the leakage, but it just reduces the channel capacity to make the attack impractical to do. I will describe the first mitigation next. So fixed rate RFM just periodically performs a preventive action independently from the memory access patterns that the applications have. So we set this time period for these RFMs as the shortest time window needed to perform RFM threshold activations, which comes from a security analysis which is available in the paper. What is important here is that by employing this, a sender cannot we make the sender unable to cause preventive actions on demand to send messages. And an attacker also cannot observe a victim's memory access patterns that lead to preventive actions, because these preventive actions happen no matter what, and no application can cause extra preventive actions. And for more details, I refer you to the paper. And the second mitigation is randomly initialized activation counters, which initializes each of these activation counters with a random value upon performing a preventive action. What this does is it randomizes the number of activations needed to receive or observe a preventive action, such that the receiver observes errors in their measurements and cannot determine the bit values correctly. So this mitigation introduces noise in measurements and reduces channel capacity. And let's quickly look at the results, and we evaluate these 4 mitigation techniques across 4 core workloads. And on the y-axis, we have the weighted speed up normalized to a system with no RowHammer mitigation. And on the x-axis, we have the RowHammer thresholds decreasing from 1K to 64. And we evaluated first PRAC and PRFM, which are the baseline mitigations that we talked about today, which are not secure against leaky hammer. And next, we have the randomly initialized activation counters, which reduces the channel capacity by 86%, but it does not prevent leakage completely. We also evaluate fixed rate RFM, which is secure against leaky hammer and RowHammer at the same time. And these are the results. And we make 2 key observations. So first, fixed rate RFM mitigates leaky hammer with small performance overheads at near future RowHammer threshold values. So as you can see, it also performs similar to PRAC and PRFM for the higher RowHammer thresholds that we see in the figure. And as we go to lower RowHammer thresholds, mitigating leak hammer incurs large overheads, and it also requires further research. And as we go to lower threshold values, you can see that fixed rate RFM has a significant performance overhead, and having a reduced channel capacity comes at a lower performance cost. So we hope and believe that our work can enable more future work on low-cost mitigations that are designed to mitigate both leak hammer and RowHammer at the same time. We have more stuff in the paper, more operational details on case studies that I covered just briefly. We also explain how to establish multi-bit covered channels with PRAC. We have a sensitivity analysis of PRAC-based covered channel, an analysis of leak hammer with other RowHammer mitigations, and comparisons against other attacks, other timing attacks. And these can be found in the paper. Now let me conclude my talk. So in this work, we make the key observation that RowHammer preventive actions have two key features that enable covered and side channel attacks. First, they often result in significantly high memory access latencies for regular memory requests that can be observed by applications. And second, they can be triggered on demand as they highly depend on memory access patterns. And when we introduced leak hammer, which is a new class of timing attacks that exploit RowHammer mitigation-induced memory latency differences to first establish communication channels, and second, leak secrets from victim applications. We talked about 3 case studies after systematically analyzing 2 latest industry mitigations to RowHammer. First, we demonstrate 2 covered channel attacks exploiting 2 of these state-of-the-art mitigations. And we demonstrate a website fingerprinting attack that can identify websites with high accuracy by observing victims' preventive actions. We also talked about how to mitigate leak hammer and proposed 2 countermeasures, fixed rate RFM, which decouples preventive actions from memory access patterns, and randomly initialized activation counters, which is a countermeasure that reduces channel capacity. And that concludes this part of the talk, and also the talk in general today, I guess. If you have questions, I'd be happy to take them.
Any questions?
Yes.
You have a microphone, go ahead.
The slide where you showed different model architectures and their accuracies. So I was wondering, since the decision tree prevailed over there.
Yes.
Yeah.
Oops. Yeah.
Yeah.
This one.
So I was wondering, there are much more complex models compared to decision trees, and yet decision trees prevailed. So I was wondering, how much do you think it's a matter of training data size, for instance, that there is still a headroom, like room for improvement of 0.20 in terms of accuracy?
Yeah, so I think the size of the data set regarding we use like for the backoffs, if we had a larger data set, which requires more time to get them, that's another sort of point. But it would allow us to use more complicated models, as you also suggested. And then I think the accuracy of the classification would be higher based on this promising like result that we get with decision trees, right? And also like the others are also maybe not that bad, let's say. Yeah, so definitely we are looking forward to basically getting more traces and then getting more fingerprints and running more complicated models. But I also think that these results highlights the fact that it is not challenging to, or like it is promising to use backoffs as a fingerprint for websites that are loaded. So yeah, I think if you're interested, we could also work together to make that possible. But yeah, the main limitation was that it is very time consuming to get the traces and then simulate them and so on.
Other questions? So, okay, I had a few, but let me try to remember. So one thing is this study is too much focused on PRAC and RFM. And it's reasonable because those are like 2 state-of-the-art industrial solutions, and you expect them to appear in like upcoming DRAM chips. But there are also other proposals in the academia right? So just pick any mechanism. Comet is one of them. So from the memory controller, if you track and then you decide to do refresh, and then you send that refresh somehow to DRAM, you can use a specialized command for that, like near row refresh or target row refresh, or yeah, in the standards, there is this directed refresh management, DRFM now. So if you use one of those, like something like Comet, it can be Comet plus Abacus, I don't know, Hydra, Graphene, any refresh-based mechanism. So would you have similar issues in that case?
My answer would be yes. So in the paper, we also discussed what makes the mitigation leaky in this sense. So if the mitigation can be triggered on demand, basically based on some memory access patterns, which most of them do, and if the preventive action latency is observable or like significantly higher than regular memory request latencies, then it is possible to leak some information based on that. And we did not use them to evaluate this, but basically preventive actions regarding like preventive refreshes and so on, we know that they have high latencies that can be observed. And based on the mitigation technique, we can also construct like patterns to trigger them on demand. So those would be vulnerable. What would be challenging to exploit is more like probabilistic mitigations like para. So you wouldn't be able to trigger it on demand. I guess you would be able to have a lot of accesses and then increase the chance of seeing it, but I'm not sure what you would leak with that information. So it would be similar to contention in that sense.
I see, yeah. And similar to the RFM in that case, no?
Maybe, yeah.
Because it counts the activations at the bank level, so it's similar to para.
Maybe, yeah.
Okay. Yeah, that makes sense. Another question about this website fingerprint, HL2 of them. Do you only understand which domain you're accessing? Like you showed like Reddit and YouTube, for example. Can you tell me like which particular Reddit post I'm reading?
That we didn't try. That would be interesting. I'm not sure if the websites make different memory accesses based on the page that you're in. But I can imagine that being the case for example, Reddit, you could have videos, you could have text probably. So that could result in different memory access patterns. And based on that, maybe we would be able to understand the content sort of. If we had like a few options, we would be able to guess which option is more likely. But if it's like an open world setting, just like billions of pages in Reddit, I would say that it's more challenging to understand which exact pages being accessed.
Okay. And the last one is, this is a cool attack, but there are like more critical attacks than that in the wild. Yeah. So can we also perform those as like side channels, like let's say stealing an RSA key, for example?
So there are works that show that you can use memory access patterns to leak some information about those. I think we would be able to leak some information. I would need to check like if we can leak it completely. That might be possible. Other than that, I think if you make the attack more powerful by allowing it to collocate with the victim on the same level, like on the same DRAM row, maybe you would be able to leak more information like the activation counters, the content of the counter, for example. But that also requires different, like that has different challenges like the synchronization and so on. So you need to make sure that the victim is executing first and then you have to execute and so on, which are fine in some settings, I think. But I guess like more powerful attacks or more critical attacks would have different challenges than what we discussed today. But it's certainly interesting to look into those.
Okay, yeah, that can be some future direction anyway. Are there any other questions? No? Maybe I'll ask once more. Did you really not find any DRAM module that implements RFM? So not RFM, PRAC.
PRAC, no.
And did you look at like all the major manufacturers?
So we checked this a while back, like last year, November or October. So at that point, we didn't see any module that implemented PRAC in specific. There were modules that supported RFM, but they did not require it officially. So the memory controller has no reason to send an RFM command in that case. So we were not able to have a real system with both of these at the time that we were looking into. Maybe now there are. I also doubt that. I think still the time interval between the introduction and now is not maybe that much.
Okay. That's quite surprising. Maybe they know about this issue and they don't implement. Anyway, yeah. I'll ask once again, are there any more questions? No? Do you have some final thoughts to add?
Sure, yeah. I think so we sort of covered this timeline of RowHammer read disturbance in general, with like starting with the vulnerability. We saw like different patterns. We saw different that vulnerability getting worse, and then we covered some low-cost mitigations. And at some point, we introduced some industry solutions that make us think that the industry is taking this more serious now by making it a feature in the specification. But there's still some work to do in terms of evaluating these mitigations and also considering security as a whole and considering like different aspects of security like timing channels before adopting these or while adopting these mitigations and having them widely available. So I think it is very exciting for us researchers to design and evaluate secure systems. And it is very exciting to work on read disturbance in this time. So if you are interested in working, you can contact us.
I must add that you can contact Safari, and I'm also creating my own group in CISPA, so you can also contact me. I'll be hiring in the winter time, I think. Okay. Yeah.
Okay.
Thanks a lot. Let's thank the speaker first. And last thing, could you stop sharing so I can show the website from here? You did? Can you put Zoom over there? Oh, I'm not sharing. Okay, let's see. I think we can figure this out. Okay. So just a reminder, so this is only the first day and hopefully the longest day. The other days will be shorter, less tiring. So the second day will be on Monday, July 14th, and it will focus on health applications. And we will have Can Firtina, Nika Mansur Giyasi, Zülal Bingöl, Konstantina Koliogeorgi. I butchered your name, I'm sorry. And also Lucas Brightwieser. So we don't have it in the picture, but we have the program here. So these are really interesting talks on bioinformatics and agent-based simulations and all sorts of health applications, I think. So please look at the program and attend in person, preferably. Thank you very much. This concludes this day. Yeah. See you later.